Good morning, everybody. Fellow friends of GCOS, so happy to see you all. And thank you for being here. This means a lot to us. And for those of you who don't know me, I'm Suma. I'm a cardiologist at the University of Minnesota. And I'm co-hosting the summit with my friend and colleague, Dr. Blaes. So today is day 2 of our summit. Yesterday, we were thrilled to see about 250 attendees, and more attendees today, and we'll have a fantastic lineup of sessions for you, focused on some of the clinical perspectives of cardio-oncology. Before I dive in, just want to give a big shout out to all the audience here. Without you attendees, I don't think the meeting would have existed. A big shout out to our GCOS board members who have sort of helped us through the logistics of conducting this summit, our organizing committee, our speakers, moderators, and also to our sponsors. And please take a moment and walk around and learn about some of the novel products and other devices that are very relevant to patient care. I think, without further ado, I'd like, introduce our dean, Dean of the Medical School, and add one to that. We're really excited all of you are here. For those of you I haven't met personally, and Blaes, I'm one of the medical oncologists, and I'm co-host this morning with, for the meeting with Dr. Konety. So you're not here to hear me this morning. You will later on, but we're really excited that you're here. Spend time sort of meeting with colleagues and asking good questions. We had a wonderful day yesterday with really pretty rich science, and I know the nurses symposium as well was very robust. Without further ado, I have the pleasure of introducing Dr. Tolar. Dr. Tolar is the dean of the University of Minnesota Medical School and is a distinguished McKnight University professor in the Department of Pediatrics, bone marrow transplant. And you may ask, we get the wonderful privilege of being with Dr. Dean Tolar this morning. And with his experience and time over the last several decades as a pediatric heme specialist, we're really delighted to talk to him this morning and to kick off the meeting. Thank you.
Well, thank you, everyone. Thank you, Dr. Mike. Thank you, Dr. Konety. It is truly an honor to welcome you to the Global Cardio Summit of 2024. And let's start with the important stuff. There has been a lot of research yesterday, and I am always inspired by people who go behind what we see in clinic and in the operating room and try to uncover what is the mechanism behind what we see in health and in disease. It is important because having this summit in Minneapolis is almost symbolic, because if you look at the field of cardiology and if you look at the field of oncology, some of the most important discoveries and advances have been done here. So I'm going to do the non-Minnesota nice things. We are supposed to be like humble and let other, okay, I'm not from here. I grew up on the other side of the Atlantic. So, just think about this. The first open heart surgery that the Lillehei, Barco, and the team, the first time people were able, it's still, I have chills just thinking about reading and then thinking about Lillehei closing the VSD and ASE blindly in a beating heart under 3 minutes. It's just almost impossible to think about this. Just the dexterity, the pressure, the ability to do that. And I have a pronounced admiration for that group, and also have a living memory of this, because one of the regents of the University of Minnesota was number 6 patient on his trial, and the first one who lived. Then you have Bakken and the pacemaker. That was the collaboration between the two and other people. Then you have added plans with the status. And then you have a series of things in cardiology, including the involvement in the immune system and including of some of the stem cell work that has been such a prominent part of the research that we have done here. And then you take the other side, which is the oncology, my data, bone marrow transplant. So the first ever bone marrow transplant that was successful from allogeneic pairing has been done here by Bob Hood in 1968, and in part why I came here with my family in 1992 from Cambridge in England. And then many other things. The first treatments for lymphoma, the first really decisive changes in some of the solid organ tumors came from here. So I think that there's a lot of symbolism and a lot of things in the legacy of being here in this city and having this meeting exactly here. The legacy, though, is not enough. We are obviously looking to the future, and like with Edmund Burke, you look, to the past to give you the directionality for the present, and you think with the horizon of 25, 50 years ahead, because that's what science is, and that's what the surprise, in science is. So one of the surprises of my lifetime has been the phenomenal work of Dr. Blaes and her team, and many other people here, but also in the whole United States. But one of the first things in survivorship have been done here in Minneapolis. And it is one of these things, that are like a gift, because we didn't have a challenge, if you will, a global challenge of survivorship, including cardiac health and heart disease and cardiovascular health, before we were able to treat cancer. Because as I hope people realize, 50 years ago, 60 years ago, everybody who had cancer died. And the ones that didn't die don't have cancer, it's something else. So the fact that we are able and have the honor and privilege of treating my patients and other people's other oncology patients at all is phenomenal. Though the increase in mortality from cardiovascular disease in cancer survivors is about 2 to 5 times higher than general population. So that's why there's this continued focus and the continued ability to get better at what we do. So I'm very grateful to all of you for being here, combining your minds and establishing networks of networks, because most of the blogs today are built, for information and equally for interaction. And I have always benefited from the recombination of ideas among people who come from slightly different areas of study. And myself, being an example of this, because I never got the career reward in my field. Actually, my career reward from American Heart Association, because I was trying to figure out how to incorporate some of the stem cells that were derived from the induced pluripotent stem cells into the cardiomyocyte. And one example of how science is sort of an experimentalist point of view that I think is helpful in societal, in personal, and in scientific and clinical issues equally, is that we are built for uncertainty and we are built for surprise, because ultimately the serendipity that science of many of us have seen is what brings the advance. So in my small, minuscule experiment that I got funded by American Heart Association, I injected the stem cells that were poised to become cardiomyocytes into rodent models of myocardial infarction. And the idea, of course, Bill, that those are graduates for it, that they will incorporate and help build function in the infarcted heart. And I set up the control group in a way that these controlled cells have to be rejected based on allogeneic mismatch. And to my surprise, which I will never forget, is that the ejection fraction actually restored in the control group that rejected the cells and not in those that engrafted themselves. That was pretty cool because that led us then to map the immune system and the inflammatory and rejection, in fact, parts of the equation, and then link that to the restoration of function in the heart. So with that, you have a tremendous meeting in front of you. I am profoundly grateful that you are here and that you can live with us the symbolism of the legacy of the University of Minnesota in both cardiology and oncology, and that you will, with the leaders behind me, able to advance it even further. Thank you very much.
Good morning, everyone. Oh, what a phenomenal meeting. I want to congratulate Dan on just a terrific meeting and for bringing us all together. My name is Dr. Bonnie Key. I direct the Alzheimer's Center for Oncology at Penn, and I also serve as energy with JACC Oncology. And I had the extraordinary pleasure and privilege of sitting down this morning next to Stephen Petrow. I just want to say a few words about Stephen. So he is an award-winning journalist. He's a contributing columnist to the Washington Post. He's also written for the New York Times. And he's the author of several books, including Stupid Things I Won't Do When I Get Old, and then now published The Joy You Make. And actually I have my own autographed copy, so I feel very grateful for this. It does bring me joy. For more than 2 decades, he's also been a volunteer at the Memorial Sloan Kettering Cancer Center, and he offers a highly impactful and inspiring perspective as a patient himself, and also as a brother and a son to his sister and to his mother, who had lived and unfortunately passed of cancer. We are very grateful to have him contribute a patient perspective to JACC CardioOncology when he publishes today, and which he dedicates to his sister Jolie, who passed away on June 30th, 2023, due to complications from ovarian cancer. But who we know and gives us great hope that she is with him every day. And I also want to thank you, Stephen, for sharing her with all of us through your writing. And thank you for being here today with us at GCOS 2024 to share with us a patient perspective, your patient perspective. Thank you.
Thank you, Dr. Yeah, having big white coat syndrome this morning. I hope everybody takes blood pressure. No, even though you're not white coat. Well, I want to thank you for being my conversation partner, and Dr. Blaes and her staff for inviting me here today. And it really is an honor to be here. One thing that is part of my history that you didn't mention is that I'm a testicular cancer survivor. 40 years this past March, and I gave a talk at MSK probably about 3 years ago. And at that time, my mother and my sister were still alive. And I said, and I had a sister-in-law who was also being treated there. And I asked for a volume discount that I didn't get that. But one of the reasons I'm here is that I wrote an essay in the Washington Post a little while ago about the cardiotoxicity, and I often write about things that personally involve me. And so I was very late to coming to understand that some of the heart issues that I was experiencing were related to the medications that I had, especially. And one message I had in that article was I was seeing a cardiologist, but he was unknowing about this association. I think he had not, and this was the early 2000s when I first started treatment there. And he put me through, a lot of tests, and I didn't have heart disease in my family. I was super healthy. I don't look generally like someone that you think has heart disease. But my coronary calcium score was about 200 20 years ago, so you can imagine what it is now. And I became an advocate for myself, which I often urge other patients to do, especially in an area like this where we're still learning so much. It's so important.
Yeah, exactly. Still learning so much and learning so much together. Stephen, take us back a little bit in terms of what it was like to be diagnosed with testicular cancer at a young age. And then how did you even come to get screened with a calcium score? Tell us a little bit about that whole journey and the different scars also that you faced that you've written about.
So I was 26 when I was diagnosed with testicular cancer. It came out of blue. Was very unknowing about such things, and cancer was for older people. And I know better now. I had 3 surgeries. I had orchiectomy. Last night I was reading, and I told the story about how I got into this argument with the nurse over the size of prosthesis that I wanted when they were still doing that. And I was like, I want the extra large. I'm like, that's not her size. And carrying her at MSCE had to come in and like arbitrate this. But that was one. And then I had the archaeology. That's a big one. At the time, this seemed so disfiguring, so much of a reminder of the bad part, but the illness. But now, when I look at my body, I say, well, I've come through a lot. And when I talk to other people who have scars, that's a different way to look at what's happened to us. And it's sort of a visual memory that we can carry.
Resiliency.
Yeah, resilience and strength, and all of that's a bit.
How did you first come to even get a calcium score, see a cardiologist? How was that transition? And in CardioOncology, especially for survivors, adult survivors of childhood cancers and adolescent young adult cancers, we often talk about loss and transition. We see the patient, they're not sure what they received, or also getting them back into the clinic and caring for them and screening for cardiovascular disease. So how can we as doctors do better there? Again, as a field, do better there?
Yeah, that's a very good question. I don't have the definitive answer to that. I can speak from my experience where after my treatment, I think I was followed by MSK for about 10 years of survey, how was I doing? And then that ended. So that would have been sometime in the 1990s. And then I was lost in transition and translation. And I think that's a real challenge. People move. I was treated at a time when we didn't have electronic medical records, so I really know where those records are, to this side of them. Our parents, if you're a young person with cancer, you don't even have your medical history to count when you're trying to figure out these things. It was really serendipity that I wound up having the calcium score done. I was working with a cardiologist who went doing a trial, and I said, "Oh, I always sign up for everything." So I said, I'll do that. I signed up with 3 colleagues. They had zeros. I had my score. And but that was a real turning point for me to begin to learn more. And I did. One of the conundrums that I raised in the column that I wrote that was, not all patients are the same. I am very much a kind of person who seeks information. But other patients, they want only what the doctor wants to tell them and nothing more. They don't want to go outside of that. So it is hard to exactly how to interface with patients, especially when oncologists, cardio-oncologists, everyone is so busy. But survivorship programs just need so much more focus in, I think at the time of treatment, so that you kind of graduate into them in some way. And it was really like when I interviewed Dr. Blaes a couple of years ago, that I understood how prevalent they were and the types of services that are got here. And I was like, wow, I'm not even in one yet.
No,
but you're my doctor on Zoom. She's not practicing.
a lot of time we talk about, and there's certainly, we believe that survivorship does start at the time of diagnosis, and that we are there as physicians and as care providers with our patients every single step of the way from day zero in terms of that. And it's just so important in order to help our patients live longer lives. I'd be interested in your perspective too about what more we can do as doctors and care providers. So you talked in the Joy You Make and in other pieces that you've written about the gentleness and directness of the oncologist, Dr. Konety, and her sister Julie. And what do you think we can do as physicians and as nurses and as care providers? What can we do more to support our patients and our patients' families? Because we know it's such a tight network, and to support the whole coalition.
Yeah. Well, I'm also glad that you mentioned nurses. I am such an advocate of nurses of all kinds. When I was seated at MSCE, there was a nurse who really took care of me. And then when my mother was admitted there 25 years later, Mercedes Conde, who had really moved up high, came down and was helpful to my mother. So thank you, nurses, for everything that you put up in the tree. And I also want to be nice to the doctors. And I will tell you, so after this poem was published, I got calls from Dr. G. I had already talked about Blaes, Dr. Selly. So many cardio-oncologists reached out to me wanting to see what more they could do and see if I could help them. I've never had that experience with another topic that I've written about. So I'm very grateful to all of you who are really working hard to try to bring this field into the future and to our minds, because I don't see that kind of energy from other disciplines. So that's one big call out to you.
It's just an amazing group, amazing.
You look amazing.
I think it's like
and so this book about joy is partially about how you treat people. It says a lot about how others will treat you. And I think that's true in our personal networks and even in the medical setting. And I have always been of the mind, treat people with respect, treat doctors with respect, because that's how they give out. But Julie's doctor, Dr. Jaiswal, was looking on Call of Duty, really being a healer to our whole family in a very big practice. And I think that he did this with his other patients as well. He wrote something before the book, and in the end, it's not for me to tell you how to manage your times, but I do know that small efforts, gestures, touches when appropriate, they all communicate empathy in ways that knowledge itself doesn't. Certainly all have the knowledge, and obviously patients are scared, and that can often be one of the biggest students of development.
It is such a scary time, and that fear sometimes in the office when we're sitting down with our patients. It's very, very powerful. So thank you for just encouraging us and just setting us on the right focus and emphasizing those little touches. And I think it does make a huge difference to let people know that you care.
And I was rereading the comments to this column yesterday, and there were more than 600, which gives me a lot. And so many of them was from cancer survivors who had now developed various forms of heart disease. And those who were diagnosed, let's say, maybe before 2000, this had come as a complete surprise. But it does seem that you're generally doing a better job, as you understand more, in conveying this information to your patients, so that it is not this total surprise. And as for myself, I think in 1984 when I was treated, I was so lucky that there was this regimen, because people with testicular cancer had not done well for that. And so had I been asked about a possible trade-off, well, of course I would have chosen life. I always felt that if I lived 10 or 20 years, that was gravy. Now I think people need to be brought into that conversation a little bit more. Transparency, and then we get to make that decision in concert with them. I really like this notion of partnership between patients and doctors and employers staff.
Share this video linking and involving the patient, the whole team, cardiology, oncology, everyone, multidisciplinary team, and the patient and all of our decisions. Absolutely.
Yeah.
Cool. Let's talk a bit about your book, The Joy You Make, just released September 10th. Congratulations. We congratulate you. It's a phenomenal read, and I think we all need more joy in life. And you talk in the book about the joy of gratitude and authenticity. And I just want to quote some brief parts that I think are highly relevant to our everyday lives, but also to the cardio-oncology community. Happiness is about me, but joy is about we, you and me, and all of us together. We're a growing field and building this field together. It's about all of us. Also, having love be so bright it is blinding, because I think really to have a love for our patients and to have a love for each other. And particularly also in the book, you talk in the chapter, The Joy of the Cancer Ward, you speak of two patients that you visited with. I would have named Peter and Mary, but
not their real name.
Was their real names, yeah. And how through sharing with others and through helping others, you learn more about yourself and about resilience and the joy and shine. So just share with us more about this.
So I started working on this book the year my sister was diagnosed, and same year my mother died of lung cancer and my father died of another ailment. And it was a challenging year for me. Things were fairly compressed, and I felt that there was no joy in my life. And I know many people feel that way. And part of what my search led me to understand is that joy manifests many different ways at different places. I had thought about joy to be the birthday party, the wedding, anniversary of Christmas, the big explosion of joys. But there are quiet joys, there are sweet joys. And so for many, many years, I would go back to the cancer ward at MSCE on Tuesday nights, and I was in a program called Patient to Patient. I could actually be visited when I was a patient by men in Alan who would just come in and talk to me, showed me a scar, and I came away thinking, he survived. And so I participated in that for a long time, and every evening, it was quiet. We could talk. The armor that we often wear in our lives to protect ourselves, it was gone. And maybe because he was having chemo and he was weaker. But when he realized that I had been through what he did, that really that gave him a lift. I felt that the gift that I had received had been passed on. And with the other woman, she had a cancer of the appendix, so it wasn't matched, but there was nobody else that night. And she asked me about fear. And that was a time when I really was trying to manage my fear with medications, not successfully. And I had actually found that by coming to MSCE once a week, it allowed me to be in touch with it in a container and to be with other people who were experiencing that. And it kind of got negated. And I was able to talk with her about the fears that I had and that I did have, and she did the same. And this kind of vulnerability opened us up in a way that just doesn't generally happen in my life. So that's part of the joy of the cancer ward that I talk about, just being able to really connect with people, because I think whether you're a doctor, nurse, journalist, we live in a world that is polarized, an epidemic of loneliness, mental health issues are rising. We need connection and be real, raise joy. That's what I've learned along the way. There are 28 other stops on both that take you out of the hospital if you don't want to go there.
Well, Stephen, thank you so much for sharing with us, for being with us. and just for being authentic and for sharing your joy with all of us. Truly impactful and truly inspiring. Thank you so much.
Thank you.
Well, what a great way to start this meeting. Truly inspirational. I think, that's why we are here doing what we do. So my name is Susan Dent. I'm a breast cancer medical oncologist at the University of Rochester in New York. And I'm currently the president of the International CardioOncology Society. So I just want to take this moment on behalf of ICOS to welcome you to this annual Global CardioOncology Summit. I remember when we had our first meeting in Nashville, Tennessee, and we had a few people. I mean, it wasn't a bad turnout, but it truly is remarkable to see how this meeting has grown and the interest in this meeting. I also want to take this moment to thank Dr. Blaes and Dr. Suma Konety and their team for pulling this together. It's always very stressful. I know it's a hard go. It's a lot of work, a year work. So I want to take this opportunity to thank you at the beginning of this meeting. Congratulations. Let's give them a round of applause. Actually smile now, but there's a lot of sweat and equity that goes into bringing this meeting together. I also want to highlight that this year we're celebrating the 15th year of my, which is truly remarkable. Congratulations on that. I want to remind everyone that this was really, this organization is formed by a number of people who came together as interested parties. We had a few meetings in different parts of the world, but really it's grown into an amazing organization. So I want to thank everyone that has come to this meeting, the speakers, the attendees. I know we all have very busy lives, that we have many commitments, but thank you so much for coming, because without you, this meeting would not be successful. So thank you, and let's go on next session. Thanks, everyone. Thank you.
Well, thank you, Susan. Good morning, everybody. I'm Joe Carver. Sometimes being the moderator is harder than giving a talk. So I was stopped a couple of years ago, and after doing this, and somebody said I enjoyed remarks, but I liked them better 5 years ago. So I've been thinking about what to say and welcome you this past weekend. Just I heard this story of father and son, 5-year-old kid sitting on his father's lap, and reading, and the kid says to his father, "Does God destroy things?" Father said, "Well, sometimes yes," and then he's really worried about what is coming at us, and he says, "Does he destroy marshmallows?" So, not that the mentality much more than the 5-year-old realized what marshmallows are. Marshmallow trees, and that's like CardioOncology. The serial work, the Siddartha will talk with the oncologists, the marshmallows are the cardiologists together, how we come together to make a tree to take care of patients, do a better job. I thought, what could you do to make that even better? And that's really what this section is all about. What about, by the way, now is the landscape changing? So, I just had I don't know how to insist. So what I'm going like this, which are basic science translation, stratification, tailored therapies, protection, better outcomes, and less toxicity. So when this is over, where can you get more education? Well, GCOS 25, Johannesburg, in Cape Town. ICOS has a whole array of educational materials. The session is sponsored by JACC Oncology, and don't forget that there's another, the original CardioOncology journal, CardioOncology journal is out there, and every week I post webinar Thursday mornings at 9 o'clock. It's an ongoing educational experience. So, in some ways, we really are a treat for each other and our patients, and we evidently get better tasting. So the landscape is changing. It's a pleasure to introduce Bonnie. She sort of semi-introduced herself, Dr. Bonnie G, the director of the Fail Member Center for CardioOncology at Penn, editor-in-chief of JACC CardioOncology, and Thomas Force Award winner. And I'm one of only two people who have a dedicated academic chair in cardio-oncology, and really a dear friend. She was my resident, and now she's my teacher, and it really is true. And so, not known by many people, when Everready decided to form the body, that Bonnie's work ethic and passion for life and everything, and style was the model for that Everready body. So, Bonnie, what yours?
I'm going to take a moment and just thank Joe for just being an amazing mentor and just for helping to start this field and for bringing us all together and for just, a lot. And also wanted to thank and congratulate Suma and Ann on seeing Lisa so many in this room that have made this an amazing conference. And thank you for the opportunity to share with you my perspective on what I think are our cardio-oncology priorities and highlights in this JACC CardioOncology session. So what do I think are our priorities in cardio-oncology science and clinical care? I think fundamentally as physicians and as scientists and as care providers, we have the role and the responsibility to advance actual science in the delivery of augmented, evidence-based, and rapid care to our patients so that they can live longer, healthier lives. And how can we go about doing so? How can we together as a field work to grow and build and define the field of cardio-oncology for our patients? And what do I think are our actual strategies and priorities? And I want to share this with you over the next 12 minutes or so. Number one, I think we need to define the basis of cancer and cancer therapy associated with cardiovascular disease in the modern treatment era in 2024. Ask and answer, in whom does the cardiovascular disease occur? Why does this occur? And then how can we use this understanding to best mitigate the risk of cardiovascular disease? And then also from a basic mechanistic standpoint, how does cancer increase cardiovascular disease risk? How does cardiovascular disease actually increase cancer risk? This really exciting, exploding field of bidirectional cardio-oncology. And then how can we further translate the mechanisms, the basic mechanisms of disease to our patients? And there's been a lot of really great work in this area, really elegant work by Arrythmias and Heme team that's detailed how anthracyclines can result in cardiomyocyte atrophy, result in changes in mitochondrial quality and changes in cardiac metabolism. And then using this knowledge to inform best strategies to mitigate risk of cardiovascular disease, such as remote ischemic conditioning, trials that are currently underway in Morris Lab. And then very elegant comprehensive work by Paul Burge and Nada Sapkota detailing how you can use iPSC cardiomyocyte model to uncover the genomic basis of cardiovascular disease with anthracyclines. Use this platform to then functionally validate these pathways and then use this knowledge to better design pharmacologic strategies to mitigate the risk of disease. And then again, of course, this really exciting work in bidirectional cardiology. You've heard about this yesterday as well. Work detailing how post-myocardial infarction, heart failure through the NGF-TRK aspect can actually induce tumor growth. And this follows really exciting work from Catherine Moore, Rudolph de Boer, many others that suggest how the immune system and inflammation, post-myocardial infarction, post-heart failure, can increase tumor growth. Number two, I think we need to understand individual patient risk, the patients that we're seeing in clinic and everyday practice, the patient in front of us. How does our individual patient's absolute cardiovascular disease risk, what is it in the context of the competing risk of cancer, particularly as we advise about the safety of different cardiovascular therapies? I think in the field we talk a lot about relative risk, but I just want to remind everyone that absolute risk is also critically important. And then what imaging, biologic, social, clinical factors most accurately predict and precisely explain cardiovascular disease risk? And then what are the most practical, evidence-based, and cost-effective screening strategies? We know that traditional cardiovascular risk scores perform poorly in our cancer survivors. Why is that? Number one, they were derived in non-cancer populations and not validated in cancer patients. Number two, they do not include cancer-specific treatment barriers. We know that's the major insult that our cancer patients undergo. And this work has been very nicely detailed for investigators from the UK, including Charlotte Lannisty, how traditional cardiovascular risk scores across various cardiovascular disease states and across various cancers perform poorly. Work, however, from the Dutch Childhood Cancer Survivor Study suggests that if you take a clinical model that does include cancer-specific variables such as anthracycline dose, radiation therapy, agent diagnosis, and add on to it NT-proBNP and high-sensitivity Konety, very high negative predictive values on the order of 95 to 99%, suggesting that you can use this type of approach to avoid unnecessary medical screening. Number three, I think we need to accurately and precisely identify cardiovascular disease and really ask and answer as a field how can we best characterize cardiovascular disease with high accuracy and precision. And really, this is across the globe, not just in North America, not just in Europe, but really across the globe. And what is the role of imaging and biomarkers as well? We have gotten so good at detecting subclinical disease, but what is it role in the long term? And what is the role of AI? A lot of excitement in medicine overall, and really in society about AI. But how can we use this to better detect disease? And work led by Siri Heck in the PRADA study, Victoria Notland and many others, Ida also suggests that troponin elevations during anthracycline chemotherapy in the PRADA study are not associated with subsequent rate declines in ejection fraction. And moreover, she called into question what thresholds should we be using as it pertains to biomarkers in terms of defining risk. And then, of course, strain. There has been a lot of excitement in our field about the role of global longitudinal strain. Of course, Dinesh and Tom have done phenomenal work trying to inform the science here. But I think as a field, we still really need to decide, is there any real clinical role for global longitudinal strain outside of the world of amyloidosis and screening? But what exactly is that? Moreover, AI. A lot of excitement towards AI, and York Harmon and colleagues have suggested that you can use AI ECG to better predict CLL patients who are at risk for BTK inhibitors. And we're also applying AI to the field of radiation oncology, where we can use AI-derived algorithms to derive Cornelius obstructive nodes. This is work led by Ray Mack that suggests that you can use this to derive dose, for example, to the power of 8, to the LED, to the left southern and so on, and then predict risk of subsequent cardiotoxicity, including arrhythmia. Number 4, I think we need to develop innovative cardioprotective strategies that target cardioprotection according to risk, and ask and answer as a field, what are the most effective cardioprotective strategies? Are these feasible, safe, and tolerable? And which patients will derive the most benefit? And what are clinically meaningful endpoints? And how can we design the best studies? On our weekly JACC CardioOncology editorial board meetings, we talk about this a lot. What is a clinically meaningful endpoint for these studies? And then what your cardioprotective strategies might exist. And recent data from the PROACT study suggests, at least in the short term, this was definitely short term, 1 month post anthracycline chemotherapy population, ACE inhibitors did not have a significant effect in anthracycline treated patients. Small study, about 111 or so, in terms of troponin EF or local stratigraphy, calling into question what we should be doing in 2024. And a lot of excitement with SGLT2 inhibitors, like really intriguing and exciting retrospective analysis led by Dr. Konety and Dr. Body, publishing today in JACC CardioOncology. And of course, a lot of basic science and mechanistic evidence suggesting that there may even be oncologic benefits in terms of SGLT2 inhibitors, with randomized clinical trials underway as these the CardioOncology. And a lot of excitement too in the field, I'd say, for non-pharmacologic therapies. And I think in general, patients would prefer, many of our patients at least would prefer this answer to that. What is the role of exercise as a cardioprotective in terms of reducing fatigue, which is so many of our survivors of cancer suffer from? And what is the role of Mediterranean diet? How should we be counseling our patients in terms of the best strategies to protect the heart? Number 5, I think we need to implement equitable, inclusive, high-quality care. And again, this is bold. And really determine as a field, what are the standards of care that our cancer patients should be receiving? What is guideline-directed medical therapy for our survivors of cancer? And the standards are not being met. Why? Go past the simple description that it's not being met, but then watch. And then ask and answer as a field, how can we deliver the best possible care to our patient, to the right patient at the right time and in the right place? And work led by Mamas. Mamas suggests that if cancer patients admitted with a myocardial infarction compared to those without cancer do suffer from disparate care in terms of angiography and procedural rates, in terms of guideline-directed medical therapy, and they also suffer from an increased heart failure readmission rate. And I think we also need to talk more about cost effectiveness. And a study that we recently published in JACC Oncology is a step in this right direction, suggesting that in breast cancer patients who are receiving left-sided radiation therapy, that deep inspirational breath hold compared to standard of care resulted in an improvement in the cost effectiveness ratio in terms of quality adjusted life years for our patients, and also risk reduction in cardiovascular disease risk. And in closing, I just wanted to take a moment and to really thank all of you and to share my gratitude for all of you for really just being an amazing community that really is cohesive, that works to drive forward science together, and is committed, highly committed, saying, to growing and building this field together. And it really is for our patients. And I just want to urge all of you and each of us to continue to seek the evidence and to fill the gaps in evidence. And to this end, JACC CardioOncology will be publishing the first to release tomorrow, a 3-part series, cardiovascular considerations before, during, and after cancer therapy, really focused on highlighting what are the gaps of evidence and what do we need to do as a field to continue to move the field forward. And I want to thank the lead authors of each of these series, Dr. MSCE, Dr. Long, Daryl Mill, and Ann Blaes for leading each of these series, and the many, many authors who have contributed to these, as well as Tolar All who served as guest editor. And with that, I want to thank you very much for your attention and our
As always said, and inspiring and example. It's my pleasure to introduce Dr. Konety, a professor of pharmacology and medicine at here in Minneapolis, director of the Simon Cancer Center, and one of the lead people in the I-SPY series. He's a breast cancer oncologist, and I-SPY is similar, I guess, to all the TIMI trials that it really is game changing and just a very interesting way to continue to do breast cancer research. These currently wonderful people and principal investigator of I-SPY 2. And it's a great pleasure to have you with us. Great to hear what are the highlights in oncology.
Thank you for that introduction. Really thrilled to be here and to give this talk. I told Dr. Blaes this many times when I was in training, never ever talked about long-term complications of cardiovascular chemotherapy because the whole goal was to get people to survive their cancers and nobody cared about survivorship. So it's great to see that this conference is being held. And as mentioned, I'm also director of the Sonic Cancer Center, so I just want to recommend the hours. So these are my disclosures. I'm going to talk only about unlinked healthcare collaboration, which is a sponsor by SPY. Like Drs. Dent and Dr. Blaes, I am a breast cancer medical oncologist, so I'm going to filter this talk through the athletics. This is a model of breast cancer mortality, and the dotted blue line, that's on the pointer up here. I'll just people on that side that can only really see this side. The dotted blue line there is the actual reduction in breast cancer mortality. The modeling in this looked at screening, better metastatic treatments, better treatments to stage 1, 2, and 3 breast cancer, and then all together. And you can see the red line showing that screening and better therapies actually account for the decrease in breast cancer mortality since the 70s. When this was pulled apart, taking a look at actually what decreased the death rates from breast cancer, you can see screening in the yellow bar has mainly been stable over time, but the increasing improvement in treatment for metastatic therapy, which is the blue line, and in the world of drug development, those metastatic therapies are then applied to earlier operable breast cancer, which is stage 1, 3, really demonstrates the increase in survivorship based on better therapies. So with that in mind, that I do apologize to the radiation oncologist and surgical oncologist in the room. This breast cancer is a medical disease, and better medical therapies are really responsible for driving the decrease in breast cancer mortality. So what have we learned about breast cancer? It is a very heterogeneous disease. There are sort of simplistic, in my mind, classification. Most breast cancers are luminal, about 70%. They express either the estrogen or progesterone receptor or both, and we just lump those together as hormone receptors. HER2 amplified breast cancers account for about 15%. Triple negative, which is none of the above, are about 10%, and triple positive are 10%. And those of you that are good math realize that it doesn't add up to 100% because of triple positive fall on both cases. We have learned that specific medical regimens depend on the subtype. We also well know that there are cardiotoxins that are in the regimen, so that decrease in mortality I've shown you is driven by the use of anthracyclines and trastuzumab. So one way to decrease the use of toxicity of these drugs, cardiotoxicity, can be avoiding or minimizing the use of those drugs, and that's what I would like to spend some time. So we've spent a lot of time trying to understand who needs chemotherapy. I realize that most of you are not breast medical oncologists, but molecular analysis, what we call the 21 gene assay, which has been commercialized since the only time of MSCE, and there are others, identifies patients who cannot get chemotherapy. I want to show you that this is an assay that uses reverse transcriptase PCR of 21 genes that creates a positive score, either low, intermediate, or high risk. The retrospective data arguing that the low-risk patients really did not benefit from chemotherapy. The high-risk patients and patients who were in the intermediate group was unclear. So 2 clinical trials, Taylor-X and Respire Responder, examined this in a prospective assay. I'm just going to show you the Taylor-X data. which were node-negative patients. So as mentioned, the low-risk patients, we had assigned endocrine therapy. This is a big trial too. You see the roughly 10,000 patients were randomized on this trial. The high-risk patients received chemotherapy alone, and the middle-risk patients received either what was then the experimental arm, and whenever the trial says experimental arm, the standard care arm is chemotherapy and endocrine therapy, and the experimental arm is endocrine therapy alone. This demonstrates that in this intermediate risk subgroup, there's absolutely no benefit for chemotherapy. And if you then ask how many patients that are, that's about a 75% of the patients receive no benefit from chemotherapy. So I'm not going to talk about the long-term toxicity of endocrine therapy. It is something to be considered, but for the most part, most of the luminal breast cancer patients can avoid chemotherapy. So if they avoid chemotherapy in that setting, we will ultimately avoid chemotherapy associated cardiotoxicity. One of the things, though, that keeps popping up is, well, what kind of chemotherapy are we talking about? This is a meta-analysis that compared anthracycline-containing regimens and taxane-containing regimens in early breast cancer, 100,000 patients, 86 randomized trials. And if you look at that particular graph, Dr. Keith pointed out, we know that the anthracyclines told us targeted toxicity. There are multiple mechanisms of this. In each subgroup, in this large meta-analysis, there's a slight increase of benefit for taxanes plus anthracyclines on the 1 to 2% range, with a very small but statistically significant reduction in recurrence as well as breast cancer mortality. So, a lot of people look at that and say, well, okay, if that proves that the anthracyclines are still required in breast cancer therapy, the other way to look at this is to say, well, that's a very small benefit. So can we figure out who doesn't need an anthracycline? I think maybe we've done this best in the subgroup I mentioned that were HER2 positive. This is a clinical trial, BCIRG 006. It was done a long time ago, but they have long-term cardiac follow-up. So this trial, all patients got chemotherapy. So they either got, you can see doxorubicin cyclophosphamide followed by paclitaxel. That's a ACT arm. That same arm plus trastuzumab. This is a very early trial showing that the HER2 targeted monoclonal antibody had benefit, or a non-anthracycline-containing regimen called TCH showed that. And you can see that ACT plus trastuzumab and TCH had relatively similar disease-free survival benefits. But if you look on the other graph, you will see the cardiac failure associated with the regimen. So ACT chemotherapy alone, roughly about 0.4%, class 3 to 4, congestive heart failure, with a greater than 10% reduction in left ventricular ejection fraction, about 11%. If you look at adding trastuzumab to that regimen, it increases both heart failure and ejection fraction drop pretty substantially. TCH is not perfect. It's not exactly the same as control, but it reduces the heart failure and ejection fraction drop without the anthracycline. So one argument has been made in this other 7 breast cancer patients, HER2 positive breast cancer patients, you just don't need anthracyclines anymore. We know we have to give the cardiotoxin trastuzumab and its companion pertuzumab. We don't have to give the anthracyclines, which compounds the cardiovascular. So what about the other kind of pesky group, triple negative breast cancers? We understand that they don't have either the HER2 or hormone receptor marker that clinically biologically progressive prognosis. The current standard of care, triple negative breast cancer, is based on a clinical trial called Keynote 522. This regimen gives the chemotherapy before surgery, and we call that neoadjuvant therapy. It includes the immune checkpoint inhibitor, pembrolizumab, which disrupts the PD-1 interaction and it activates T cells. The regimen, so then includes pembrolizumab. Patients get 12 weeks of taxane plus carboplatinum, followed by 12 weeks of doxorubicin cyclophosphamide, and then actually followed by pembrolizumab. So all the way through, patients are getting immune checkpoint inhibitor plus pretty aggressive chemotherapy. The FDA approved this regimen, and that's why it's on standard of care. There are high rates of pathologic complete response rate. So I need to say a word about pathologic complete response rate. This is when you get the chemotherapy prior to surgery, and then you go to surgery, there is no invasive cancer left in the breast or axillary lymph nodes. That's a biomarker associated with improved long-term outcomes, and that led to the approval because both were shown in Keynote 522. So it raises a question, do all patients need the therapy? Are there better drugs? It cannot result in achieving less therapy. So this is where we talked about two things. Are there better drugs? And can we get optimal results achieved with better therapy? So I'm going to say a word about antibody-drug conjugates. This is kind of a complicated slide in the sense that antibody-drug conjugates are complicated drugs. There's obviously an antibody, which forms the basics of the drug, and the epitope targeted with self-cancer epitope. There is a linker, a chemical linker that links a payload, which is now mostly cytotoxic chemotherapy to the antibody. So if you think about AADC, they're kind of three drugs. So there's an antibody, there's a linker, and there's a payload, and they all have kind of slightly different properties. And I'm not going to go over in all the details, but you can modify these. You can put a lot of payload on a single antibody, you can put two payloads on a single antibody, you can make the payload be an immune activator, you can change the antibody itself. So I actually think, I go on with them, I think these largely will be getting used more often and maybe replace conventional cytotoxic chemotherapy because of their potential delivery specifically to the target. And we can argue about that a little bit, but that's certainly the goal of antibody-drug conjugates. So we heard a little bit about I-SPY, and I want to show you some results that were presented at the European Society of Medical Oncology a week ago Saturday, using an antibody-drug conjugate called datopotamab deruxtecan. Datopotamab is an antibody directed against the TROP2 antigen. Deruxtecan is a topoisomerase inhibitor. And we used it in combination with durvalumab. Durvalumab is an immune checkpoint inhibitor that inhibits the PD-1, PD-L1 axis. So that's antibody-drug conjugate, immune checkpoint inhibitor in breast cancer. So the I-SPY2 trial is shown here. There it is called Block A, which is the experimental treatment that I just outlined. We assay these patients very closely. We biopsy at the end of Block A, and we get an MRI. If patients have what is shown to be suggested pathologic complete response, they can go on surgery. If they still have the apparent residual tumor, they can go on Block B. I'm not going to go into the gory details of what Block B is, but except to tell you that's conventional therapy that we use for triple-negative breast cancer now. Same thing, if it works, go to surgery. If it doesn't work, go on to the anthracycline, the TADI. So that's the highlights for people that want to know the details of drug dosing, but Block A was what we showed, but the data is. And I'm not going to spend a lot of time on conventional, but the dynamic control was because I-SPY goes over time. There were multiple control arms. So what we found in this particular trial was that nearly half of the patients had a pathologic complete response after Block A. So in other words, the experimental regimen was very effective. Almost 90% of patients had pathologic complete response after Block B, suggesting 90% of patients could avoid the anthracycline, which was seen in Block C, and everybody did, and it was pathological response. So I think the idea that you can give drugs that are better and give them sequentially is another way to avoid anthracycline. Don't just buy the whole package. So this was published simultaneously in Nature Medicine for those of you that want to see the details. Finally, I need to say a word about our other new class of drug immune-mediated effectors. So far, we think cardiac AEs are pretty rare, somewhere in the 1% range. These are all the drugs that are active in trials. And the result I talked about breast cancer, many of these trials are from other diseases. But certainly seeing, we get it. And Dr. Blaes is probably not in the grand rounds that was shown the other day about Arrythmias vascular on it. It's immune meaning. Potentially, she has a patient on a DNA or tinnitus, potentially from pembrolizumab. So it's rare, but it happens. So anyway, my last slide, how do we do cardiotoxicity cancer therapy? We want to define the molecular substance of cancer to do not better cytotoxic chemotherapy in breast cancer. That's a lot. We want to develop anthracycline-free regimens when we get better drugs to include in that strategy. Design trials in the adjuvant setting only give anthracyclines when needed. Improve chemotherapy to reduce cardiac toxicity. I did not talk about ADC cardiac toxicity, but the first one targeted against HER2 showed overall lower rates than certainly the cyclin trastuzumab reference there and monitored in check. I would be remiss if not telling you that I-SPY is a big trial. It's got a lot of investigators that I want to thank the families and patients who have contributed to the trial and for allowing me to actually present it there, and I presented that. So thanks very much for your action.
We're now allocated any time for questions. I'll get finding you around if anybody has anything unusual questions. I thank you guys. It's really good. And we're ready in the next session. We're on time. Oh.
Thank you for being on time. We'll move on to our keynote lecture. It's my distinct pleasure to invite Siddartha and Jaiswal to give us a keynote lecture. Welcome to GCOS and welcome to Minneapolis. He'll talk with us about the hot topic of health associations with clonal hematopoiesis. Just a brief introduction. It doesn't really need introduction, but people who follow this topic. But nonetheless, he started his career at Stanford and spent some time in Boston, and is currently at Stanford University as an assistant professor in pathology. He has several high-impact journals that are publications and journals that he has written on clonal hematopoiesis, or CHIP, and is well funded with agencies like NIH and the Leukemia and Lymphoma Society and the NIH Initiative. And without further ado, then to welcome Siddartha.
Dr. Konety, for that very kind introduction. It's my pleasure to be here today. I have the following disclosures. So what is clonal hematopoiesis? So if you think back to your college biology classes, you learned about the multi-step pathogenesis of cancer, typically described for colorectal cancers, where you get mutation 1, 2, 3, 4, which transforms a normal cell into a cancerous. We believe a similar process occurs in the hematopoietic system, where we have hematopoietic stem cells as the cell origin for blood cancers, acute myeloid leukemia. These HSCs acquire random mutations throughout life, most of which are inconsequential. However, occasionally mutation will arise that increases the fitness of a hematopoietic stem cell. That would be the first hit, allowing it to clonally expand. And this clonally expanded stage is what we refer to as clonal hematopoiesis. Now, if you acquire additional mutations later in life, then blood cancers may develop. Now, when we expect such process to be common or rare with aging. So consider the following calculation. There are roughly 50,000 to 200,000 hematopoietic stem cells in each of us. And we know that Each of these HSCs requires one mutation, protein coding mutation, every 10 years, which doesn't sound like a big number. But if you multiply these two numbers together, you calculate that by the age of 70, there will be 1.4 million protein coding mutations within the HSC of all of us. And if just one of these mutations is sufficient to cause clonal expansions, then these sorts of clonal hematopoiesis should result. And indeed, this is the case. So this is a graph from a paper we published now 10 years ago showing the prevalence of clonal hematopoiesis as a function of age. You can see that people younger than 40, very few of them have these clonal expansions, but the prevalence increases with each decade of life, such that when you now look at people 70 or older, somewhere between 10 to 30% will have a detectable clone carrying an oncogenic mutation in their blood. So based on these findings, my co-authors and I defined a novel clinical entity that we termed clonal hematopoiesis of indeterminate potential, or CHIP for short. It is defined as a cancer-associated clonal mutation with a variant fraction greater than 2% in the blood of otherwise healthy individuals. And as I've shown you, it's common aging. And it is indeed a bona fide pre-malignant state shown here in this cumulative incidence plot. You can see that those with CHIP have a hazard ratio of nearly tenfold for increased risk of hematologic malignancies and an absolute risk of progression of about 1% per year. So as I've told you, cell of origin in CHIP and myeloid cancers is hematopoietic stem cell. But interestingly, these mutated hematopoietic stem cells still retain the ability to divide and differentiate from all of the circulating immune cells in the body. And so we hypothesized, could these mutations alter effector immune cell function in such a way as to influence non-malignant diseases of aging? And the one that we looked at first was coronary heart disease, of course, the leading cause of death in most of the world today. Shown on the left is a cumulative incidence plot in our paper published 10 years ago, where we found that those with CHIP mutations indeed had a higher risk of developing coronary heart disease, and this risk was maintained even when we adjusted for known cardiovascular risk factors as shown on the table on the right. So of course, we wanted to replicate these findings. It was an unplanned secondary analysis. And so we teamed up with our cardiologist friends at MGH and Petrow, St. Katarina and Bidirectional, and performed a large follow-up study. So the case-controlled study using two cohorts, bioimage and von Willebrand cancer. And you can see that finding replicated in both of these cohorts. Those with CHIP mutations had a roughly twofold increased risk of developing coronary heart disease. This finding has been replicated many times. I'm not going to go through every single study on this list. I'll just highlight that a number of different associations have been shown, including coronary heart disease, that I just showed you, mortality associated with cardiovascular diseases, stroke, heart failure, and others. And then one study I will highlight that was just recently published, last one on this list. This was an analysis of clinical trial patients in the TINI cohorts. And curiously, they found that individuals who had not had a prior cardiovascular event did have increased risk of coronary heart disease if they had CHIP as a ratio of 1.3. This was not seen in those with prior cardiovascular events. So still trying to digest what this means, but this could influence how we think about conducting clinical trials in this population. So what is the biology of these mutations? How are they causing this increased risk? So one of the things we wanted to know, can we even find these mutated cells within the atherosclerotic plaques? So as many of you know, one of the most populous cell types in the plaques are monocytes and macrophages, which are hematopoietic cells derived from hematopoietic stem cells. And so we obtained carotid plaque samples from several patients. These are surgical samples. We digested them and then it looked for the same mutations that were found circulating in blood. And what we found was that there was a very strong correlation between the proportion of mutant cells within the plaque as seen in the blood, which indicates that throughout life, these blood cells are probably colonizing these plaques and potentially influencing their biology. And so how might these cells be influencing their biology, and is this causal? To address the question of causality, we performed experimental models, commonly used model in the field, are the LDLR knockout mice that had a high cholesterol diet, developed atherosclerotic lesions very rapidly in a matter of weeks to months. One of the nice things about this model is that you can condition these mice with total body irradiation to ablate their bone marrow, and then transplanting bone marrow that contains your genotype of interest to ask the question, how does knocking out or perturbing a particular gene in the hematopoietic system influence atherosclerosis? And we first did this with loss of TET2, which the second was commonly mutated genes, and then followed by Hematopoiesis. I show here are descending aortic spice after about 17 weeks of high-fat diet. See that minus that last one, where 2 copies of TET2 developed substantially larger atherosclerotic lesions, supporting the hypothesis that these mutations were indeed causal for reducing atherosclerosis. We next wanted to know if we knocked out these genes specifically in the myeloid cells using a pre-recombinase system that was expressed only in the myeloid lineage, the Blaes2 gene cream. Would we also see increased atherosclerotic lesion size? And we did this for both a loss of function TET2 model, which is the second most commonly mutated gene in CHIP, as well as the loss of function TNNT3A model, which is the most commonly seen mutation in CHIP. And in both cases, myeloid-specific knockout of these genes was sufficient to expand the cell, the plaques. And in terms of the specific mechanism, we did gene expression analyses for both macrophages that lacked TET2 as well as TNNT3A. And in both cases, what we see is enhanced inflammation, as shown by gene set enrichment analysis. So we see many pathways upregulated in both sets of knockouts, all suggestive of enhanced inflammation due to these particular mutations. And so our working model right now is that these mutations have a particular effect on hematopoietic stem cells, causing them to clonally expand. These clonally expanded stem cells produce mutated immune circulating cells, such as monocytes, which are able to colonize the plaque. And once in the plaque, they seem to exhibit a hyperinflammatory function, which may exacerbate atherosclerosis and lead to the increased clinical events that we see in people with these mutations. So to just summarize what I've told you so far, CHIP is associated with a number of adverse health outcomes, such as 30% increased mortality, a 10-fold increased risk of developing myeloid malignancy, roughly doubling increased risk of coronary heart disease, and many other studies have shown other adverse consequences associated with CHIP, such as increased risk of heart failure, chronic liver disease, gout, osteoporosis, diabetes, thrombosis, etc. What we wanted to know was, does CHIP associate with other diseases of aging, and in particular neurodegenerative phenotypes? And there's reason to suspect that this might be the case. So genome-wide association studies for Alzheimer's have strongly implicated microglia as a cell type of greatest importance. And microglia are immune cells. They are essentially the macrophages of the brain. Based on our studies, including the ones that I just told you, we knew that CHIP alters both HSC and myeloid cell phenotypes. And so it was a relatively straightforward hypothesis to ask, could these circulating immune cells also enter the brain, develop into microglia, and therefore influence neurological phenotypes? We did this in a number of ways, including a longitudinal cohort study as well as a case control study. The meta-analysis of both of these is shown here, and much to our surprise, the presence of CHIP was not associated with an increased risk of Alzheimer's disease. Rather, it was protected. So the odds ratio shown here is 0.64, so roughly a 40% decreased risk of developing Alzheimer's in individuals with CHIP. We confirmed that this protective association was seen using Mendelian randomization analyses, and we also looked at brain pathology in people who never developed clinical dementia in their lifetime, and that's shown here. So based on neuropathology at autopsy, we looked at the burden of amyloid, which is given by the CRET score, as well as the extent of tau spread in the brain, that's given by the BRAC stage. And in both cases, if people had CHIP at death, they had greatly reduced amyloid burden as well as tau spread, suggesting that CHIP may potentially be altering the pathophysiology of Alzheimer's. We've subsequently studied this in the UK Biobank data. This is unpublished, but overall we do see confirmation of this data in the UK Biobank cohort for Alzheimer's. That's the graph with the forest plot shown at the top. But curiously, this protective effect is dependent on the specific pathophysiology, as we did not see a protective effect for vascular dementia in the UK Biobank cohort, and in fact, perhaps a trend toward increase of vascular dementia. And CHIP was also associated with an increased risk of Parkinson's related dementia. So this finding is specific for Alzheimer's. Furthermore, in the UK Biobank cohort, there was heterogeneity based on the specific mutated gene. So DNMT3A mutations, most commonly mutated gene in CHIP, were not associated with protection from Alzheimer's disease in the UK Biobank cohort, but several other classes of CHIP mutations were. So can we find these mutant cells in the brain? And so we did look for this. And much to our surprise, the cells were present in the brain, but actually at quite a high proportion. And we looked in about 8 individuals, and we found that at the lower end, 30% of the microglia contained the mutation, and at the higher end, 90% contained the mutation. So between 30 to 90% of the microglia seem to be derived from these mutant hematopoietic stem cells. And when we tried to correlate the proportion of mutant cells in the blood with what we saw in the brain, that's the graph shown on the right there, you can see that there is a nearly perfect correlation, suggesting that there is probably lysosomal seeding of the brain from the peripheral blood, similar to what I showed you for gastroenteric plaques. So there are a number of unanswered questions about this finding of CHIP and Alzheimer's disease that we're actively exploring in the lab. For example, do these mutant cells have superior ability to cross the blood-brain barrier? Perhaps once they're in the brain, do they have a greater ability to proliferate or survive in the brain microenvironment? Or do they have a superior phagocytic ability? Are they just better at clearing amyloid aggregates? And so we're utilizing a number of experimental models to address these questions with the end goal of knowing, could any of these mechanisms eventually be used to create rational therapies for Alzheimer's disease? So just to end here, it's associated with a number of bad outcomes, including mortality, blood cancers, atherosclerotic cardiovascular disease. But the outlook is not all bad. If you have CHIP, you may also have reduced risk of Alzheimer's. I'd like to thank the people who did the work in my lab. Many of them were already shown on the slides, as well as all of the participants in the human cohorts that are very numerous collaborators around the world. Thank you for your attention.
Audience.
Yes, I mean, Peter made it from Italy. It's very nice talk. My question is there anything of the mutations causing CHIP also on later sites and other bleed function?
Yeah, that's a really great question. It's much harder to study that because, as you know, platelets are anucleate. So we don't know to what degree the mutant cells are contributing to the platelet pool humans. I will say that some of our collaborators, we partner the network, granted, we're studying this question in animal models, and they found limited evidence that at least the commonly mutated CHIP driver mutations had an effect on platelet function. So probably not. I will highlight one study from Beth Ebert's lab where they did look at the effect of some of these CHIP driver mutations on the process of netosis, which neutrophils can release their DNA, these neutrophil extracellular traps, which can lead to increased clotting. And some of the CHIP driver mutations did contribute to that event.
Good morning.
Go back to Stefan.
Good morning. Thank you for your presentation. With all the excitement about CHIP, how far away do you think we are from clinically viable assays? And do you think the assays will have to account for gain of function versus loss of function mutations eventually?
Thank you for your question. So if I understood correctly, you're asking, can we clinically measure this and return the results to patients? And the answer to that is absolutely so. These assays are already routinely done in hematology clinics. Right? So often patients will come in with abnormal blood counts that are unexplained, and it would be routine to get a molecular panel to assess these mutations, including both gain of function and loss of function. So absolutely, we could do this. The question is, would we ever do this for cardiovascular verification? And the answer to that right now is no, because we don't know what to do for these patients other than the routine counseling you would give anyone with their cardiovascular risk profile. And so I think that would depend on if there is a prospective randomized control study that showed that a particular drug would benefit patients with chronic hematopoiesis, and that might be a reason this might test for this cardiology clinics.
So Ronzaha, you yourself question Dallas. So thinking about the landscape that's painting here with certain negative, but certainly positive factors from CHIP, I was wondering if you can comment further on potential interventions looking at the intersection between cardiovascular disease and oncology. So is there maybe something where we need to reverse the CHIP process, and in what circumstances? And what are the options?
Yeah, so that's a great question. So if you're thinking about therapeutics for CHIP, you can think about intervening in two ways. So one is to try to suppress the mutant clone at the stem cell level. And the second would be to deal with the downstream consequences, such as the enhanced inflammation. To date, there is no drug that would be safe to give to people in CHIP that we know of to suppress the mutant clone, but I think this is an active area of investigation. Now, are there ways that you can do that very safely? Because you'd have to have a very safe profile to treat people who do not have an active malignancy. The second pathway might be a little bit more feasible in the short term. So, for example, Novartis did a reanalysis of the CANTOS trial, which I'm sure many of you are familiar with, where they asked if people had hematopoiesis, did they derive greater benefit from canakinumab? In this post-hoc analysis, individuals with TET2 mutations did seem to derive a greater benefit. And so you could imagine that there may be a prospective trial done in the near future using anti-IL-1 beta or NLRP3 small molecule inhibitors in the CHIP population. So that would be a way forward.
Said amazing talk as always. One thing is, we know that CHIP is common among cancer patients and survivors, and it has been associated with adverse health outcomes. But CHIP is not a static process; it's dynamic. It evolves, and it can become more. It can become bigger size clones. So, what do you think is a good strategy if you were to include this in our risk prediction model? How often do you think that we should sequence it? I guess every 5 years, every reasonable time, or just trying to figure out what are the good strategies to incorporate in our clinical process where the CHIP itself is a dynamic process.
Yeah, that's a great question. And I think one that we're still trying to figure out. And so, these patients do come to hematology with eggs, and often if they have a normal blood count and a mutation, they're going to be followed more closely. And certainly the CBC, the complete blood count, would be taken more regularly in that phase. But it's an open question of how often would we reassess their molecular profile. What I can tell you is that in general, the clones grow relatively slowly. So, I use this term variant allele fraction, which is a measure of the size of the clone based on the proportion you do reads in the DNA. And that would, double maybe every 10 years for most of these mutations. So that would suggest that something like yearly monitoring may be too much. But the case may be different for high-risk mutations. So for example, if somebody comes in with a TP53 mutation, which probably has a relatively high risk of transformation to a malignancy, that would be a more frequent monitoring. So to answer your question, I don't know how often this should be reassessed, but I would probably suggest not too frequently, like every year, maybe every few years.
Thank you.
Thank you for your presentation. Since you showed some studies also looking at the risk of heart failure, is that independent of the risk of coronary disease? Is there an increased risk of non-ischemic heart failure? And is that confounded by those who develop pathologic malignancies that may require doxorubicin-containing regimens? And the second aspect of this question, from the cardiology point of view, are those at least here with the common mutations included in the panels that will routinely screen, particularly for non-ischemic cardiomyopathies, or should we, and what clues should we get? We look at specific aspects of the differential in the CBC, since these people by default don't have an established immunologic malignancy by the time they develop the mutation.
Right. So great question. So your first question, I think, was what kind of heart failure is associated with increased risk in patients with CHIP? I believe it was both preserved and reduced ejection fraction heart failure, but I'd have to go back to those studies to see. If I'm recalling correctly, preserved ejection fraction heart failure had a higher hazard ratio associated with it. And I believe that this risk was also independent of underlying atherosclerotic disease, if I'm recalling correctly. And I think your second question is what blood count parameters should we be looking at in these patients? Is that right? So in general, CHIP would be subtly associated with changes in blood count parameters. So for the most part, people with CHIP have more or less normal blood counts. If they did have some abnormality of their blood counts, that would trigger hematology consults and more frequent monitoring for potential myelodysplastic syndrome. The one blood parameter that does seem to be particularly interesting and perhaps prognostic is increased red cell distribution width, RDW. For whatever reason, if people have a CHIP with a high RDW, that seems to indicate increased risk of both blood cancer development as well as all-cause mortality, eventually cardiovascular disease. So RDW might be something.
Got it. Well, that's what we usually don't look at in repeat cardiology.
Yeah, you probably know.
It's really very exciting and provocative data. Thank you very much. So you think it's ready for prime time as a biomarker?
I think we still need prospective randomized trial showed that some agent, I mentioned a couple possibilities, Q&A would provide benefits for patients with CHIP. Again, the idea would be that CHIP is a biomarker for a patient population with an enhanced inflammatory risk profile, and therefore blocking that inflammation. And what data, IL-6 or an LRP3 or something like that, would that work in that population? I think that trial is.
Thank you very much.
Good morning, everyone. And we start the session. So could you please sit and we'll get started. So I'm very thrilled to introduce this session. My name is Petrow. I'm a cardiologist and cardio-oncologist in Genoa, Italy. And I'm also currently secretary of the Council of Cardio-Oncology of the ESC. And I will co-chair in June this session about the coexistence of cancer and cardiovascular disease. The first speaker is Professor Suma Konety. Doesn't need so much introduction. She's professor of cardiology at the University of Minnesota and director of the CardioOncology program. And she will start the session. Please, so good.
Thank you very much for the kind introduction. And the title of my talk is Cancer and Cardiovascular Disease. And I hope to provide a broad overview from the lens of a clinician. Over the course of this meeting already, we have heard quite a bit about this buzzword of cancer and heart disease being bidirectional in risk. I have no relevant faculty disclosures. The objectives of my talk today is, one, to recognize that there are shared risk factors for heart disease and cancer, and recognize that patients with cancer are at increased risk of heart disease, that we're quite familiar with that paradigm, and review some epidemiological data on patients with CVD and incidental cancer risk. And I'll kind of let you guys be the judge on how valid the data is. And lastly, to understand the shared mechanisms underlying the bidirectional relationship of heart disease and cancer. And why is it important to study heart disease and cancer? Obvious that heart disease and cancer are the leading cause of death in both men and women. So this would have a tremendous global health impact if we reduce our rates. We've also seen some of these, this slide put up previously, but essentially this is data from SEER registry, kind of denoting or pointing out to the fact that there is quite a bit of overlap of heart disease and cancer, and it's prevalent throughout the continuum of cancer. So the red heat maps denote heart disease from the very early stages of diagnosis all the way to much later ones after diagnosis. Our work and work of others really has explored the overlap of heart disease and cancer and the coexistence of modifiable cardiac risk factors. So here listed are some of the estimated cancer risks for some of the well-known or modifiable cardiovascular risk factors. I don't know how well the graph projects, but as you can see, tobacco, hypertension, diabetes, physical inactivity, obesity, etc., are also associated with elevated estimated risk of cancer. So essentially, previously, these clinical factors were thought to be discrete and associated either with cancer or heart disease, and now there's growing appreciation for common modifiable risk factors in heart disease and cancer, suggesting that these diseases have shared biological mechanisms. We're all kind of familiar with this paradigm of cardiovascular effects of chemotherapy and radiation therapy, and we're aware that tyrosine kinase inhibition, HER2, anthracyclines, proteasome inhibitors, alkylating agents, platinums, all of these can create cardiac perturbations either through cardiomyopathy, hypertension, atherosclerotic heart disease, etc. And we're also all too familiar with radiation-induced heart disease, a higher risk of death and major coronary events treated in women treated with radiation. Higher the risk, higher the radiation dose and increased cardiovascular risk, higher the risk of heart disease and death. From there we've also begun to recognize that cardiomyopathy can exist in cancer patients pre-chemotherapy or pre-radiation therapy. And this is an example of a 57-year-old gentleman who I recently saw in my clinic with pretty bad squamous cell carcinoma of the lip, who has a 55-year history of small gaining, BMI pretty low, had cancer cachexia, if you will, pre-chemo, echocardiogram showed severe organ dysfunction, as you can see, sort of globally down, as highlighted by the echocardiogram here, using LV contrast. And angiogram below really didn't show any significant heart disease to explain this degree of cardiomyopathy, but nonetheless, there was some mid-RCA lesion that was studied. And we could actually spend a lot of time just talking about the care of this patient itself, but in the essence of time, I'll continue to move on. So essentially, this is highlighting that the existence or the prevalence of cardiomyopathy in patients due to cancer itself is another entity that we're starting to realize. I'll review now some of the epidemiological data supporting the increased risk of cancer in patients with heart disease. And again, what this really underscores is the importance of cancer surveillance in this population. So I have a few slides here sort of driving this point. Here is from the early reports of this community-based case control study showing an elevated risk of a higher risk of cancer in patients with heart failure compared to controls with a hazard ratio of 1.68, even after adjustment for cancer-associated comorbidities, and also portending a higher risk of death with a hazard ratio of 1.6. This has been replicated by many other studies. Here's another study looking at MI patients who developed heart failure down the road or a year and a half later, and they're noted to have an increased risk of cancer. A data study again confirmed these findings. The hazard ratio reported of 1.24 for incident cancer in heart failure patients. These studies, when you kind of look through them carefully, there are certain confounders that may have not been sort of adjusted, and in particular for this study, tobacco use was not available and was not adjusted, but nonetheless, there's a pretty strong signal. But the data is mixed, and there's lack of association of heart failure and incident cancer in the physician's health study. This is predominantly healthy male cohort who provided information about cancer and heart failure via questionnaires. While the Women's Health Initiative study didn't show a higher risk of cancer, and the association was strongest for lung cancer and colorectal cancer, and pronounced for the heart failure with preserved ejection fraction group, but no association with breast cancer. And one more study here looking more recently of a population-based cohort, 27 million, using the IBM market scan claims data, showing that the association was most pronounced, or the association of higher risk of incident cancer being most pronounced for atherosclerotic cardiovascular disease. Now, as biological sort of mechanisms continue to be elucidated, it's imperative that the progressive risk factor modification be continued for secondary CVD prevention and potentially for the primary cancer prevention as well. Now, shared mechanisms underlying both CVD and cancer include any number of these mechanisms outlined here in this slide, which includes chronic inflammation, oxidative stress, metabolic dysregulation, CHIP, we just heard at the very elegant talk about that, microbial dysbiosis, some hormonal effects, and even cell senescence. So from this, I think targeting chronic inflammation would be a very effective therapeutic, or could be an effective therapeutic strategy to mitigate atherosclerotic disease. Now, preclinical studies have identified several mechanisms that may underlie the stimulatory effects of acute Lyme, heart failure, aortic constriction, and preclinical data inducing tumor growth. Now, these include cardiac release of nerve growth factors, periostin, serpin, etc., that are listed here. This hasn't quite translated to clinical data yet. So I think in a sense, I am providing this additional data. I hope I can convince you that there may really be a bidirectional risk between heart disease and cancer. We're aware that among cancer survivors, CVD is the leading cause of non-cancer related mortality. Now, we also know from Eric's study that individuals who maintain good CV health have a lower risk of incident cancer. We've heard of Cadmus trial being many times reported during this summit or alluded to in many of our talks, and that blocking IL-1 beta could lower recurrent CV events and even lung cancer incidence in a sub-study of the Cadmus trial. And a point I want to make is, and this is for Petrow, is mortality, cancer mortality is reported only in about 25% of our cardiology randomized clinical trials, but yet they can account for about 6 to 14% of all that. So it's important, but we don't have our cardiology clinical trials are not designed to look at incident cancer as one of the endpoints, but hopefully that will become at least a secondary endpoint. So in conclusion, I would say that CVD and cancer appear to have a bidirectional risk with shared mechanisms and risk factors. Patients with cancer are at an increased risk for CVD as a direct effect of cancer or from cancer therapeutics. And now epidemiological data which are provided suggests that patients with CVD are at increased risk for cancer. And there are shared pathways, including oxidative stress, neurohormonal activation, and chronic inflammation that may explain some of this bidirectional risk. And from a global health perspective, I think aggressive risk factor modification for CVD prevention could potentially prevent incident cancer. So, sorry, I went over by a few minutes, maybe a minute, but thank you for your time.
Thank you so much. So we'll have the discussion at the end of the session. So I'm calling the next speaker, who's Dr. Jennifer Liu, Chief of Cardiology at Memorial Sloan Kettering, and she will talk about the current status and perspectives of early detection of Cardiovascular. Please.
Thank you. First, I'd like to thank Suma and Anne for the invitation to participate in this program. It's a real honor and privilege. So here, disclosures. So as we all know, 2D transthoracic echo is the most widely used tool for assessing cardiac function, and that includes patients undergoing chemotherapy. LVEF, an index of LV systolic function, is the primary parameter most commonly monitored for detection of cancer therapy-related cardiac dysfunction, or CTR-CD. Now, similar to the general population, the prognostic value of EF during chemotherapy has been well established. The study on the left showed that among patients with breast cancer undergoing anthracycline plus trastuzumab, a baseline lower EF or a decline in EF during treatment, as small as a 5% absolute change, was associated with increased risk of trastuzumab-related cardiotoxicity. And the study on the right, led by Anthony Farmer Group, showed that an EF less than 55% at any surveillance time point was associated with increased risk of clinical heart failure. Now, I think it's also well recognized that 2D EF is not enough on its own. And this is partly due to the study by Dr. Davendra and Nathan, showing that the reproducibility of 2D EF is such that the minimal detectable difference in serial studies is 10% among patients undergoing chemotherapy, which is problematic as 10% decline or greater is often noted as a sign of cardiotoxicity. And it's important to remember that the accuracy of 2D EF is very much dependent on the image quality, assumptions about LV geometry, expertise, as well as limiting conditions. And the seminal work from Dr. Cardinelli's group showed that even with rigorous monitoring, initiating ACE inhibitor when EF decline is detected is only associated with 11% of total EF improvement. And patients with partial or no recovery had higher incidence of adverse cardiac events. So the take-home points from the study is that EF decline is a late phenomenon and more sensitive indices are needed for monitoring. Now, the strain has become commonly used for assessing myocardial function. So strain is a dimensionless parameter representing deformation of an object relative to its original length in response to applied force. In the myocardium, strain measures its length in diastole and systole, serves as a measure of contractility. Strain is negative when the fiber is shortening and positive when it's thickening or lengthening. Strain on 2D echo was based on spectral tracking on standard grayscale images. Global longitudinal strain, or GLS, is the clinical standard for deformation analysis and most commonly used for research or clinical practice. It is an index of longitudinal myocardial shortening, a measure for subendocardial function that can be obtained on standard apical views on routine 2D echo, as shown in these videos. Now, GLS has emerged as a valuable tool in cardio-oncology as it is a sensitive parameter for assessing myocardial function and for detecting subclinical LV dysfunction. It has been shown to be more reproducible than 2D EF, at better correlation with MRI EF, and prediction of overall outcome. And there have been many studies showing the utility of GLS as an early marker of cardiotoxicity, nicely summarized by meta-analysis by Dr. Davendra and Nathan, showing that a decline in GLS was predicted of CTRZD. Now, the prognostic value of GLS prior to treatment has been nicely shown by work from Dr. Mary Shell Crosby. In this baseline risk score for predicting heart failure in patients with acute leukemia treated with doxorubicin, GLS was strongly associated with heart failure risk and independently associated with all-cause mortality, while cardiovascular disease and EF less than 50% were not, and that's after adjusting for age and leukemia type. And moving beyond CTRCD, Dr. Neal and his group showed that GLS decreased with the development of ICI-related myocarditis, even among patients with normal EF, and that the decrease was associated with subsequent major adverse cardiac events in patients with both normal and reduced ejection fraction. And as shown in his previous work, EF is a poor predictive outcome in this condition. It's important to remember, however, that GLS reduction is not reliable as a diagnostic marker, as it can occur during ICI therapy without myocarditis due to infiltration of T cells into the myocardium. And the work from Dr. Key's group provided evidence that 3D staining can detect cardiotoxicity earlier than 2D strain. 3D strain measurements are inherently better for analyzing the complex mind-fiber architecture and LV mechanics. However, at the current time, it still remains primarily a research tool due to practical limitations. And then, of course, the question is, hamstring guide cardioprotection to lessen the change in EF during cardiotoxic therapy was addressed in the support trial, a randomized trial of patients with breast cancer receiving anthracycline and trastuzumab primarily. So patients were randomized to a GLS-guided versus a EF-guided cardioprotection. And the primary endpoint was a change in EF from baseline to 3 years. And I think many of you know the results show no difference between the two groups, and that the final three-year EF was also similar. However, if you look at the data from that support trial, that the final EF was lower in the EF treated group than the GLS treated group, suggesting that the GLS approach may be beneficial in a higher risk population. But nevertheless, the conclusion of the study was that a GLS guided cardioprotection was not superior to EF-guided approach when applied broadly across a low to moderate risk population. And of course, we know that the story didn't end there, as Dr. Warwick and the investigators then conducted the SECORE MRI trial, which was recently published in the European Heart Journal. And the question asked this time is that, is there a benefit of cardioprotection in patients with isolated GLS decline but no change in EF during echo surveillance for anthracycline treatment? So patients who had isolated 12% decline in GLS was randomized to cardioprotection versus usual care. And the primary endpoint was similar to the initial SECORE trial, which was a change in EF from baseline to 12 months. And this study did meet its primary endpoint, and that is that the treated group, the cardioprotective treated group, showed a less EF decline than the usual care. And the EF at 12 months was also higher in the treated group than usual care. And the EF CPR-CD had a lower incidence in the treated group than in the usual care, though that did not reach statistical significance. So the conclusion of the study was that cardioprotection for isolated GLS change is associated with less EF decline during anthracycline treatment among high-risk patients, and the findings to support the use of GLS in surveillance for CPR-CD. Now moving to circulating biomarkers, namely troponin and BNP, which are well-established markers for the diagnosis of cardiovascular disease and determining prognosis. So this meta-analysis aimed to determine whether troponins and BNP predict cancer therapy-related LV dysfunction. And the meta-analysis revealed that troponin and BNP increased during cancer therapy, and the troponin elevation was associated with LV dysfunction, though BNP was not. Now, early work by Dr. Konety showed that there was an increase in troponin soon after high-dose chemotherapy, which predicted LV dysfunction. So when patients with elevated troponin were randomized to enalapril versus no treatment, significant EF reduction was seen only in the control group, and that early cardioprotection prevented the development of cardiotoxicity, and the study concluded that troponin was an effective tool for risk stratification and guiding cardioprotection to prevent cardiotoxicity in patients receiving high-dose chemotherapy. Now, the CardioGear trial, more recently, tested the same hypothesis, but using a high-sensitivity troponin. So patients receiving anthracycline that had a high-sensitivity troponin level greater than 5 nanogram per liter was randomized to neurohormonal blockade or usual care. And the primary outcome, adjusted change in EF from baseline to 6 months, was minimal and quite similar between the two groups. So the study concluded that among patients undergoing anthracycline treatment with elevated troponin, the cardioprotection with neurohormonal blockade had minimal impact on EF treatment. And some of the reasons for the varying results across studies include, for example, differences in the study populations. Dr. Konety's study included patients receiving high-dose chemotherapy and randomized to a higher troponin threshold cutoff than the cardiac care study. In addition, we need to recognize the limitations of biomarkers, including the typical variability in troponin and PMP, and capturing the troponin signals at different time points, as well as the specificity of biomarker signal, such as in cases involving changes in volume status or the presence of other cardiac conditions. So in the ESC guideline, patients who have preserved at least EF but a drop in GLS of greater than 15 points or no rise in biomarkers are considered to have mild CT/CD, and treatment with neurohormonal blockade is considered as a 2A, 2B indication during anthracycline treatment, though the guidelines was drafted before the release of the more recent trials that I just mentioned. So in summary, we know from the SUPPORT and MARA-I trial that a decline in GLS is prognostic and helps guide cardioprotection, which could lead to a modest reduction in EF during CGRCD surveillance in the virus patients. Troponin and PMP are markers of myocardial injury. However, its optimal use in cardio-oncology remains to be further investigated. And for identification of cardiotoxicity, Dr. Key has already elegantly detailed this morning that we need to better define which populations the imaging and the circulating biomarkers should use to screen, and what thresholds should be used to initiate treatment, and then also what agents should be used for cardioprotection. I think these are the key questions that still need to be further addressed. And then finally, we need to explore novel approaches to identify patients at risk, align screening with risk levels, and incorporate functional metrics beyond the added and cyclical predictors in order to identify effective tools to evaluate heart failure risk. Thank you.
Our next speaker is Dr. R.T. Asnani, assistant professor at Harvard and also section head of cardio-oncology at Beth Medical Center. Dr. Asnani will talk about how we can leverage genomics and precision medicine for early detection of cardiotoxicity.
Thank you very much to the organizers, Dr. Konety, Blaes, Dr. Reed, Dr. Baring, and the invitation to speak on this panel. These are my disclosures, none of which are directly relevant to the content of this talk. And so I think, as Dr. Liu has very nicely pointed out in the previous talk, as a cardio-oncology community, we often struggle to identify patients that have an early cardiotoxicity that very importantly is clinically relevant. So that would be cardiac toxicity that will translate to heart failure events and potentially interaction with cancer treatment. I'm sure many of us in the room have taken care of patients who have no clinical risk factors, yet develop severe cardiotoxicity, suggesting that heritable factors likely contribute to cardiotoxicity risk. These heritable factors can be interrogated along any point in the central dogma shown here, including genetic variants, as well as changes in RNA levels, protein levels, and metabolite levels. Oftentimes, we think of proteins and metabolites as distal mediators of heritable risk. However, currently, you can assess the heritability of individual proteins and metabolites from population-based genome-wide association studies. And so we'll start with genomics. Most of the prior work has been done in the context of anthracyclines. We heard about several mechanisms of anthracycline cardiotoxicity that were described in the research symposium yesterday. And Dr. Yeri Kim in particular touched on a number of genetic variants that represent molecular pathways in anthracycline cardiomyopathy, including tightly truncating variants, which is work that she has led, as well as several variants described by Dr. Smita Bhatia, together this very elegant figure. Notably, most of these genetic variants represent known pathways of cardiotoxicity, including oxidative stress, cardiac structural proteins, topoisomerase 2 beta, drug transport genes, and as Dr. Nahali noted yesterday, iron homeostasis, particularly in the mitochondria. To date, we have been limited in our ability to do discovery genetics by small cohort sizes. So most of the cohorts that were used for these studies ranging from 50 patients to the maximum of 300 patients. It's been very difficult to do discovery work in that setting. So now we move on to transcriptomics, where we've really had an explosion of new technologies within the past decade. Given all these new technologies, I wanted to start by sharing with you definitions. So bulk RNA sequencing measures transcripts across all cells and in tissue. So when we're thinking of the heart, for instance, there's cardiomyocytes, fibroblasts, endothelial cells, and immune cells. Development of single-cell RNA sequencing techniques has allowed us to now measure transcripts in a single cell. And specifically, technologies such as FACC, or cellular indexing of stranded transcriptomes and epitopes by sequencing, allows us to be even more specific about single-cell identification by integrating single-cell transcripts with antibody-based cell surface protein analysis. These antibodies are typically conjugated structamen. Next, we have single nucleus RNA sequencing because it allows us to measure transcripts in isolated nuclei. This is particularly important for this community because it's preferable for assessing cardiomyocytes. Cardiomyocytes are relatively large at cell types, and so they are difficult to capture by traditional single-cell RNA sequencing technologies. And then finally, we have more recently spatial transcriptomics, which shows us the positional location of RNA expression in an intact tissue by cell-to-cell pattern. And so we saw some beautiful examples of the application of these technologies yesterday in a research symposium. For instance, Dr. Axelrod showed us how T-cell receptor sequencing can be used to identify clonal T-cell populations that target a specific antigen, for instance, alpha-myosin. And this is work that was performed in a mouse model of immune checkpoint inhibitor myocarditis. Similarly, Dr. Jaiswal showed us an application of cytometry of time flight, or CyTOF, which is a technology that detects cell surface and intracellular proteins using antibodies conjugated to metal isotopes. This gives us increased specificity. Dr. Su was able to apply this technique to identify a specific CD8-positive T-cell population that was induced in patients who received immune checkpoint inhibitors who specifically developed myocarditis. So I'll now move on to proteomics, and I'll show work from our laboratory. This was work that we published in collaboration with Dr. Mariel Scherer-Crosby. Dr. Crosby previously enrolled this patient cohort, which included women treated for breast cancer with anthracyclines and HER2-targeted treatment as shown here. This was a very well-phenotyped cohort. Patients had serial questionnaires, blood sampling, as well as echocardiography. And in using blood samples from this cohort, we performed aptamer-based profiling of proteins using the Suma scan platform. Aptamers are modified nucleotides that bind to a specific protein with a slow off rate. This increases their specificity, and the current version of the platform provides relative quantification of up to 11,000 proteins. And this can be performed in a very small volume of plasma, less than 100 microliters. And so this was work that was led by Dr. Jing Liu, very talented postdoctoral fellow in our laboratory, who showed that in this initial discovery cohort using SomaScan, the change in a protein called hemopexin, a circulating heme-binding protein, was strongly associated with the change in global longitudinal strain in these patients. So another way to put it is that in patients who had early cardiotoxicity noted by change in global longitudinal strain, they had an induction of hemopexin levels in the blood. So we found this to be very interesting because hemopexin binds on heme with great affinity. And heme is cytotoxic, it can cause oxidative stress. And so hemopexin serves as a way to sop up this excess heme, bring it into the cell for lysosomal degradation. So given the interest in this finding in anthracycline cardiomyopathy, we repeated this analysis in a validation cohort. We saw similar findings. Summarizing many years of work by Dr. Liu, we found that hemopexin knocked out mice had increased cardiotoxicity, and treatment with hemopexin preventing the cardiotoxicity. This strongly suggests that hemopexin is induced as a compensatory and cardioprotective mechanism. And she has shown that this is really carried by CD64 positive monocytes and macrophages to provide this protective role. I'll show another example in the published literature of how proteomics has been applied to carfilzomib cardiotoxicity. Many in the room will be familiar with carfilzomib. It's a proteasome inhibitor that is associated with cardiovascular events, cardiomyopathy. And for this study, the investigators used an only antibody-based platform. This proteomics technology is thought to be slightly more specific, perhaps, than the aptamer-based technologies because it involves binding of two antibodies to a specific antigen. Binding of these two antibodies, each has a oligomer, a piece of DNA that then binds to each other. This creates a DNA barcode that then can be amplified by PCR and can be read out by next generation sequence. And in this example, unfortunately, they were underpowered to detect statistically significant changes in proteins, but it does serve as a proof of concept that we can start applying these technologies to newer cancer therapies that cause cardiovascular toxicity. Now, I'll end with an example from metabolomics. This is where it again was performed with Dr. Mariel Scherer-Crosby. This was using the same breast cancer cohort that Dr. Scherer-Crosby had enrolled. And for this study, we designed patients as either having cardiotoxicity or not having cardiotoxicity, using a definition based on the LV injection fraction from ECHO that was very similar to what's published currently in the ESC guidelines. And so those patients in yellow did not develop cardiac toxicity. They were protected. Patients in red had a decline in injection fraction. And what we found is that patients who were protected from cardiac toxicity had augmentation of TCA cycle metabolites, citric acid, as well as aconitic acid, whereas those who had cardiotoxicity were unable to mount this response. Now, one challenge with doing metabolite profiling is that metabolites can be modulated by the diet. These patients were fasting. So it's been hard to find replication cohorts where we have patients who are similarly fasted when we do these analyses. So that brings us to limitations of the current approaches, certainly availability of well-feeded time to validation cohorts. This includes, as was mentioned previously, cancer therapy, phenotyping, dose, timing, as well as phenotyping cardiovascular events, and having standardized cardiac imaging or biomarker analysis. Functional validation can certainly be challenging. This came up yesterday in the research symposium. So tissue is the issue. For our cancer biologists in the audience, you can take a tumor sample and biopsy it and get a very elegant profile of the molecular biology. For cardiovascular biologists, it's much more complicated. We certainly can't put our patients through an endomyocardial biopsy every time we see them. So as Dr. Carver showed yesterday, human-induced pluripotent stem cells differentiated into cardiomyocytes can serve as one model for functional validation and to try to start to understand mechanisms based on what is in human genetic variation. So I'll conclude that precision medicine technologies hold great potential for the early detection of cardiotoxicity. I think this is where we're at right now, where we have these amazing discovery technologies that we're starting to apply to cardio-oncology, which is a very exciting time. It will be a bit of a steep slope to integrate these into clinical practice, but I have no doubt working together on the clinical and molecular sides that we will be able to do so. So I'll end by acknowledging my lab. Were a lot of fun. It's shown here. Our many collaborators, Dr. Scherer-Crosby, who participated in a lot of work that and really led a lot of the work that I showed here. Dr. Bechet-Zornogi, Dr. Julia Guerra, who I believe is here, and Fermento Alexandra Guido, as well as Robert Gerson, who's been a mentor of Omics Technologies of mine for nearly 20 years. I wanted to note that we will have an upcoming AHA scientific statement that has been put forth by the Cardio-Oncology Committee. This is going to focus on precision medicine and cardio-oncology, and it will summarize many of the concepts that I've shown here today. Thank you very much.
Our final speaker is Dr. Ariane Machado, who is a professor of medicine at Sao Paulo, and she's also chair of Cardio-Oncology Clinic. She'll talk about cardioprotective therapies for cancer patients. Thank you. Ladies and gentlemen, it's a pleasure to be here in this 100% female panel. So I'm truly honored to be here. Thank you. So my talk today is about the cardioprevention therapies in adult patients with cancer. These are my disclosures. And well, we know that cardiovascular disease and cancer account for more than 40% of disease-related deaths globally. And there is a bidirectional mechanism for relationship between cancer and cardiovascular disease. And cardiovascular side effects of the cancer treatment plays a role in this direction. Cancer is not to induce some modifications in the homeostasis of the cardiovascular system that can also increase the incidence of cardiovascular disease. And then one point that I would like to highlight here, since my previous speakers has already set the stage about biomarkers, shared risk factors, and also precision medicine, and that more recently we have studied a lot how to explore this markedly different that has among risk stratification. During most of since the beginning of the CardioOncology, we have focused on the drug, but probably we need to focus not only on the drug that we give, but also the disease that the patient has. So maybe cancer type may be a critical role, a process in consideration of this risk assessment process. Let's see something. This is a database from the United Kingdom that they measure the 1 year, after 1 year of the cancer diagnosis, the incidence of a lot of cardiovascular outcomes regarding the tumor type. And in the first slide, we can see a huge difference in the incidence of heart failure in myeloma patients. And look at the beginning of this graphic. Breast cancer incidence comparing with myeloma incidence of heart failure. Why we are looking so much for breast cancer? We are losing the chance to treat patients that would be benefit more. I'm talking about cardiotransplantation. Everybody interested, it's important, but look at this data, maybe we're missing something. And then we look for other outcomes like stroke, pericarditis, vascular heart disease. There is a huge difference in the incidence of these cardiovascular outcomes, and they are not only related to the drug that we give. So not only the tumor type makes difference, but also the burden that the patient has during the cancer treatment. At the beginning of the cancer diagnosis, since then, these patients die more for cardiovascular disease, but there are some differences. For example, for patients with endometrial cancer, after 1 year of the diagnosis, maybe in the first year, the chance of this woman to die from cardiovascular disease is overpass the chance to die from endometrial cancer. So after some years, this overlap of cancer and cardiovascular mortality, there are some differences among the main cancer types, but at the end, cardiovascular disease differs among this kind of cancer. More recent data is analyzing the risk profiles and incidence of cardiovascular events across different kinds of types of cancer, but also adjusting for risk factors for cardiovascular disease. So maybe these patients can have different risk factors due to disease, but let's look at this data. A very recent publication that we can see the cardiovascular risk factors for more than 800,000 patients in this database, US database. They showed that the cardiovascular risk factors among these various types of cancer, hypertension and dyslipidemia were the most frequent, and the baseline prevalence of risk factors were lowest in patients with breast cancer and melanoma, and highest in kidney, prostate, lung cancer, and also myeloma. And after some years of the diagnosis, this incidence of cardiovascular disease is increasing and sometimes overpass for many years again the cancer risk. So cancer type may also bring critical consideration the risk assessment process, getting understanding, and I feel that it's our mission. It's understand what characteristics each patient has and how this is associated with cardiovascular disease. So let's begin a new era of cardioprotection. We need to move on. We need to move on from looking into anthracyclines, breast cancer, and have another look and commit to research the multiple parameters between cancer and cardiovascular disease and the impact of cancer biology and cancer therapies on the cardiovascular research. Of course, we need to keep the work that has been done so far. It's very important to follow the instructions and the guidelines, they making the risk stratification. After that, decide what kind of strategy we are going to use, what kind of drug, and we have good results for this strategy, but maybe it's not enough. We have selected cardiotoxicities that we can focus on and try to have a potential protective strategies, anthracyclines, trastuzumab. We decide and look into what is the main cardiovascular profile of toxicity. We needed to do the control the risk factors. After that, decide what kind of cancer treatment adjustment that we will need and decide what kind of drug, the cancer therapies that for anthracyclines, we have much more data about that. It's important. It's a very relevant drug for very relevant tumors. And whether we can try to reduce the risk of cardiotoxicity, try not to use anthracyclines, the most effective way to prevent, not use. But sometimes the oncologists don't have this option. So we need to move on. We can try to reduce the anthracycline dose since the cardiovascular toxicity is depending of the dose, and that this dose is accumulated over years and even for different types of treatment. We can reduce the infusion rate for bolus injection or a slow infusion. We can use liposomal doxorubicin, that is a special formulation that is no limit of dose for cardiotoxicity, but also we can use for replace the doxorubicin by itself. And we have pharmacological drugs that we can use for many years, and we still go on trying to use the neurohormonal blockade to reduce the risk of cardiotoxicity. Of course, the data is, we have a lot of trials. We have tried to do this in a meta-analysis, and more we see recently, this Bayesian network meta-analysis showed some interesting data. They put together more than 39 clinical trials, and they look into heart failure incidence, mortality, and ventricular ejection fraction as a primary endpoint. And the way that they put this together is very interesting because they try to use a very direct cardioprotective strategy. Everybody that needs some kind of cardioprotection will get it. So they test ACE inhibitors, beta blockers, statins, and also dexamethasone. And looking at the results of heart failure prevention, dexamethasone was the most effective therapy for cardioprotection, followed by some neurohormonal treatments. Looking into the ejection fraction prevention and protection, also we have some protective strategies, but not so important as the reduction in heart failure. For mortality, none of these studies would show some results since the trials were not designed to show mortality effectiveness in mortality. More recently, we keep on moving in this area, trying to identify more in a more precise way using biomarkers and also some echo parameters, how to identify who needs more for cardioprotection. The so-called MRI, right? A positive trial that showed that a strategy of treating patients with reduced with a strategy positive, it was effective and cardioprotection. However, Other recent trial, the PROTECT trial, then trying to use troponin as a result of cardiovascular protection, was not able to show the same result as a cardioprotective strategy. So in the area of neuropharmacology, we have very controversial data about who needs, maybe as a strategy. We have some good results, protects for heart failure incidents, but who needs these? We don't know yet. For starting, some new data has shown a protective effect in incidence of cardiotoxicity. This is a recent meta-analysis. We have the result of the STOP-CA trial in the Malignancies, and the more recent trial showing that the statins for patients who use anthracycline could be an effective strategy for cardiotoxicity. And the new kid on the block for cardioprotection is SGLT2 inhibitors, with a huge promise, not only for the cardioprotective effect, but also for the AIDS cancer effect. It seems like everything that SGLT2 does becomes positive as a factor, as a good outcome. So maybe we will see, and we'll see soon, a lot of trials are being designed to test how this can be applied in the cardiology, mainly for the protective point of view of cardiotoxicity. We will have soon some good results of the PRADA2 trials, the randomized controlled double-blind multi-center clinical trial, tested if sacubitril/valsartan would be an effective cardioprotection drug for patients under chemotherapy. But what's next? Maybe we're moving from the cardioprotection for the recyclings, but also try to protect the heart of our patients with ICE inhibitors. Well, about this cardioprotective effect. Some studies showing that atorvastatin should be a possible strategy, but also some more direct anti-inflammation drugs are being tested. These are presented in the last ISC Congress. I invite everyone to take a look. It's very, very interesting data. So my final message is that, well, we did new clinical trials designed to show us how to protect better than the heart of our patients. Not to allow a complete assessment, also from the cardiovascular, but also cancer outcomes, and how the cancer biology influence in our results, not only showing the drug, but showing the patient with the disease and taking the drugs. It's our mission. Thank you very much. Any questions? One question that I have, maybe for like there's 90 and that clear and the rest is first for proteomics. And I truly believe proteomics are, like the future as it's going to correlate. What do you prefer when you choose a proteomic platform, whether it's targeted versus non-targeted, but just that panel? The second question is, how do we efficiently, effectively translate these amazing genomics and precision medicine approaches in clinic so that we could really shorten the time from bench to clinic? Thank you, Chip. Those are some complex questions. So let's start by answering the first one around targeted versus non-targeted proteomics. Now that some of these platforms are able to measure up to 11,000 proteins, some of those afterwards are certainly more specific than others. And we have this beautiful correlated genetic and protein data from large population-based studies that help us with that effort. So for instance, if there's some protein quantitative trait locus or PQTL that can help us validate aftermer specificity, that can be very useful. So that allows us to be as targeted as possible. Untargeted approaches are sometimes necessary. They can be very time-consuming because then we're going back to the LCMS that, for instance, I had done when I was a college student, and it would take about 2 months to identify the target for one protein.
But certainly there are applications for that. And many times if we're trying to validate something from a high throughput proteomics analysis, we won't do that. The question about translating, I'm happy to have other thoughts because I think it is challenging.
Right. Questions? I think that we can have them. Just short questions, really for rounders, and then that will close the session, please.
Coswara, Australia. Question about cardiac protection. How do you see the role of lifestyle interventions as a cardioprotective intervention? A great question. Thank you for that. I didn't include that in lifestyle in this area, but it's very important. And recently, we have a publication in the European Heart Journal showing a strategy of physical exercise. And after, during, or only after the finishing of cancer treatment, and the results measuring the capacity and exercise capacity, are amazing results, showing that only the patient that does not do exercise have no improvement in this capacity, and also perception of quality of life. That's for our patients very important. So definitely we have a role for exercise and also some kind of food that can also prevent some kind of damage in the heart. Thank you.
And my question probably leads us into the next session, but I'm curious from the panelists about how we continue to work with diverse patient populations. So even when we're looking at proteomics and we're looking at intervention studies, how do we make sure that our samples are representative of our populations? Very important.
I feel that is from the oncology point of view. We need oncologists with us because when you have the trials, maybe trying to put the surrogate endpoints about cardiotoxicity and also try to include the patient. I know it's not easy, but not so strict inclusion criteria for the patients. I feel that is, and we will move on if the oncologist takes our position as taking care of the heart of our patients.
Just that many of our blood-based biomarker and sampling platforms are really located at urban academic centers, and we're making a conscious effort to try to get to our community sites to enroll patients for biobanking. Should you want to help with that effort?
Well, thank you so much. We'll move on to the next session. Thank you so much for the panelists.
Hi, everyone. Thank you so much for being here. We'd like to end our congratulations to the organizers of this beautiful meeting. And thank you for teeing up for us. We are starting our new session, which I think will be most interesting to everyone. I am Dr. Nina Arnold from Lee Health, Southwest Florida in Fort Myers, and I was founder of the CardioOncology program there and established the Analyst and Transition Care. My co-chair, Dr. David Dasa, who was a medical oncologist and assistant professor here at the University of Minnesota. We have a wonderful session lined up for you, so we're going to get started right away.
Our next section is on disparities in cardio-oncology. We have 3 excellent talks with Q&A over at the end. So please save your questions until the end, then come on the mic. The 3 sessions include a talk by Dr. Tiffany Paul Whiteley from the National Institute of Health, Dr. Andreas Mayer from the Medical College of Wisconsin, and Dr. Ron Key, who we met earlier today from REPED. Dr. Paul Whiteley, the first talk will be from her, and she'll be outlining one framework of disparities.
Thank you so much to our co-chairs and to the meeting organizers for the opportunity to be here today. These are my disclosures. As we know, for cardiovascular disease, there are also clear racial and ethnic disparities for cardiovascular mortality for patients with cancer. We have data in the United States, specifically from the SEER registry, that showed us that when we look at cardiovascular mortality across racial ethnic groups, but also across age groups and locations of cancer, that those who are self-identified as non-Hispanic Black had a higher risk of cardiovascular mortality, but also all-cause mortality as compared to non-Hispanic white patients. We also know from these data that Hispanic and Asian populations had a lower likelihood of cardiovascular mortality. And these racial and ethnic differences in mortality are most pronounced among younger populations with cancer and those with localized cancer or without spread. And so these data suggest that particularly for younger populations, we need to better understand the mechanisms by which these racial and ethnic differences exist. And we also need to think about how do we account for some of those factors that might play a role in defining these racial and ethnic differences in mortality. We also have data to define that shows us some of the intersectional effects of both race and sex and how those relate to disparities, particularly cancer treatment-related cardiotoxicity. For instance, Black survivors of HER2-positive breast cancer have a higher risk of cardiotoxicity, particularly when we account for the confounders related to cardiotoxicity. And this leads and relates to a higher likelihood of treatment cessation for these populations. We also see that Black patients with breast cancer overall have a higher cardiovascular mortality risk as compared to white patients. And again, this is more seen in younger patients. Those, when I looked at women and men, comparing populations with Hodgkin's lymphoma, just as an example, we see differences by sex in outcomes related to cardiovascular events, where women have a higher likelihood of cardiovascular events as compared to men, again, suggesting that differences that contribute to racial, but also sex-related disparities may be playing a role in these differences in outcomes for cardiotoxicity and cardiovascular events. And so I would posit and provide other evidence to suggest that we can think of social determinants of health playing a key role in outcomes, not only in cardio-oncology, but in cardiovascular events for cardio-oncology patients. And really thinking about the factors related to where we live, work, play, and pray, and how those limit and worsen outcomes, particularly for those who are most impacted by adverse social conditions. And so I worked with colleagues in my lab, particularly Dr. Foster Osebon, who's a postdoc on my team, who's now faculty at Emory, and Sol Sharda, who's a medical student, who led our efforts with colleagues, especially from Nevers Hospital in Delaware, to write this review and highlight the relationships between social determinants of health and cardio-oncology outcomes. And so within this review, we first wanted to highlight a framework for how we can think of social determinants of health and how they relate to outcomes for patients with cancer and cardiovascular disease. And we built this on a framework that we have highlighted connecting social determinants to cardiovascular disease, where we focused initially on structural determinants of outcomes, whether they be social, political, economic, or environmental factors that limit access to resources and have effects on more intermediary determinants. which are factors related to the social needs within a community, whether it be financial needs, food insecurity or transportation, but also more individual level social determinants, psychosocial factors, things such as depression, but also experiences of discrimination and factors around perceptions of the environment in which they live. And we know that these structural and intermediate determinants influence social position, but also influence psychosocial and environmental stress that individuals experience that limit their health behaviors and ultimately have effects on their cardiovascular outcomes, particularly for patients with cancer. And so to highlight some of the data that we already have in how these socioeconomic and neighborhood factors relate to cardiovascular outcomes for patients with cancer, we know that neighborhood socioeconomic status measured particularly using census level data relates to excess mortality from cardiovascular events for those with cancer. That insurance status, particularly those who are uninsured or publicly insured, have a higher risk of cardiovascular events when diagnosed with cancer. And then the individual level is socioeconomic status, including poverty, but also education and geographic region also have a role in cardiovascular mortality patients who are cancer survivors in particular. And then more recent data has shown that financial toxicity related to economic resources, particularly for caring for healthcare, their healthcare status relates to cardiovascular outcomes for patients with a cancer history. And more recent data also connects neighborhood area deprivation as a marker of neighborhood level resources and how that relates to cardiovascular outcomes for cardio-oncology patients. And so these are just some of the studies that show these connections between social determinants and how they relate to cardiovascular outcomes. But we need to think about how do we bring many more of these measures into the studies that we are doing for patients with cardiovascular disease and cancer, and how do we look at more of the biologic connections that relate to social determinants and cardiovascular outcomes. We know from studies looking at population-based cohorts that social determinants can have a direct effect on the immune response, but also cardiovascular risk by activation of the neurohematopoietic axis, effects on sympathetic nervous system, as well as the HPA axis, and effects on glucocorticoid catecholamine signaling. And all of these relate to increases in cardiovascular risk, but also these stressors have indirect effects on health behaviors and therefore promote cardiovascular risk factors such as hyperlipidemia and hypertension, but also cancer risk. And so there are overlapping pathways, many of which were talked about in previous discussions, where the factors and the pathways that connect social determinants to cardiovascular disease are the same pathways that influence by which cancer therapeutics influence cardiovascular risk. These include pathways related to catecholamine signaling, as I mentioned, but also pathways related to MAP kinase and NF-kappa B activation, alterations in DNA and genomic factors in methylation, mitochondrial dysfunction, as well as clonal hematopoiesis, where we certainly need more data and how stress plays a role in the effects of and the risk for clonal hematopoiesis and inflammatory cytokines that have been connected in many studies to both social determinants of health, but also the risk for cancer, cardiotoxicity, cancer therapeutics. And so I would argue that in many ways to bring the patients who are most impacted by these disparities, who are most at risk for adverse cardio-oncology outcomes, we need to think about how do we engage these communities through community engagement using tools such as community-based participatory research, but also community-based approaches through healthcare systems. We can work to address adverse social determinants of health that not only influence cardiometabolic risk, but also cancer outcomes by building interventions that reflect on building trust with communities, building on assets that already exist within communities, and making sure that interventions that we're working on for cardio-oncology patients are accessible and available to all. And so these are just some ways to think about what these types of interventions might exist or might look like. They might exist at the individual level, where they mean to engage individuals through telemedicine, through technologies that make healthcare accessible, but there also may be community interventions that help improve resources within the community around social needs related to health, and policy level interventions, improving access to healthcare resources within a healthcare system that can help in improving outcomes, but also leveraging the voice of the community in the development of the intervention. And so when we think of research priorities, it really is about developing measures and metrics that will measure social determinants of health for the populations that we work with, incorporating those into EHRs to make sure that we understand the impact of these social factors in treatment for patients, but also identifying how we can address social needs as a part of the treatment process, building interdisciplinary teams to do this type of work, but also leveraging the cohorts, longitudinal cohorts, and intervention cohorts to incorporate markers of social determinants of health. And so in summary, I would posit again that social determinants of health have a clear impact on cardio-oncology outcomes. And we need more work, not only to incorporate these measures into the work that we do, but also to examine biological pathways that connect social determinants to cardio-oncology outcomes. And so this really is about an integrated approach, and not only in healthcare, in the healthcare system, but also in the research enterprise that we are part of. So I'd like to acknowledge my co-authors and those who, again, led this review, and I thank you for your time and attention.
We're very happy to be doctors. And now we'd like to invite Dr. Arrythmias to the stage from the College of Wisconsin.
Thank you very much for having me. I don't know very much about social determinants of health, but I think we married the population scientists, so this is how some of all this data can be. Okay, so I'm going to tell you a little bit about racial disparities in cardio-oncology. Now I'm going to work on vascular function. Hopefully some of you are familiar with the role of microcirculation and its dysfunction that's involved in different processes of organic events. And I'm not going to go over great details with this, but you can think of most diseases that the microcirculation is involved on some level. The physiological and clinical relevance why we study this is because it is an excellent predictor of future-based events. So this is data from a study in 2014, and there's by now several others that show very similar things. They looked at long-term health outcomes in patients with large all disabilities. As you can see on the graph here, cumulative MACE squares and the years of follow-up plotted here. The blue line here is patients that have normal large and normal small vessel function, and they have about a 20% risk of developing basal dystire. Interestingly, if you have patients with large vessel disease, but not small vessel disease, they're relatively fine compared to the control population. But if you're looking at patients who have normal arterial disease and impaired microvascular function in the heart, the number of MACE events jumps up significantly and a lot earlier. So this tells us microcirculation is important in the pathology to our development of adverse cardiovascular events. Well, what's the problem with this? Microvascular function tries to outcomes better than with artery disease, but there is very little known how microcirculation is affected in response to chemotherapy, let alone in human patient populations, or when the effect of race and social economic status is perceived. These studies do not really include healthy subjects. You cannot really treat healthy patients with chemotherapy in the sense of cath lab. Cancer patients in the cath lab is not something that is a primary idea either. So how can we try to understand it? So we at the Medical College of Wisconsin are very fortunate. David Gutterman, 25 years ago, has set up a wonderful resource to study the microcirculation in luminous scar tissue. We do this with both atrial and cardiac tissue as well as adipose tissue, and the matches are very nicely. So what we do, we ask our clinical colleagues when they cut off an atrial appendage or have left pieces of adipose tissue to give it to us. We can isolate microvessels from there, stick some on organ bath and study physiological responses to pharmacological agents, mechanical medicine, and others, and study mechanisms. Here's a summary data from papers that's currently under review that is, by knowledge, the first longitudinal study in breast cancer patients that looked at microvascular functions with a long-term follow-up. And what you can see here, in patients pre-chemotherapy, both responses to acetylcholine, Clonal boost dilation is relatively normal, but during and about 1 month after chemotherapy, microvascular function is severely impaired. And that translates to long-term problems. As you can see in the lower graph, the phenotype lasts for about 6 months, and it takes at least a year to go back to normal. Okay, so based on a lot of these findings, was mostly done in patients without any pre-existing cardiovascular disease. And we came up with a funding proposal that was eventually supported by the American Heart Association, and led to our ongoing study that is based on the discovery and validation of CardioOncology disparities for equity in the heartland. This is a wonderful work that my wife came up with. And here are the aims of my project of the Center grant. I'm not going to talk about APO because this is a quite clinical trial and there's not more for it. But I can tell you a little bit about what we're finding in Konety, where we're simply taking isolated vessels from mostly healthy individuals and comparing responses to previous chemotherapy and in cardiovascular function behavior. Write a little bit of a setting here. If we're taking vessels from otherwise healthy, non-Hispanic black and non-Hispanic white patients, there's virtually no difference in endothelial response to flow or acetylcholine, as well as response to Carver. This data that's been currently collected with our ongoing patient cohort, but we can go back with the last 20 years of data and essentially see the same thing. So what happens if we take these vessels and expose them to chemotherapy? Well, no surprise to anybody, doxorubicin is severely vascular toxic and essentially eliminates microvascular function response to flow. Acetylcholine shows the same meaning, with muscle media dilation as normal. So that's what it is. But what about more specific therapies that are targeting certain things, for example, anti-HER2 medications? What we find here is trastuzumab has a certain amount of cardiotoxicity in non-Hispanic white patients, but that is significantly augmented in non-Hispanic black patients. Interestingly, pertuzumab, which also targets HER2, but a different part of the is toxic in non-Hispanic white patients, but does not appear to have toxicity in non-Hispanic black patients. So that's sort of an interesting thing, and we're currently in the process of extending these studies to other biosimilars that are coming to market, looking at small molecule inhibitors, But the general idea here is, if this will be true, don't give Black patients chance to do that. They need some virtues in that. Relatively easy intervention, just, for the oncology also. Moving on, we were trying to be good scientists and use negative controls. The idea was microtubule inhibitors of brain-whole cardiotoxicity. And those were famous works. So we started looking at the effect of partially toxol. We found in white patients there's virtually no cardiovascular toxicity, but we're seeing a severe in middle systemic Black patients. In line with impaired with dilated function, we're seeing reduction in nitric oxide production and involvement and production of vital organ loss after exposure before the toxol. So that was very surprising to us. Digging around in the literature, in the cancer field, there's really nothing that supports this notion. The correlations are only, well, this is unreal. So we looked a little deeper. Interestingly, in patients who are receiving stents, drug-eluting stents, there is a well-documented racial disparities outcome. To my knowledge, no one has identified why that is. But a lot of these stents are not with them. If you base your large vessels in prostate, so the microcirculation gets into, and henceforth, MACE is hugs out and it really is right. So then when you went back, right at clinical relevance of this, we reviewed electronic health records from patients that are all in hospital. So this data is still preliminary. It is currently not just of the pre-existing conditions. There seems to be a little water spill out of my understanding, but I think the data shows a nice trend. So we looked at about 3,000 breast cancer patients who received different kinds of therapies, and we had a 10-year follow-up at least. And you can see the group A that received radiation or surgery only. There is about 90% incident of MSCE, but it goes up to about 30% of patients who received vaccines in the absence of cardiovascular therapy. And then in group C, patients who received cardiotoxic therapies and includes anthracyclines and or IPO2 therapy, the levels go up to about 40% and 46%. So what happens in patients that are not antibiotic plasma? The numbers are basically increased in all parts, to the most goes on with the data that my colleague just introduced in the previous talk. But what is stunning to me is that in group B, patients who receive only taxanes, the level of MACE is almost double, and it's the same level as you're seeing with anthracycline and beta therapy. So this would strongly suggest that taxanes are indeed more toxic from patients who are not privileged by our race. So again, can't really tell you all the much about completely too, because it's an intervention. I don't know which patient fits in what was the follow-up, but I can give you a brief snippet of the break-in on the last, which kind of goes in like with some of the studies here. So we have data in ex vivo measures with the microcirculation, and there are too little ends to interpret much. Here's some of the data on large vessel function, looking at breakout rate of emptying and pulse wave velocity, and you can pretty much see that there's not much difference. However, when we do the cardiopulmonary fitness testing these days, we see a pretty severe impairment in the non-Hispanic Black population. Those are breast cancer patients that are chemo naive, have been diagnosed with breast cancer of various types, but otherwise relatively healthy. BMI is not different, age is not different, but we've seen a reduction in neutrophils, we see a reduction in lax sweatage production, and it is about wattage adjusted for body weight, and similarly, average measures of cardiovascular fitness, we've seen a reduction in the cytostatic exercise and in an strength. Both of those are correlated with vaccine failure. If you're going to ask me in a few minutes, what we're seeing that is different in the patient populations, we can't really find all too much outside of sodium determinants of health, growth factors, everything that population side is checked all light up like a Christmas tree and is possibly driving. In summary, I showed you some data that endophilia is their function ex vivo and before exploring chemotherapy. is an indicator of events that may precede heart failure. The ex vivo exposure of clinical use antineoplastic therapies is a valuable tool to identify possible toxicities that contribute to long-term cardiovascular health. And as you all know, minority of species are very underrepresented in clinical trials, and this will be a very easy favorite into clinical trials and organ path and restats or C6. Interestingly, before exploring chemotherapy, large vessel epithelial function and arterial stimulus has no changes but cardiovascular fitness. In vivo setting, before malignant exposure to cardiovascular toxicity is impaired conditions. So we would like to say that microvascular function maybe is generic coli that precedes and protects future maze in cancer survivors. And with that, I'm sort of a time, like to know lots of people contributing to the work and well, which says or studying to you, and thank you very much for your advice.
Lunch on there. Up next, we have Dr. Konety, who will be discussing populations audience disparities.
Thanks so much, and thank you again for the opportunity to speak with you today about our work in Oncology disparities from a population science perspective. In terms of an outline, what I'd like to share with you today is first discuss the disparities in cardiovascular disease risk and how we can best mitigate that risk. Share with you some of our ongoing work at Penn, focused on prostate cancer and men receiving androgen deprivation therapy, and in breast cancer, women receiving anthracyclines, HER2, immune and radiation therapies. And then it's also respected in some thoughts on how I think we can best advance science and ensure our patients receive equitable, accessible care. So Tiffany very eloquently detailed to us the substantial disparities that our patients face. And particularly in prostate cancer, we know that there are disparities in terms of cancer outcomes. Black men are disproportionately affected and have higher all-cause mortality. Also, as it pertains to cardiovascular disease, we know that Black men have a greater prevalence and burden of cardiovascular risk factors that are poorly controlled, hypertension, obesity, diabetes, and dyslipidemia, and worse prognosis in terms of adverse cardiovascular outcomes. And then, of course, we know that there are significant disparities in the social health inequities that Black men with prostate cancer commonly experience worse social determinants. I would say, though, that in CardioOncology and at this intersection, there still needs to be a great deal of science generation, evidence generation. You heard Andreas so eloquently tell us about his ongoing work. And we've also been very interested in asking how disparities impact cancer and cardiovascular care, and then use this knowledge to help better inform how we can overcome disparities. We've taken various approaches in our work ongoing in my lab. First, we've taken and built detailed retrospective cohort studies. So here we've leveraged the Penn EMR system to look to define the impact of the social determinants of health on cardiovascular outcomes in cancer. Some of this work is part of an ongoing T24 grant where we're looking to also use NLP to extract social determinants of health on EMR. What I want to share with you today was some ongoing work and some completed work in our prostate cancer cohort, where we focus on various domains of influence as it pertains to social determinants of health that's set forth by the National Institute of Minority Health and Health Disparities, as well as levels of influence, similar to the work that Tiffany also shared with you. So what we've done at Penn is taken from our EMR, we've identified over 3,500 men with prostate cancer who are receiving androgen deprivation therapy. And from this population, we've extracted all the historical address data and then geocoded them using ArcGIS. And from these data, then identified social vulnerability index. We also extracted very detailed data on clinical measures, including cardiovascular risk factors, cancer outcomes, medications, and also matched these patients also to Social Security death index data. So we're actually also able to obtain specific cause of death. We performed stratified analysis to determine the risk of MACE, heart failure, cerebrovascular disease, and cardiovascular mortality in our Black men with prostate cancer treated with ADT compared to a white men. And what you can see in these cumulative incidence function curves was that Black men, as shown in purple, compared to white men, as shown in green, had significantly increased risk of MACE, heart failure, cerebrovascular disease, as well as cardiovascular mortality. And in an adjusted analysis, the risk of major adverse cardiovascular events was 1.93 folds greater and remained significant even after consideration of multiple confounders, also increased risk of heart failure, cerebrovascular disease as well. We also looked at social vulnerability index, and we found that Black men compared to white men had consistently worse social vulnerability overall and across individual domains as well, including socioeconomic status, housing composition, minority status and language, as well as housing and transportation. And then we sought to ask why. So why do Black men have an increased risk of MACE compared to white men? And here we use social vulnerability index as a causal mediator. So in causal mediation analysis, we determined that SVI, and in particular socioeconomic status, was responsible for 98% of the association between race and MACE. We've also undertaken prospective phenotyping and created longitudinal prospective cohorts ahead of our patients living with cancer, prostate cancer in particular, men receiving androgen deprivation therapy, and enrolled them in a longitudinal prospective cohort study where at baseline, prior to the initiation of an ADT, we performed very detailed characterization of the social terms of health using the PENX tool. And here we look at both individual as well as structural measures based upon address and historical address data, and then follow them over time with serial echocardiograms, biomarkers, as well as clinical outcomes. And through this work, and this is also through an AHA network award, where I've had the great pleasure of also getting to know and working with Dr. Ennis and also with Susan and many others. Through this work, we hope that we will be able to define how the sociological construct of race, both individual as well as structural measures, are associated with cardiotoxicity risk and cancer. We do hypothesize that the social determinants of health will be associated with increased risk of cardiotoxicity in this population, and association will differ from rate to race. I just want to share with you some early descriptive findings from these cohort studies and data we can see in the population of patients. And we see at a pen, and we care for a pen. Black men have disproportionately worse nutritional status, as well as greater food insecurity compared to white men. Also, significant disparities in terms of healthcare and discrimination. 51% of Black men compared to only 4% of white men state that they suffer from discrimination. And I've shared this with my research team many times. I mean, we read about this all the time in the literature, and it is extremely disheartening when we see this. But then when it's your own patients that you're caring for in everyday clinical practice that you're sitting across in the clinic room and that you really sincerely want the best for them, it hits home that much harder that our own patients, my own patients, are suffering from these significant disparities. And it drives us further and motivates us further to work to make a difference. We also see significant disparities in structural measures, SVI, just like the retrospective data, our prospective data also corroborate this. And what is the significance of these findings? Well, in our prospective cohort studies, we do see significant associations between worse SVI and worse physical activity, and worse SVI and increased risk of diabetes. And then in exploratory analysis, these associations are also stronger in Black patients. So in conclusion from this work, we can state there are significant disparities in cardiovascular disease risk, and then with prostate cancer, these differ according to race, also significant disparities in social determinants of health. And cardiovascular disparities are mediated by these structural measures, and we need, as Jane really motivated us to do and gave us a very nice pathway and roadmap, we need to develop multi-level strategies to overcome disparities in care. This work is part of an ongoing AHA Strategically Focused Research Network Award. Many of us are headed to Dallas later this week to present on this. And here we have the great privilege and opportunity to partner with experts across the country. You just saw June up here a few minutes ago, but she and Aziz Syed and Jill Wu are using the iPSC cardiomyocyte model to help us to understand the genomic basis of cardiotoxicity in both breast and prostate cancer patients according to race. And if there are differences, I'm leading a clinical science project, and we're, again, enrolling patients in prostate cancer as well as in breast cancer, performing very detailed characterization of the social determinants of health. We're also working with Sarah Armenian, Kevin Ball, and Alex Vonroff on physical activity intervention, specifically in Black and Hispanic breast and prostate cancer survivors with increased risk, trying to use behavioral economics principle to motivate and increase physical activity and ensure that it's sustainable. And also with Clyde Yancey leading a training and educational curriculum focused on and investing in the next generation of physicians and scientists. We're also very interested in overcoming disparities across the globe and have an ongoing CBAR pilot in Botswana, where we're looking to define the intersection, particularly high-risk populations. Those women who suffer from breast cancer have a high prevalence of cardiovascular risk factors and also suffer from HIV, which also adds additional risk in terms of immune deficiency, endothelial dysfunction, and inflammation. So in closing, how do I think we can continue to advance actual science in the care of our patients? I think we need to comprehensively understand disparities in the cardiovascular care of our patients with cancer and understand the basis of these disparities, the why. Move past just a simple description. We need to work, of course, to overcome disparities to ensure accessible and inclusive care for all, and determine the most effective evidence-based care models for our patients. And then ultimately also, of course, build, educate, and strengthen the global community through science, innovation, and patient centers. And again, I want to thank GCOS for bringing us all together. And of course, we also need to invest in the next generation. And we at Penn are very highly committed to this endeavor and really have the privilege of working with such bright-minded young scientists and physicians. And of course, as a journal, also highly committed to this and published a special issue on the social deterrence just in June. And I also want to call out and thank Sadhu Manatra for bringing this idea to our forefront attention at one of our editorial board meetings. With that, I want to thank you all, thank patients and the various collaborators for spotting sources. Thank you. So much, Dr. Key, we have some time for questions and answers now. I want to come out to the podium. We're happy to take questions. I'm just going to start out and say that I really appreciate all the work that you guys have done in this stuff. I'm going to read off this because I'm nervous, but I believe it's understood that patient-doctor relationship can influence patient outcomes, and that language barrier is factored. And I'm unsure if professionals believe that Ebonics to be a different style of English language. And I was just wondering for Dr. Farrell, you know, saying everybody, Wally? Sorry. I was wondering in your framework is Ebonics just trying to close the gap between how doctors understand Ebonics that could be considered in your framework, or how it could be considered in your framework for lessening health disparities among patients. For some reason, I'm having a hard time hearing. I don't know what, but I think it's about your questions about language and meeting patients where they are in terms of language. It's specifically African American nations, so and just understanding that a lot of African American patients speak in Ebonics language, which is a different type of English style. So is that going to be considered in your
on health disparities framework you sell out? Sure. So we don't specifically talk about emotics in the framework, but we do talk about culture of humility and getting training on better understanding the culture of the patients you're working with. And that is a huge tenet of the work in community engagement. It's about understanding not only where your community is right now that you're working with, but also understanding the history of the what has impacted the health of the community. So just to give an example, I work primarily with African American women who live in the Washington, D.C. area as a part of studies to address cardiovascular health for women at risk for cardiovascular disease. And so working in that community, building trust in that community required me to not only build partnerships with individuals who live and work in Washington, D.C. and the metropolitan area, but also required me to understand more of the history of how social political factors have influenced health. So, for instance, there's a great deal of distrust related to how the HIV epidemic was dealt with in the African American community. There's distrust related to how crack cocaine epidemic affected the Washington, D.C. area, and that's not unique to Washington, D.C., but those are issues that came up that I had to better understand as I worked with the populations. But I think you can bring up an excellent point that language also plays a key role. You have to understand how your patients are communicating with you, and so I think that plays into even some benefits in having racial and ethnic congruence in the caregivers of patients, their breast population.
Thank you. Thanks so much. We probably have questions for one or two more people. We'll take one part.
Thank you. So my question is for Dr. Julie. I think that your work looking at how social determinants of health affect the cardiovascular outcomes of Black men with prostate cancer is really profound. And my question was, what are your thoughts about the underlying mechanisms as to why you see that? Is it, like you mentioned, barriers to care? Is it maybe epigenetic changes related to food insecurity? Is it chronic inflammation and psychosocial stress? What are your thoughts about those underlying factors?
Yeah, no, thanks so much for that question. I think just very broadly speaking, and this is probably too broad, and we need to dive deeper into some really intriguing work on how the social determinants then affect the biology, but socioeconomic status is largely causing or mediating a lot of this. But then what is it about SES, I think is what you're saying, that's then resulting in these disparities? Is it that stress that the results will lead to increased inflammation and so forth? Is it that stress that's not resulting in them not being able to get their cardiovascular medications and so forth? I don't think we know yet, but this is what I think we're trying to figure out. For example, to the AJ, SFRN, and through that work. I will add one other point to that is what was particularly humbling about that work was that actually in terms of cancer outcomes, there were no differences. That Black men and white men had similar prostate cancer outcomes, but they're really suffering from cardiovascular morbidity and mortality. So really, really humbling in terms of the work that we had to do. Maybe it's just that they weren't getting appropriately managed because of financial stressors and financial toxicity. We don't know. Well, we need to figure it out. Thank you.
Yeah. Thanks so much. Are there questions for one more person over here?
Yeah, sure. Thank you so much. And that's researcher, so I enjoy this part really very much. So I have a question for Dr. Cormany and Kay. I want a lot of disparity research that focus on the racial and ethnicity disparities. I'm wondering if you have looked at gender or like sex disparities, because there is a biological, it's a underlying, and also the like structural sexism also like immediate outcomes. So as far as I am just the basic statistics, that we may have lower a risk of cancer death and lower risk of cardiovascular disease. However, when we see the cardiovascular mortality among the cancer patients compared to the general population who don't have cancer history, that women had a higher mortality risk than the men. So I just wondering, have you ever looked at the like gender or sex disparities? Is there?
So, my group in particular has not looked specifically at sex or gender disparities, but there's certainly data to show that those disparities exist. And I would say we know, as I mentioned, that there's disparities in outcomes, cardiovascular outcomes for patients. For women versus men with Hodgkin's lymphoma for cardiovascular outcomes. But there's also some data that suggests disparities for sexual and gender minority patients in terms of higher cardiovascular mortality in those populations. And so, again, I think that highlights the need for building these diverse cohorts, working within communities to build diverse cohorts, to build the trust that's required to have individuals who are traditionally underrepresented in research populations to feel comfortable being a part of research studies.
Yeah, I did elaborate. I have a lot. So,
I think we're out of time, so sorry, but we can come up and chat afterwards. Thank you all so much for your attention. Thank you so much to the speakers for an excellent talk.
So I want to first thank all the organizers for inviting me to be part of this. I have the great pleasure of introducing our Thomas Force Pioneer Award winner today. So I really felt like when you start looking at Dr. Lipshultz CV or looking at all of some past work, it really gets quite long. And so as it turns out, I called him a couple of weeks ago just to kind of give the other side of the story. And it reminded me that how bold it was for so like when I first went to MD Anderson in about 2000, I was, cardiologist at a cancer hospital, and I was trying to think, well, what exactly am I doing here? And I started looking around. All of a sudden, I saw all these papers by Dr. Lipshultz about looking at cardiac biomarkers, children that were undergoing cancer therapy. I thought, wow, that's pretty cool. He's kind of looking at the cardiology side and the cancer world. There might be something to that. And then, of course, I reached out to him way back then and would invite him to talk at some meeting or try to meet up with him at one of our annual meetings. And each time I had met with him or talked to him, it was very clear to me that he was not only a visionary, but he had, absolute determination. And he didn't do it in a way that was abrasive, but rather, for somebody who was so determined to actually do something in a gentle way, this is kind of remarkable. So over the years, it's been astonishing to see what he's achieved. And so it's my great honor to introduce Dr. Lipshultz as our Thomas Force Pioneer Award winner. I did want to remind everybody who doesn't know who Thomas Force was. And he is our first and only Hall of Fame inductee in 2016, and really a great listener for many in the row. But certainly for me personally, he was a very smart, kind patient. We made the decision a little while ago to making this Pioneer Award for Tom Force in his memory. And I think it was obviously a very good thing to do. And then I would also say you've seen many of these people on the stage this morning. So these are our fellow pioneers, of course, behind you, who you've already heard from several times, including just recently, and then soon Dennis, Della Cardinale, and Joe Carver. These are all previous Pioneer Award winners. So I want to welcome Dr. Lipshultz. There, yes. Thank you from the bottom of my heart for all the years and all he must have said. Truly honor do that. Not heavy. Weapon must be yes. Thank you.
Thanks, Danny. And Tom Force and I were on the Harvard faculty together. I had the pleasure with his presence, including his wisdom and wit, making this award even more meaningful. And at least for me, as Dan was saying, patients are the real heroes for me, who life with courage and dignity and a smile, and that'll never leave you. And I got into this for having a lot of pediatric patients that, just like I said, they never leave you. So I accept this award on behalf of those who fought their disease and won, in memory of those who have not. And along those lines, I'm also, when I started taking care of these patients, it's the late 70s, early 80s, and there was no room full of people like this. So I'm proud of you and your teams for having created absence of hope that your patients with these serious diseases and their families really a reason to believe that they'll get the highest quality of life by having these programs address their physical, social, spiritual factors that exacerbate their distress. And so the goals of this meeting and each of you, the integrated programs you're working to try to them become so meaningful and important to me and for I think all of you and your colleagues for what you do. So I thought I'd try to go through a little bit of my journey with the idea that there's a number of people here that have been working on their journey, and that, with focus and determination, it can really make a difference. So beginning with the underlying cardiotoxicity and some disclosures in terms of learning objectives. So the third point is really the main one I wanted to focus on, discuss the role of translational transdisciplinary team science, emphasizing collaboration, data sharing, and diversity expertise to improve the quality of life across the lifespan. And so in the beginning, about 40 years ago, I started to get asked to see any long-term survivors of childhood cancer, the first generation of these patients, and come in and have events, so with anesthesia in the OR, or with activities or childbirth. And I published them as anecdotal case reports. I had a cluster in about a half dozen patients that had double hit hypothesis that a movie was made out of civil action. 5 young children under 5 that played in the same stream, downstream from a tannery where there were toxic exposures to myocardium. Sadly, they all got leukemia. The setting of getting chemo before them, I had to do cardiac transplants on. So this whole idea of exposures and what really leads to this. So based on that, working my oncology colleagues, I started a prospective study of anthracycline-treated children 6 years after therapy, and resulted in that New Journal paper there. And in that era, the feeling was if you didn't get heart failure during therapy, you were good to go. And so about 2 years after the New England Journal paper, the administration at Boston Children's Hospital said to me, Dr. Lipshultz, which should our cost center do you want to have us charge the more than $1 million of cardiac tests associated with your long-term survivor care? And I said, well, what do you mean? I said, well, no insurance company is covering this because they said, quote, there's no need for survivor cardiac monitoring since it's not a problem. And so we've come a long way. And so in my journey, I'm going to go through a lot of slides relatively quickly, not as a scientific talk, but just to have you understand, to me, and it emphasized to me that if we want more evidence-based practice, we really need more evidence, more practice-based evidence. So that really led us to say that am I just saying there were exceptions? So we've worked here to study the coarse and green on the top, yellow risk factors at the bottom, develop a number of biomarkers to see which unvalidated surrogate endpoints, the longest lead time. And this has helped us in the bottom with preventive strategies and treatment strategies. At least in children, our mechanism of action for the anthracycline published extensively through the years. It's cumulative, mostly irreversible, dependent on individual sensitivity, unpredictable, underestimated. And in the cartoon, it's the anthracyclines go into the cardiomyocytes, bind iron, get free radicals, use myocytes early on. We have very few children in a cumulative dose-limited setting or congestive heart failure, but having an inadequate number becomes important. So some of our work dovetails nicely with the talk yesterday about the importance of iron. So we did a bunch of studies in preclinical models and children, in this case with high-risk leukemia, looking at the gene for hemochromatosis where there's higher iron inserted. Clinically, we found 10% of these children with high-risk leukemia had the CA2Y mutation. And what we found was when we treated them with anthracycline, what we published was they had 9-fold higher rates of dead and dying heart muscle during anthracycline chemotherapy than children with the exact same disease on the exact same protocol that didn't have that mutation, again, supporting the importance of this hypothesis. And so we use some heart muscle cells training there. Price and pay, no heart failure, treat, cure. I brought them all back 2 years later in the bottom. Those carriers that were NGFE had significantly more dilated left ventricles, more open dysfunction that are posterior walls, and reduced LV mass, providing service area than normal. So one of the things that I had put in the title of the last slide, that was something that if somebody's newly diagnosed, we can screen for. Certainly, when I was a voting member of FDA, there were other mutations for toxicity and genetic mutations that were approved. And we didn't, but we're not necessarily doing that here. Helps you protect the heart when you solve the therapies. I also been PI of a multi-center large NIH study of not gene mutations associated with toxicity with chemotherapy, but gene mutations associated with having less cardiac reserve. This is a study that had almost 600 children and their families and had clinical cardiomyopathy and what gene mutations. And yeah, we can screen for that also. Why? Well, it's less cardiac reserve. Having predisposition, I mentioned earlier, double that hypothesis. So both of these, genetics are important, and isoregistering really makes a difference. On the gene mutations we see absolutely never in certain ethnicities, backgrounds, and very high levels in others. So there's a lot more science you can bring than trying to protect the heart. So one of the things that we did in that paper where the insurance companies would pay for what we've considered clinical care was in this figure, we looked at the contractility of the left ventricle, the health of heart muscle cells. And we found that in these 4-year-olds that are treated with about 360 milligrams per square of doxorubicin, that's at time 0, and they got it over the first year and a half of therapy with the red dash line being the end of doxorubicin. At the end of doxorubicin, their LV contractility was significantly less than the red line that says normal, and they had an asymptomatic dilated cardiomyopathy. Great. Over the first 6 or 8 years, there were more than 12 papers published in the literature. People said, no big deal. This is, you get a poison, you get away from the poison, you recover, you're good to go. Well, in this field, children look forward to decades of active, productive life, and the real endpoint is their quality of life. Lifespan. 6 years is not your endpoint. So here we're continuing to follow that. And what we found is as these kids went through puberty and their body, and their heart needed to grow, they lost enough heart muscle cells that their hearts were too small for their body. And they developed about 13, 14 years later, not a dilated cardiomyopathy, but a restrictive cardiomyopathy. It becomes important as we think about this. On the right here, what we did were echo studies and echo measurements. And people said to me, those are going to stay asymptomatic. Well, on the right, a lot of very large population-based epidemiological studies, every single one is consistent. 20, 30 years out, very increased levels of morbidity and mortality from a cardiac perspective. And we found in another study we published in the New England Journal of Kids with Osteosarcoma and leukemia 8 years after getting this, that there were 2 distinct pathways. One, common in adults and kids. We reported that at the same dose of anthracycline, female sex was much more susceptible to the toxicity than male sex. And in our multivariable analyses, it was associated with decreased left ventricular contractility, which drove heart function down and green on the bottom. But what we found is growing children, you have a 60-gram LV at 6 months of age. The loss of muscle cells in that younger age of diagnosis is an independent risk factor for having inadequate LV mass that is child reaching both sides. So increased years of follow-up, younger age, less wall thickness for body surface area, and increased stress on the walls of the heart. And we thought people might remember and call it British syndrome because the Grinch had a heart too small for the body. But the Grinch's heart got bigger, realized problems, but these kids don't. And so this is now the same cohort followed for 40 years, 40. And they're still have decades of life. Their hearts are basically too small for body size. And you see here, if you look in the upper left, the LV dimension goes from being dilated above normal for body surface area to about 15 years out where the red arrow is being too small for the body surface area. And if you look at the far right, LV mass, you can see just how much it's smaller for body surface area than it is, which is a problem. So people said to me that 5 years ago, no, Dr. Lipshultz, now you got 2 NIH grants to do randomized prospective studies of ACE inhibitor versus placebo. But we saw the SOLVE study in adults, and we saw this. We just know it works, and it is how you treat asymptomatic ACM. So I had to do a retrospective study, and I found that, yes, we gave an ACE inhibitor early on to the survivors that were treated with doxorubicin. Their LV dimension and fraction for mass really improved significantly. But it didn't prevent. The damage was done. It gave me 6 to 10 years before it's no longer significant. And for the group that we started with the heart failure, they absolutely improved them immediately. But by 5 to 6 years, 100% of them either died of cardiac death or needed a cardiac transplant. So the improvement with ACE inhibitor beta blockers to these patients in our studies, there were early improvements in LV structure and function. They were transient, the primary defect continued to deteriorate, and they mostly worked by lowering blood pressure and other factors. So second, my other colleagues said, well, we have such good survival statistics. We don't want to mess around with therapies. So we just know there's at least a dozen protocols around the world that get informed consent and that tell families that their children will have less heart damage by a gentler, lighter approach. That is, instead of giving the anthracycline or bolus over 15 minutes times 12 cycles, we bring them into the hospital for 48-hour continuous infusion and their peak serum levels are lower. And we'd be willing to do a prospective randomized study of kids with high risk ALL. So we did that. And in the field of pediatric cardiology, it's probably the world's record for cardiologists being blinded in a prospective study, 18 years. 18 years we were blinded. And finally, what you see here was, even with the longest follow-up, there was no significant difference in structure and function of the LV between the 2 groups, the bolus versus the continuous. There was no advantage for tenure or event-free survival on oncology. And it meant an extra month in the hospital for these 5-year-olds, extra cost, significantly more mucositis, and more thromboembolic events. And it didn't protect our. So that enabled us to say, let's get mechanism-based protection. So why don't we tested in preclinical about 200 different mechanism-related things. What was they were saying these signals that these peptides and vestroxaxine within our preclinical models in rodents really was very effective. I'll show you that in a minute. Dextroxyzine binds iron before it enters cycling center cardiomyocytes. The binding prevents the formation of an iron anthracycline complex, preventing free radical release in cardiac damage. In the cartoon, you'll see it here. The green dextroxyzine binds iron, the cardiomyocytes, the anthracyclines can't bind. There's less free radical damage and less cardiomyocyte apoptosis lost. This is even in the back of the room. If I said, which panel would you not want your heart to look like? You would all say panel A, upper left corner, I hope. So the kids are normally dosed or at the time with 12 courses of doxorubicin. So we tried to mimic it in our rat models. And the ones that took the doxorubicin alone had all the myocardial vacuumization, myofibrillary loss. And in the upper right, panel C, the ones that got the dextroxyzine before every dose, they looked much better. So that prompted my oncology colleagues to allow us to do together a study in children with high-risk leukemia, and our secondary endpoint was the death and dying heart muscle train therapy, as measured by cardiac troponin T and a SUN. Our DSMB unblinded prematurely. We had to publish this in New England Journal because it showed that the blue on the left, 50% of the kids that got doxorubicin alone had dead dying heart muscle. The yellow next to it, only 20% that got pretreated with the dextroxyzine. And on the right is the typical dose response curve. But our primary endpoint was 5 years after randomization. How did what was the health of these children's hearts? Because again, we cared about long term. So the upper cartoon is not kids at all. I stole this from the adult cartoon of what is pathologic ventricular remodeling. In this case, a hematopoiesis infarct. And as you see here, we've talked about here is this. As it thins, as it dilates, that outcomes. Our marker of pathological modeling is in the lower half of this, and as you see, the girls that got treated, this exact same study, this is our primary endpoint was 5 years out. The girls that got treated with dextroxyzine before every dose, the blue, no different than normal 5 years out. The girls that got treated with dextroxyzine without dextroxyzine, and the red, progressive pathological modeling. The asterisks are that it was significant. We then went ahead, the FDA said they wouldn't consider indication unless we did a number of studies. So a priority, we got them to approve a large 600 patient study with Children's Oncology, MSCE funding, showed the exact name for TCLA, NOL, on months. They wanted us to do a third study, so we some of our teenagers with osteosarcoma that were positive. We gave concomitant Herceptin and doxorubicin, concomitant, non-sequential, with dextroxyzine, and they were weren't significantly different than normal by EF on the left and NT road right. We have to do another one, so the fourth study, in this case, osteosarcoma, and then the DSMB, so I went and said if you even get one patient with heart failure, we're pulling the plug because it's probably unethical to give an anthracycline to a young child or teenager. You're at 600 milligrams per meter squared. What we did, we didn't get any heart failure, and going out to 600 and get dextroxyzine, they weren't different than warning. We're going to do 9 studies with this 6th one there at the right side was got another grant, brought in 10-year ALL survivors that we treated with invertetrazoxane or not. And we heard a lot about mitochondria, what was made today. So when you study mitochondria for about 20 years in this population, when we look at ATP production, oxidative phosphorylation, the table on the right, complex 1, complex 4 activity, whether you were in the dots group, the dex docs group, they were all normal. And we said, wow, that's good. We always thought that was going to be the hypothesis. Premature senescence, the mitochondrial aging, mitochondrial YEM don't look so good at these kids. And then we looked at mitochondrial DNA copy per cell. And in these young kids that, were 4 or 5, they were diagnosed at 14, 15. The group that got the docs, their strategy for protecting their hearts were that increased number of effective amount of mitochondrial DNA, highest you've ever seen, and it was dominated like the dex docs group. So we don't think that's a good lifetime mechanism. The 8th study we did about hundreds around the world as far as Perth, Australia, patients. Was we took all those kids, we randomized, we brought them back 18 years later, 18 years after getting randomized, because at the end of the day, that's what we really care about. We didn't have heart failure joining therapy, but how are they as adults? So we ran back and we found that dextrazoxane didn't protect the tumor and didn't keep second cancers. Dextrazoxane, the grade and a significant fewer cardiac events. This past year in JCO, we published that the dextrazoxane was associated 10 years later with better heart function, less heart stress. It was more pronounced. It's advantage at females and those who received higher recycling doses. And there was better heart function 18 years later. Somebody showed me, on Wall Street now, I don't think about it this way, but I guess it's being used more and more because it's a buy. One of the things that about 35 years ago, JCO asked me to write an editorial. I said, as a cardiologist, there should be a shift in the paradigm. And successful treatment of childhood cancer shouldn't be event-free survival, but should be the successful treatment of cancer determined by the balance between our oncologic efficacy on one side and toxicity and light effects measured by the quality of life for not only the patient, but the patient and their family over a lifespan. And so along those lines, I shared a lot of quality of life. It had a lot of graphs on this. I did an overlay on an adult published study of just adult heart failure patients. And here is the 16-year survivors of childhood cancer, and their PF, their physical function domain of an SF-36, a well-accepted instrument, was somewhere between New York Heart 2 and New York Heart 3. And then I brought them back in 20 years, and you saw that it got even worse. But if you ask them, how do you feel? There's a lot of invincibility, Lance Armstrong type syndrome. I feel great. So if you don't look, you don't know. Some of our current funding, and HLBI, ROI, R21, is to look at epigenetic clocks. You've been looking at upward here, focus on one of the interests of time. So if you look here at the second bullet, Monday, these patients were 23 years old when we studied them on the study. So that's their chronologic age, 75 survivors. But their grim age, which is based on DNA methylation markers of inflammation and metabolic condition, and it predicts lifespan and health span of age-related conditions, was almost 18 years beyond that. So even though they were 23, by chronologic age, their biologic age was worth 41 years of age. And so then you could say, well, yeah, but how's that relate to the heart? So the same study here, second bullet, the 17.6-year increase in greater biologic age was associated with the fall in LVEF from 60 to 49%. That's just with 10-year survival. So does this relate to the premature senescence, androcyte, mitochondrial toxicity, ongoing low-grade inflammation? So we were just turning about a little more this morning, lifestyle changes, and all, of course, most all of those. So one of the things, maybe in 2030, 2040, Rabbit Cardias did show their scientific statement on CardioOncology, which I did. And when I looked at that in the pediatric literature, I found there were more publications that were review articles or book chapters or clinical practice guidelines than there were really original investigation. So it prompted me to say discovery matters. So we've worked in 4 or 5 areas. So I'm putting this in just because some of you may not be aware of this, but it might be relevant for you. So in 2015, Cyril Pettit and I, and maybe 1 or 2 others, we started the Hessen Thrive CardioOncology seed funding program initiative to support enhanced long-term quality of life for survivors of childhood and adult cancers. And we wanted to fund impactful cross-disciplinary research that has real-world connections, and including translational cardiac collaborations. That continues, and just this week we announced our 2024 winners. We get about 100 annual applications. It's open globally. Joe Biden has inspired White House Cancer Shot Task Force Science published the whole article on medicine. It's like what's called enhanced quality of life as a goal for anti-cancer therapeutics about this program. So it's very vibrant. It's just 5 examples of that of the kind of Thrive funding cardio-oncology grants. So, if you have some great ideas or look out or like that, right, you can look it up. It's on the web. And we'd be happy to hear your great ideas. And then the second thing is, I had very few people to speak to when I started listening to these petitions. And I run a monthly webinar now on pediatric cardio-oncology. People wanted to hear, well, we want to see the recipe for a pediatric cardio-oncology program. So no problem. Most people, they're my colleagues. Will you give us the recipes for your program? So a lot of people talk about it, but the number that have truly functioning and the program is relatively small. So one of the things that I started in 2015, and some of my patients necessarily make it, that is my heart failure pediatric patients, really liver transplant or failed medical management. And many families want to make it better. So I suggested a senior scholar program, first in cardiomyopathy, now in pediatric cardio-oncology, foster and career development sessions. This less around cover patients and great family the lost rather cardio-oncology, but they started foundations of consult. And they're now funding our senior scholar in cardio-oncology. And so far, we've had 6 scholars, and all have made this their field of career focus or become chiefs in their institutions in this area. Another's an international authority. and it's more than 100 publications, presentations, some grants by senior scholars. And so feeding a pipeline becomes really important, especially in our case. We've been blessed by having consistent NIH funding, so we're able to get awards in NIH where research and follow programs. The third thing, I've been blessed by having so many and fantastic colleagues. This includes, I'm just talking this morning with Joe Carver, Giorgio Lanati, and that. And to be I also know that as a cardiologist, if I publish in a cardiology journal, my oncology colleagues are going to be up on that. If I publish an oncology journal the same way, so a lot of our early work, I tried to publish in general interest journals. Like, we were lucky and we got a lot of things in, but it's not going to be true for the world. So our feeling was at that time, there wasn't JACC Cardiology or any other journal. So we put the idea forward about starting a journal, CardioOncology, and Springer liked it, and it's still there, and it's growing, and I think it got the index 2020 there. It's the first in this field, and it's not a competitive thing. The field needs a place to get it good work out, and then we really appreciate the strong tie into iDosing and having a platform, not only for the science, but to help people really understand through being reviewers, and being editors, through being in a process. How do we really package this narrative? And then, another thing was a meeting like this is spectacular. It brings people together. Dissemination hopefully leads to implementation. So coming up in 2 months, I know I'm seeing almost all of you in Cincinnati at our face-to-face pediatrics, second International Pediatric Cardio-Oncology Conference. We take this really seriously. We have a planning committee that forms councils to play and very robust agenda. And along with that, like I said, every month we have webinars. And so, at least for this, to share a little bit of at least my personal journey, that cardiotoxicity is cancer therapy. It's pervasive, persistent, and progressive, often missed. The burden's increasing. 1 in every 500 young adults in the United States is a survivor of childhood cancer, and over 75% are treated with cardiotoxic therapies. I showed you there's genetic, environmental, and temporal factors that interact. And we can identify high-risk groups increasingly through that genetic predisposition, as I mentioned. I showed you continuous infusion, our Hemes didn't work. And it's now pro beta blockers, and it doesn't prevent long term. Showing you dextroazoxane and 9 studies we did prospectively. And finally, with this, understanding the etiologies, we give multi-agent chemotherapy, multi-agent cardioprotection needs to match that. So we've studied that for over 20 years now. I tried to show you a little bit that persistent mitochondrial damage may relate to the lifespan cardiotoxicity. And again, we have an opportunity, and that's always the politically correct word, opportunity, for there might more point of care, really diagnosed patient screening. If we know there's mutations, with 9 times more risk of then diagnosis, it's an opportunity for us to look at that, as well as underlying predisposition. And again, my last point on this, some president, somebody said, trust but verifying. And when they were all years ago, that and these survivors, our standard risk is they got 1 dose of anthracycline Their families said they couldn't do anything. Their cardiac stenosis, they were normal. The ones that got a high risk on maximal anthracycline, they said they can do everything. And the cardiac studies the same day were terrible. And so if you don't know, you don't know. And finally, this room really represents Team Reddit. And, I'm presenting it in the first person, but it's been the collective work of so many who strive daily to achieve the highest quality of life in this population. I just want to thank all of you for how, I am some things that at least me on there and not every read up some, I think what it is. So you wouldn't be here if you feel the same way. So thanks.
Thank you, Dr. Lipshultz, for this wonderful, inspiring regard. I guess we'll break and then reconvene in about 10 minutes for the myocardial solution symposium. Thank you.
Hello, everyone. I'm Sanjal Desai, Assistant Professor in the Division of Hematology, Oncology, and Transplantation at the University of Minnesota. And I'm thrilled to co-chair this session with Dr. Anju Loria, Heme Malignancies, Arrythmia, and Anticoagulation. So we welcome you to the session. Thank you. So in the interest of staying on time, we'll start with our first speaker, who is Dr. Abhishek Kongalkar. He is a hematologist at Mayo Clinic, and he'll be talking to us about updates in myelodysplastic syndromes and acute myeloid leukemia.
Thank you very much. Thank you to the organizers, and I'm very glad to be here. Sorry. Also, got it. Thank you. So yeah, I'm a hematologist, and I work at the Mayo Clinic, assistant professor, and I treat patients with MDS, AML, and I also do hematopoietic transplant for patients. So no direct disclosures. We have some funding to institution from these companies, none directly related to the talk. Yeah. So here's the outline of the talk. I'll try to sort of give you a more clinical perspective of how I think about cardiac dysfunction and cardiotoxicities, outline the current treatment paradigm in MDS and AML, and then go over how I think about cardiotoxicities with these drugs. And then how do we screen and prevent some of these complications? Then for transplant, how do we consider patients with suboptimal cardiac function? And then finally, what treatment modifications we can do to minimize some of these complications. So MDS and AML, we can think about these conditions as clonal hematopoietic stem cell disorders. And the first stage is really the clonal hematopoiesis, which then sort of goes up to MDS and then AMLs. And you can see that you can almost look at the, you can imagine that the clonal hematopoiesis stage starts with a few clones and then sort of expands as you go through to the MDS phase and then the AML phase, which is pretty much full of clones in the bone marrow. And you can also think that the treatment, therefore, is more intensive in the AML stage compared to the MDS stage. And at least as of now, we don't have any approved therapies for clonal hematopoiesis. So these are sort of the therapies that are sort of considered standard of care. The ones in red are ones that we think of as being cardiotoxic and screen for cardiac function. So MDS is basically also called myelodysplastic neoplasm. It's also called chronic leukemia. We tend to think of it more as a condition that is associated with primarily two main problems. One is low blood counts, as you can see, cytopenias and sort of bone marrow failure. And then on the other extreme, you have a propensity to cause AML, which is just increasing blast percentage of bone marrow. So based on where your patient fits, we tend to think of try to solve
these two problems, sometimes there is an overlap between the two. So if you have bone marrow failure, primarily the drugs that are used are improve your erythropoiesis. And on the other side, you have more cytotoxic therapy on the AML side. So the treatment guidelines for AML have changed quite a bit in the last few years. 7+3 remains our standard induction, but now there are many drugs that are approved in the last few years. So it really depends on the fitness of the patient and the disease state of the patient. So newly diagnosed patients, it depends on your molecular characteristics. For binding factor leukemias, I still prefer intensive induction. For some of the other targetable mutations, basically you have targeted inhibitors that can be used in combination with intensive chemotherapy, such as FLT3, and then you have some newer sort of regimens like CPX351, which is basically liposomal formulations of doxorubicin and cytarabine, and then you have HMA high-demand litigation plus venetoclax, which is now becoming more and more popular as is an older sort of adults of AML. And then when you go to the when AML, then it becomes a little bit tricky because of the fitness. HMA ven remains an upfront treatment, and then you try to do just more targeted therapies in these patients in combination with HMA ven. And now you have triplet regimens that are coming up as we go into sort of the more targeted therapy era. And the HMA ven is, given the fact that it works so well, we try to get this into more and more younger patients. And of course, it's more easy tolerated than your intensive induction. Now, when we look at MDS, we tend to think about what is the underlying sort of biology of the disease that puts patients at higher risk for cardiovascular events. So this was a SEER analysis that showed that MDS patients actually have a higher incidence of cardiac issues going into treatment. And it could be biological, it could be a function of just the disease, the exposure that they've had before. So this was a SEER analysis that compared age and gender matched controls. They found that the MDS patients have a higher incidence of cardiac events. And we know that from previous talks and also like from our pre-clonal studies of MDS, which shows that clonal hematopoiesis is actually an independent risk factor for cardiovascular disease, ischemic strokes, and it's sort of independent of other conventional risk factors like smoking, hypertension, and so on and so forth. And it's not just an association. There are multiple independent groups that have now shown that there's a causal association where actually the mutant TET2 cells can actually accelerate atherosclerosis. Not just atherosclerotic vascular disease, but also ischemic heart failure, chronic ischemic heart failure has been associated independently with clonal hematopoiesis. And if you think about clonal hematopoiesis being sort of a precursor to MDS and AML, you can sort of envision that that sort of plays a role into why patients are at a higher risk. So when you look at induction chemotherapy and our patients, typically in the age group of around 60 to 70 years of age, these were several registry studies that showed that like quite a significant percentage of these patients already have underlying cardiac issues. So you can see that anywhere from 10 to 40% of patients already have some sort of heart disease history. And then we think about cumulative dose of anthracyclines. So when you do 7 and 3, the 3 part is the anthracycline, where daunorubicin, typically standard dose is 60 milligram per meter square, where if you multiply by 3, that comes to around 180. And then if you do a reinduction, then that sort of times 2. So it's sort of getting up there, where if you go sort of beyond a couple of cycles, that can cause heart failure. And it's important to also consider the fact that a lot of these patients may have already had anthracycline exposure in the past as a result of previous history of other solid tumor malignancies. And here you can see that the prevalence of risk factors for anthracycline-related cardiac dysfunction is pretty much
is essentially very high. You have to think about this in every single patient. Okay. And then interestingly, we are now seeing more and more evidence that even hypomethylating agents in venetoclax have about a 20% incidence of cardiac events, which is again quite striking. This is much lower than anthracycline-related cardiac events, but it's still a very relevant point that we have to think about. The other sort of cardiac toxicity that we think about is QT prolongation, especially with FLT3 inhibitors. Now, FLT3 inhibitors are getting very popular, especially in combination with your standard induction and also as single agent and also in combination with hypomethylating agents plus venetoclax therapy. And all of them, unfortunately, have an association with QTc prolongation, especially the quizartinib drug, which at higher doses, in fact, really caused quite a significant elevation of the sort of QTc and torsades events, and to the point where the approved dose is 30 to 60 milligrams, which we don't see it that much. It's about 2 to 5% or so, but it's still a very relevant thing. And then you have to think about how do you adjust these doses when patients are on antifungal therapies. All of our patients are on antifungal therapies, pretty much everyone. Our most common drug is posaconazole, which is unfortunately a very strong CYP3A4 inhibitor. So you have to reduce the doses accordingly, almost by roughly around 50% across the board. So here's how I think about AML regimens if I have a patient with suboptimal cardiac function. So if it's a young fit patient, I would want them to get more intensive chemotherapy. A FLAG is a good regimen. Cladribine-based regimens are good without the anthracycline, of course. Decitabine venetoclax, although we consider this in older unfit patients, but we can sometimes use it in even younger patients with a sort of a suboptimal cardiac function. Cytarabine is another regimen without the anthracycline portion in combination with gemtuzumab. So these are some of the regimens we think about. In elderly unfit sort of patients with more comorbidities, we consider decitabine venetoclax as our primary go-to regimen, but there are other options as well, like cladribine, targeted therapies, and so on. Then just a couple of points about allogeneic bone marrow transplant. Obviously, all patients have to be carefully screened for cardiomyopathy, arrhythmias, effusions, and so on. And iron overload in some cases have had quite a bit of transfusions. And some of the post-transplant issues include polyglobal load, pericarditis, and so on. Now, so as I said, all patients undergo this evaluation. And then basically, I look at this as a very fruitful thing through secondary prevention strategies prior to them going forward, primarily with beta blockers and heart flow reduction. So measures to reduce cardiotoxicity really reduce during transplant. The main drug is the cyclophosphamide. We reduce the dose by about 20 to 50%. We consider reduced intensity regimens more commonly over myeloablative regimens, and then careful fluid management post-transplant are some of the main highlights of how we think about this issue. So in conclusion, MDS-AML and their precursor states are all associated with cardiac dysfunction. There are many drugs that are cardiotoxic, not just on the LV function, but also on the arrhythmias. Screening should happen at almost all patients with primary and secondary prevention strategies to be considered. And then especially the importance needs to be placed on dose modifications in the context of CYP3 and 4 inhibitors, and also preemptive dose reductions in patients with a sort of screening problems. With that, I'd like to stop here. So I'd like to thank patients and families and the Division of Hematology at Mayo Clinic. Thank you very much.
Thank you, Dr. Mangaonkar, for a very concise review of treatment with AML from CardioOncology standpoint. I will now invite Dr. Ronald Bidirectional, Professor of Cardiovascular Medicine at Stanford University, for the next presentation, Navigating the Complexities of Plasma Cell Dysplasia, a Cardiologist's Perspective. Thank you. Questions will be at the end of the session.
Okay, thank you so much. I want to thank the organizers for the opportunity to present at this meeting. So as we're going to talk about plasma cell dyscrasia, just a quick review about plasma cell dyscrasia. So plasma cells, of course, make antibodies made up of heavy and light chains. The light chains come in two broad flavors, kappa and lambda. And so now imagine somebody develops a clonal plasma cell population. Three things will happen. Number one is that the plasma cells will take over some percentage of the marrow, maybe a little, maybe a lot. Two is that the clone will typically produce whatever antibody it is destined to produce. So that's what the example I've given here, I lambda. And third is that the plasma cells will typically produce an excess of whatever light chain goes along with that clone. So this example, lambda light chain. There are now three possible outcomes. Number one, the most common, is that you have a clone that's not that at risk. It doesn't take over much of the marrow. The light chains and antibodies come out harmless in the urine. We call this monoclonal gammopathy of undetermined significance, or MGUS. The second is that it is a more aggressive clone that takes over more of the marrow. It leads to things like anemia, fractures, and this, of course, is what we call myeloma. And third is that the light chain just happens to be one that by its very conformation is prone to misfold and deposit. And that's, of course, we call AL amyloidosis. So it's likely obvious that number two and number three, myeloma and AL amyloidosis, can overlap, but they don't need to, because you don't need a lot of clonal plasma cells that make the light chain. It just has to be the wrong kind. Or put another way, if this is the world of plasma cell disorders, most of it is MGUS with a much smaller amount. It's myeloma. We can split that into symptomatic, which needs treatment, smoldering, which typically doesn't. And then overlapping that in a much smaller circle is AL amyloidosis, which will know that most of AL amyloidosis doesn't actually criteria for myeloma. We can make this even more complex if we then overlay ATTR amyloidosis, which shares a lot of the risk factors, namely age, with monoclonal gammopathies, and you can see that it will overlap with all this, but again, most of it is overlapping with MGUS. Now, when you're looking for a plasma cell clone, there's three tests that you want to do: serum and urine protein electrophoresis with immune fixation. This is looking directly at clonality for the whole antibody in the serum and for the light chains in urine. And then the serum-free light chain assay, which is indirectly looking at clonality by measuring the free kappa, the free lambda in the serum. The ratio should normally be approximately 1-to-1. But keep in mind that the marrow produces kappa about twice as much as lambda, but the kidneys are much better at clearing kappa than lambda. So as you have normal kidney function, you'll often have mild lambda predominance. Well, most of our patients who are older, they're going to have some degree of kidney dysfunction and therefore some kappa predominance. But anything above about 2 or 2.5-to-1 is clearly abnormal. So in terms of amyloidosis, it is a generic term for many diseases where you have a protein that's misfolding into the sheath, things stack into 8 to 10 nanometer fibrils, which then deposit extracellularly. And from a terminology standpoint, AL amyloidosis leads A for amyloid, L for the clonal light chain. Now, the clinical features of AL amyloidosis are generally, and this is largely distinguishing from ATTR, is that it is a quite multi-system disease. We're going to talk more about the heart, of course, but it's those rare for AL amyloidosis to involve all of these organ systems. It's even rarer for it to only involve one. So you want to look for things like proteinuria, neuropathy, dysphagia, constipation, macroglossy, large tongues, you can see in the middle. In terms of cardiac manifestations, it's, of course, a disease of heart failure with particularly diastolic dysfunction, heart block, tachyarrhythmias, low voltages on the EKG, which aren't always there, but are there much more commonly than with ATTR. And then a lot of people think about this in terms of a thick heart, that again, you can pretty much count on an ATTR cardiomyopathy, but you can't count on an AL because a lot of the cardiac dysfunction comes from the high toxicity of light chain fibrils. There are distinct MRI patterns, diffuse late gadolinium enhancements, difficulty knowing the myocardium, and then an elevated troponin chronically because of chronic destruction of cardiomyocytes. It's going to advance. Here we go.
So these are two echoes, and I ask you which of these patients has amyloidosis, and it's a trick question, of course, because the answer is that they both do. And the one on the right, oops, backwards, the one on the right, hopefully nobody missed. That's in the case of ATTR amyloidosis, is very thick, jumps off the screen. But now it really going. Okay, the one on the left, though, is a biopsy-proven, cardiac biopsy-proven AL amyloidosis. And how was this one discovered? Because of the combination of the unexplained heart failure with dyspnea and proteinuria. So to make the diagnosis, the only way to make an AL amyloidosis diagnosis is biopsy. And where to biopsy, our typical practice is to biopsy the clinically involved organs. So worried about the heart, then biopsy the heart. This has a nearly 100% sensitivity, and what's more is that you have enough tissue typically to be able to do the other important part, is subtyping it as AL or ATTR, et cetera, by immunofluorescence or mass spec. Cautions of abdominal fat PET biopsies, which you'll see in the literature with figures as high as 84%. That's really not right. That comes from an era where the only patients being diagnosed were those with really clinically overt disease, and of course was done only in specialty centers. Beware doing bone scintigraphy in this patient population. So this has been a huge advance for the diagnosis of ATTR amyloidosis. But this shows you why you can't use it in the setting of a monoclonal lymphopathy. So here were 292 patients with AL amyloidosis, and you see that nearly 40% of them had some uptake with bone scintigraphy, and in fact, 10% of them had frankly positive scans. So you can't use bone scintigraphy to rule in or rule out AL amyloidosis. So please, everybody, no PYP or in other countries DDD scans without first ruling out a monoclonal protein. This is the diagnostic algorithm. Once you suspect amyloidosis, the first thing to do is to look for the laboratory abnormalities for monoclonal protein. If it's not there, now you can move on to your bone scintigraphy. If you do have a monoclonal protein, now you must move on to biopsy. In terms of treatment, I always like to think of it with parallel paths, treating the consequences of the organ dysfunction and then treating the clonoplasma cell disorder. For the cardiac specific, the most important thing is volume management. These patients are often drowning in fluid because people are afraid to diurese them because of hypotension or kidney dysfunction, and let that happen. You generally want to avoid digoxin and biased amyloid fibrils that lead to local toxicity, more so at AL than ATTR. Beta blockers and vasodilators are typically very poorly tolerated because of hypotension due to not only the cardiac dysfunction, but the very common autonomic dysfunction and nephrotic proteinuria. Midodrine, in fact, is reasonably commonly useful. And then in terms of arrhythmias, that's a whole talk in of itself. I just want to focus on this issue, which is intracardiac thrombus in the left atrial appendage being extremely common in patients with atrial arrhythmias with this disease. You can see rates when you look in TEE that are extremely high from studies that have looked at this. So the general standard practice has been to get TEEs before every cardioversion. This was a recent research letter out of Brigham where they questioned that, and they said, look, we did 132 cardioversions on anticoagulated patients and just didn't look, and they did fine, which I suppose is one level of evidence. But I would say most of these are ATTR patients, and I would still have caution. I'd say the general standard of practice is still to do it for AML patients. Now, how about light chain-directed therapy? So this was the first study of any note that showed that chemotherapy does anything in this disease. This was melphalan and prednisone versus colchicine, and you can see that the chemotherapy arm did do better, but the overall survival was still really quite dismal. Median survival in the treatment group of about a year and a half. So this led to looking into alternative ways to control the plasma cell excretion, including with autologous stem cell transplant, which of course is nothing more and nothing less than a way of giving a high dose of one type of chemotherapy, in this case, an alkylator. But it hadn't been studied in a rigorous fashion. So this clinical trial was done, a randomized clinical trial of 100 patients in France, randomized to standard chemotherapy versus stem cell transplant. Keep in mind, the standard chemotherapy that they're randomized to will never be used today because we have far better agents. But this was the trial at the time, and people surprised the group that actually did better from a survival standpoint was the standard chemotherapy arm. And so there were a lot of critics who said, well, it was done in a bunch of small centers in France, and they didn't really know what they were doing, and the transplant-related mortality was too high. But they had built in a 6-month landmark analysis as well, pre-specified, that said, we're only going to look at patients who made it through their therapy and lived at least 6 months. And even there, you can see that the trend is in favor of a standard chemotherapy. Then when you consider these days how much better and how many even more options there are for standard therapy, and I would say the role of stem cell transplant has really grown much smaller. And so these days, most patients will get started on the combination of daratumumab, a proteasome inhibitor, a steroid, and an alkylator, the so-called Dara-Cyclor-D regimen. And the real workhorse is this medication daratumumab. It's a CD38-directed monoclonal antibody. We did one of the first studies of inhaled amyloidosis, 25 patients who had gone through a median of 3 prior therapies. And we put them on daratumumab, and they all had drops in their free light chains, and you can see most of them had dramatic responses, with a lot of them having complete hematologic responses, despite being quite treatment refractory. So data like that led to the Andromeda trial, which was a randomized placebo-controlled trial of patients getting standard of care chemo at the time, Cyclor-D, with or without daratumumab. The primary outcome being 3% with a complete hematologic response. And you can see that just adding daratumumab to the standard chemotherapy about tripled the rate of a complete hematologic response, really remarkable, and it about doubled the rate of a cardiac response. So really a game changer in this disease. I just want to finish with a couple other comments on plasma cell disorders. So specifically about proteasome inhibitors, of course, the ubiquitous proteasome system is involved in normal cardiomyocyte function, raising the concerns that proteasome inhibitors could have cardiotoxicity. The 2 main ones that are used, of course, are bortezomib and carfilzomib. But keep in mind, when you see cardiac events in these clinical trials, sure, they could be from toxicity from the agents, but they could be from other things as well. Past treatment toxicity, overlapping non-cardiac symptoms, bone marrow shunting, I'm going to mention that in a second, and then fluid retention from common and IV fluid steroids, and of course, undiagnosed amyloid. So the data from bortezomib, this is the original trial, New England Journal of Medicine, 2005, and what you can see is that when you compare bortezomib versus dexamethasone, there's just not much there. Rates are pretty much the same. And this is a meta-analysis of over 5,000 patients in 25 clinical trials. Very low rates of toxicity and no different from the control arm. So my take on this is that bortezomib cardiotoxicity is really not a significant clinical problem. Now, carfilzomib is a little different. This was one of the main trials called Inspire, comparing carfilzomib addition to lenalidomide and dexamethasone with the 2 alone. And here where you start looking at things, you can see modestly higher rates of events in the carfilzomib arm, actually most notably in DVT and hypertension, and a little bit on the heart failure endpoints. This was a study that was prospectively looking at 95 patients with myeloma getting carfilzomib or bortezomib-based therapy. And they did really intensive assessments with biomarkers and echoes and EKGs every cycle. I would recommend doing this clinically. This was done in a study. And you can see the results showed very high rates of toxicity, but most of these were small biomarker elevations. But clearly, carfilzomib sticks out as worse than bortezomib. And then finally, Endeavor, which is the study of carfilzomib versus bortezomib in myeloma. And you can see the rates of adverse events do seem to be higher in the carfilzomib arm, legitimately so, about twice as high, or more in some. But they have also built in an echo sub-study where 151 patients got echoes at baseline and then every 3 months. And none of them developed systolic dysfunction, not a lot at the carfilzomib arm. So what this tells us is that carfilzomib cardiotoxicity is real, but not as common as we think, and it's not a disease of systolic dysfunction. So echo monitoring, I would argue, really doesn't make sense most of the time. Hypertension, venous thrombosis, and HFpEF are really the bigger issues. And the last point I'll make, because I think this is very underappreciated, it's a very real entity, and that is high output heart failure happening in the cases of really rip-roaring myeloma. So this was a nice figure from a study of 11 patients with high output heart failure who had injections of this nuclear labeled microaggregated albumin particles, which should get caught up in the capillaries, and they're injecting it in the femoral artery. So if it makes its way to the lungs, it tells you there's got to be bone marrow shunting. And as you can see in those examples, it makes its way to their lungs of the lungs. And you see about a quarter of patients in one study, 16 or 18% in the other, just looking, screening all comers, you'll have high output heart failure. So again, if you see a myeloma patient with heart failure, particularly if they have a high plasma, don't forget about this. So in summary, AL amyloidosis, though it is a legitimately rare disease, you'll counter it. You won't avoid those diagnostic errors we talked about. And then treatment drug, the volume management, rhythm management, and then light chain therapy, which usually does not need to include stem cell transplants. We talked about proteasome inhibitors, more of an issue with carfilzomib, but not as a dysfunction issue, and about high output heart failure. I'll just point out, obviously, we've seen a lot of references today to JACC CardioOncology, but besides being a great journal for all things cardio-oncology, we've really tried to make it be home for amyloidosis, and we have a whole section on amyloidosis that you can that should be easily navigated to the website. And I just want to acknowledge the tremendous team I get to work with at Stanford and the Amyloid Center. So thanks for attending it. And
Thank you, Dr. Vidales, for such a detailed review. Next, I'd like to invite Dr. Bacanova, Veronica Bacanova, Section Head of Heme Malignancy and Professor of Medicine and Division of Hematology, Oncology, and Transplantation at University of Minnesota. And she'll be presenting T-cell therapies and advances in leukemia and lymphoma. Thank you.
Good afternoon. Thank you so much for the kind invitation and for selecting this topic for this conference. I learned a lot. This is a fascinating field, and I am happy to share with you some of the fascinating new class of cancer therapy, CAR-T. It's not only the first ever FDA-approved therapy for human disease, but it also transformed the hematology field, where we were lucky to get the first approval for CAR in 2017. So, my disclosures. So this is really a product of synthetic biology and fascinating reprogramming of the native T lymphocytes with a dynamic antigen receptor, which turns the T cell and augments the ability to kill cancer cells with a specificity for the antigen. It uses the variable fragment of the antibody as a part of the targeting. And in cell signaling domain, this is a CAR. The DNA of the CAR is inserted into the T cells via genetic reprogramming or manufacturing, usually using viral vector. And then subsequent CAR T cell is defined by the CAR and targets the antigen expressing cancer cell. This is in situ the diagram of the immunological sequence when the CAR-T engages the cancer cell in the tumor site. And this particular cell-to-cell interaction stimulates and activates the CAR-T in uninhibited and supraphysiological mechanisms. The CAR-T targets only surface antigens. It has an HLA-independent definition, and it is always on. It's not a tunable response. What this means is that when the CAR-T engages the antigen, it starts to activate, proliferate, make millions of cell copies, starts to kill, but most importantly, interact with all the other immune cells around it by secreting interferon, interleukin-2, cytokines, and then these other cells respond to the cytokines with the augmenting and accelerated response of an immune system to the cancer cell, particularly monocytes and macrophages. They secrete IL-6, IL-1, number of cytokines, which has a downstream effect on a patient's body. And so this is the list of 6 currently available FDA-approved products for human hematologic malignancies. They are targeting either CD19 or BCMA, which is a B-cell maturing antigen on plasma cells. And the FDA approval first was in 2017, and as you see here, it's really a rapidly expanding number of products available. We have now FDA-approved projects for non-Hodgkin lymphoma, for mantle cell lymphoma, follicular lymphoma, diffuse large B-cell lymphoma,
for acute lymphoblastic leukemia of adult and pediatric. In fact, pediatric B-ALL was the first disease for which the CAR T was approved, and the multiple myeloma. And for just to illustrate the rapidity with which this field is moving forward, as soon as last year, 3 of these products were in fact approved second line. So the first relapse of the diseases such as DLBCL, Bartzel lymphoma, and Mendelssohn multiple myeloma already is an indication for the CAR T-cell therapy, which really triggered a number of patients who come to us for the CAR T. And CAR T-cells are moving to other indications, and there are a number of clinical trials in solid tumor. And now, in the last 5 years, for a non-cancer diagnosis, such as autoimmune disease, lupus nephritis, myasthenia gravis, neurological conditions. There are slew of autoimmune disorders for which the CAR T cells are moving. So we really need to learn about CAR T, where we know they're effective, but they also came with the recognition of a very new and previously undescribed set of side effects. This is the CAR T cell journey. It starts with the apheresis, retracting the T cells called patient's blood, and then the manufacturing, which takes place in outside of the patient's body. Of course, in facilities, takes about 20 days roughly, and products are infused after a short course of lymphodepleting chemotherapy, and everything is happening very fast. After CAR T cell infusion, usually within 2 weeks, the CAR is expanding and works. After 2 weeks, things are quieting down. As soon as 1 month after infusion, we see typically responses, commonly complete responses as seen on the PET scan, the patient with a multiple relapse and refractory lymphoma with a complete resolution of the metastatic disease. And then there's follow-up. So it's one and done, then a single infusion. After the CAR T cell expand in a patient's blood, which is the first picture on the left, there's a sharp CAR T spike. Most of the mononuclear cells in the blood infect our CAR T cells. This is happening in the first few days, and then slowly decline. The subsequent of the CAR T expansion, there's the cytokine release, and the middle illustration showed the spike of the IL-6 interferon gamma and the CRP, which very closely correlates with the IL-6. And as you see these numbers, they are about 2,000-3,000. Even in a sepsis big shock, the interleukin-6 spike is about 100. When you look at the literature, the maximum is maybe 2 to 300. There is not a physiological status in the biology where you found these high levels of interleukin-6. So this is really uninhibited immune activation. When, as you can imagine, the cytokine release then lead to a syndrome, which is a response to this widespread cytokine and chemokine, which are circulating in the body. They are causing all kinds of effects on the endothelial function, on increasing capillary leak, on disturbing blood-brain barrier. And this syndrome has been a multi-organ, systemic inflammatory response. Typically presents with a fever. Vascular leak, of course, leads to hypotension, hypoxemia, respiratory distress, often kidney dysfunction or cytopenias, coagulopathy. So this multi-organ inflammatory response, if it is not recognized or treated, can lead to multi-organ failure and potentially life-threatening. There is a treatment which has been very idiosyncratic recognized to be extremely effective for CRS. It's a tocilizumab. It's an IL-6 receptor monoclonal antibody being used for mostly rheumatological conditions. But it turned out that it is a very effective blocking agent for IL-6, and very quickly reverses the CRS manifestations. In addition to tocilizumab, we have corticosteroids, which really are also quite widespread in use and are effective to address the widespread inflammation. There is a number of other emerging agents, as you see on this complex diagram. And some of them are already being used in the clinic, particularly IL-1 receptor antibody, anakinra, and some inhibitors of the JACC pathways, for example, ruxolitinib. So we have a grading system for CRS, and this really reflects the manifest clinical manifestations. Fever, that's the grade 1. Low blood pressure, that is dependency. If you respond to fluid, it's a grade 2, but you don't need a vasopressor, that's a grade 3. So this grading really guides the therapy with the use of tocilizumab and steroids, and it's quite widely used in the clinic. Another unusual manifestation is called immune effect-associated neurotoxicity syndrome, or INS. And this is ICANS is a syndrome of the brain dysfunction. It's quite remarkably how immune system can affect our brain function. We also often, we don't see it with any other therapy, but in patients develop cognitive slowness. They are often cannot really respond very well. They have sort of like aphasia. This graphia is a very sensitive tool. We have them write in sentences every day, and it's so sensitive that sometimes that precedes anything other you can find even in our indication. So ICANS is a very important syndrome, which again can become a very life-threatening, including risk for increasing intracranial pressure, brain edema. Right for that, ICANS is available every treatment is with the dexamethasone. So in terms of the toxicities, they have been well described for the pilot and pivotal studies for all of these 6 products. But in terms of the cardiovascular complications, they really haven't been studied very well. And it's really limited on positive data on a number of broad list of the cardiovascular complications. Some just hypertension that are common, part of the CRS, almost all of the patients will be without hypertension. Tachycardia, very common, grade 3, maybe one of patients, but it's also product specific. Those low Lipshultz that we used in these sites in clinical patients. So in terms of what's really available for the specific description and observation of the cardiovascular events, I really found 3 retrospective studies and 1 prospective cohort, and they kind of show a similar picture. This is a multi-center registry. Only 137 patients were described in this registry. They were about 60 years old. They were not all patients, actually it was 70. And there were 17 major cardiovascular adverse events, so about 12%. But interesting enough, for those patients who were not body measured, at least half of them had high top body levels. About 4 had a decreased EF function, and remember, this is not something which was prospectively designed, just were ready to echo having done. 6 cardiovascular deaths were reported, and 3 of those were with the sepsis or hypertension picture, and 3 were sudden cardiac deaths or cardiac arrests. 6 patients had a concomitant heart failure, and there were a number of patients with a new onset arrhythmia. Another study, one more point in this within this interesting observation was that time from the CRS onset to administration of tocilizumab was apparently associated with the risk of developing severe cardiac events. So shorter tocilizumab administration, the shorter duration of its fever leads to better outcomes. Here is another study which looked at cardiomyopathy, and again, about 10% of the patients develop cardiomyopathy, most of those were reversible, but there were a few patients with long-term cardiac dysfunction. And the study also suggested that the presence of the cardiovascular risk factors, such as hyperlipidemia, coronary disease, and use of beta blockers was in fact associated with the increased risk. So in terms of the pathophysiology, of course, there is a clear association with the CRS, when English is mostly cytokine-induced, but it also could be stress-induced or Takotsubo cardiomyopathy. Some of this is reversible. The direct damage of a cardiac muscle by CAR T has not been implicated from the studies. There is no cross-reactivity with the cardiac muscle, with the CD19. But as we move to other diseases, particularly solid tumor, for example, there is a study using a melanoma target, A3. In these patients, there were 3 patients who died with a cardiac necrosis. So I think it's going to be very important to really understand the cross-reactivity and on a target of toxicity of the CAR T as they move to other indications. There were some cardiac biomarkers tried to be recognized for the predictive value, but the studies are very, in perfect, this is just meta-analysis. And there was one prospective trial which looked at predicting the toxicity by doing the serial chopper DVT and ERT profiling, and basically none of those really predicted or were very helpful to manage or to identify earlier the patients who are at risk. One of the studies, this is a study from Germany, showed that chopper DVT, particularly for the patients who had an increase in the early, like first 14 days, have a higher mortality, overall mortality. I think it's just an interesting, provoking thought, and more work is we have to really see that look at the associations. So here are the best practice recommendations for the cardiac patients. They are supposed to, or they need to be evaluated for the cardiac function. Everybody has a echocardiogram, typically ECG, and we are increasingly use the cardiac biomarkers such as proBNP and troponin, particularly for the myeloma, where some of the patients could have a cardiac expansion at the baseline. So in conclusion, this is a very understudied topic in terms of the cardiovascular complications. It follows a new therapy. So a lot of work is being done to elucidate mechanisms and to develop preventive therapies. Troponins could be indicators for toxicity and may guide the administration of rosnilimab. I think that's an important, already in fact, it's changing the point that for patients with the cardiac risk factors, early tocilizumab may be useful to avoid or prevent more serious complications. So with this, I'm having questions and thank you for your attention.
Thank you for a very detailed description of CAR T cells and their cardiotoxicity. Our next speaker is Dr. Craig Beavers. He is from the University of Kentucky College of Pharmacology, and he'll talk about cardiotoxicity of pharmacotherapeutics and heme malignancies.
Thank you, everyone, for having me today. In the context of this presentation, I'm going to be talking about those cardiotoxicities. Obviously, in this session, we're clearly alluding to arrhythmias and what that looks like from a management patient population standpoint. I have nothing to disclose in this talk. We want to identify some mechanism of action as it relates to our agents of choice and the toxicity, specifically talking a little bit about arrhythmogenic-related toxicity. That went ahead and scheduled on my own. So we're going to talk a little bit about anthracyclines. I'm not going to spend an exorbitant amount of time because we've talked a lot about them during this particular conference and looking at the mechanism and related to cell death. And clearly, we're very aware of the cardiotoxicities that anthracyclines hold, knowing very well from the dose exposure standpoint in terms of what we lead to cardiomyopathies and et cetera. But when I'm drawing your attention away from that slide, I'm really talking about how we kind of underplay or sometimes forget about the risk of arrhythmogenic potential that anthracyclines can distribute or lead to. There's a broad range of cardiotoxicities that are arrhythmogenic potential that can hold forth. And unlike our cardiotoxicity that we see with cardiomyopathy, these can be dose independent, and oftentimes you can see a broad range of arrhythmogenic potential early on in the dose exposure, even right after the administration of therapy, and it can accumulate that incidence can increase over our continual exposure. And what we often see is this can be completely related to the agent itself in the administration of the cell toxicity that occurs with the agents, but also as the patient progresses towards developing that cardiomyopathy, we can see increased risk of arrhythmias, especially atrial fibrillation, for example, that is very similar to what we see in patients that have non-chemo identified cardiotoxicity. So we have lots of ICD and Holter-based studies that support that concept. And realistically, the bigger lessons point is we don't know ideally what the incidence back over time is, because historically in a lot of these original studies, they did not do baseline ECG monitoring or understanding who may have had this at the beginning or at the time. So it's an area of interest that we need to continue to identify and be proactively in terms of monitoring and understanding that is a risk factor as we move forward and continue to treat patients with anthracycline beyond just the traditional chemotherapy cardiotoxicity. And obviously, as we continue to look and explore ways, if we look at prevention, and obviously seeing the most recent CARE trial showing a major increase or change in LVEF, we got to continue to look to and evaluate strategies to continue to mitigate or reduce the risk of chemotherapy-induced arrhythmia with anthracyclines. Secondarily, another agent that's used in the heme malignancy is cyclophosphamide. It doesn't necessarily get a lot of great attention in the sense. Now, we know that cyclophosphamide is metabolized by CYP450, and a lot of variability can occur in that process and some of the metabolites that occur and how they're cleared and the risk factors that can distribute in terms of what we see in terms of side effects. But as is metabolized to hydroxycyclophosphamide, is further broken down to autophosphamide and through non-enzymatic reaction to a phosphoramide mustard and acrolein, which is the toxic metabolite that leads to a lot of the side effects. And what you can kind of see from this cardiotoxicity, you can really see that similar cell apoptosis that can occur across the broad spectrum and leading to a variety of cardiotoxic metabolites or cell death that can occur that can lead to that particular LV dysfunction. But more importantly, also be related to that cell death, we see a broad spectrum of arrhythmias that can also occur with this particular agent, so specifically ranging from QT prolongation to arrhythmias as well. And it's an interesting piece about this is when you look at a lot of the studies that look at cyclophosphamide-induced toxicity, historically, if you look at the gambit of it, on the right side, you can kind of see the incidence of the toxicity is variable, leading somewhere between 30%. Now, a lot of the literature is occurring in conjunction in stem cell patients that are being transplanted in conjunction with either anthracycline therapies or others. But to draw your attention, if you look at the Goldberg study, the largest study that's been done, and they kind of look at it by itself, or the largest study that looks at it by itself without any other agents, you see about an 18% incidence risk. And you're really dividing up into a cumulative body surface area that we see that risk of cardiotoxicity of 1.55 milligrams per meter squared per day. But interesting enough, when you look at the arrhythmiogenic potential of these agents, you can see that there are case reports and incidences of these patients developing QT prolongation or other arrhythmias at lower doses. Partially, maybe do they have comorbidities or renal dysfunction that increases the risk of that metabolite accumulating and causing these problems. But just something to definitely be aware of. And as we go through and better define our cardiotoxicity management, look at the risk factors for cyclophosphamide cardiotoxicity, and really as you approach that dosing threshold, or even if they have the comorbid risk factors, considering alternative therapies, and of course doing our consistent ECG monitoring and being aware of the side effects as they need to be managed as appropriately as they occur. In terms of protein tyrosine kinase inhibitors, we're obviously very aware that there's a arrhythmogenic potential with atrial fibrillation. We're going to talk about that in a moment, and especially we'll talk about the next session with Dr. Fraley. But looking at the bleeding risk is important to also consider, as these agents do increase your bleeding risk. If you are dealing with someone who's going to eventually develop atrial fibrillation, that bleeding is something to be aware of with these classes of agents, especially as you look at the kind of first and second generations. And the reason that bleeding mechanism happens is because of off-target side effects that impacts the overall platelet function processing. It's not anything that happens to intrinsically achieve the intrinsic extrinsic coagulation pathway, but internally with the platelet function. And we see that with the coagulation parameters as studied with the BTKAs, that they don't impact our overall coagulation parameters. It totally functions around the function of the platelet within that context. And of course, from a mechanism standpoint, there's off-target effects with the agents in terms of developing atrial fibrillation. And we see that especially with our earlier generation agents across the trials, that there is an increased risk of atrial fibrillation that we have to manage and be prepared for. And this creates quite the conundrum, because if a patient does develop atrial fibrillation, which they potentially can develop, that you then have to put them on anticoagulation with an agent that also predisposes them to a bleeding risk. That is a different mechanism of a bleeding risk that we traditionally see with our anticoagulant strategies. And of course, as we've seen with some of the newer generation agents, there is a decreased risk potentially of atrial fibrillation. There is some concern that as we continue to use these more broad spreadly, that maybe the atrial fibrillation risk may be higher than was suspected. And then looking at the BCA, BLTKIs, of course, these agents have kind of multi-kinase inhibitors with more than one target, allowing for additional downstream effects that may overcome the resistance. But as we see this, when we look at the cardiotoxicity profile of these agents, there is a broad non-class-wide effect with these agents. Rarely does a imatinib A be postulated to be positive with positive vascular effects. But balancing the understanding of the off-target and the on-target effects, you can see in the conjunction with the comorbidities, kind of a broad and diverse cardiovascular risk profile. And especially when you target it into the arrhythmia standpoint, you can see the imatinib having a high risk of QT prolongation and atrial fibrillation, and seeing some of the other second-generation agents having some risk, some QT risk or arrhythmia risk in that process. And so realistically, when you start looking at these agents and looking across the broad spectrum, it really is important to consider looking at these baseline cardio risk factors, kind of doing that baseline ECG monitoring, continuing to check regularly for those side effects to occur, especially when you're looking with a non-liver, and be able to be prepared that these are some considerations. Following electrolytes, doing the things that you need to do to lead to the prevention of that QT prolongation. And the last agents that I was tasked to talk to during this process in terms of heme malignancy is arsenic and arsenic cardiotoxicity. And arsenic-induced cardiotoxicity obviously leads to apoptosis, and inducing apoptosis factor to lead to cardiac cell death. And that is what we're looking for to use to manage these patients, especially in acute proteomic leukemia. However, because of that off-target effect, there is some changes that occur to both our calcium channel and potassium channels that lead to downregulation and changes that can increase in prolonged QT. Then arsenic trioxide is very frequently associated with the QT prolonged interval prolongation, about 26 and 39% of patients. And there's acute right ventricular tachyarrhythmias have been reported. And traditionally, due to the nature of these agents and the quick effect of these agents, you often see these effects that occur very early on in the treatment, about 1 to 5 weeks after therapy. And thus, because of the acute urgency and the degree of change that you see with these, it is suggested for weekly monitoring ECGs and electrolytes with arsenic during the first 8 weeks of therapy. And you can kind of follow based on the European algorithm that was providing the guidelines in terms of things you've got to think about. And what I like to connect the dots with the speaker at the beginning of the session, so we pointed out to, a lot of times these patients that are being treated are treated with other agents that concomitantly can change QT. So it's about understanding what are the risks, what other agents that are going to be contributing to this risk, how do we mitigate that risk, and being very vigilant in terms of providing a foundation to reduce that risk during the treatment with arsenic toxicity. So that in conclusion kind of gives us a broad overview, especially with focusing in terms of our imaging potential with our cardiotoxicities of heme malignancies. I think the big messaging that you want to take away from this kind of talk is clearly there's a lot of, given the mechanism of cardiotoxicity and cell death that occurs with a lot of these agents, there is an opportunity for patients to develop arrhythmias that we need to be aware of. But sometimes don't always take the precedence or awareness to our mind of the disease state. Proactive monitoring and being aware of that and understanding where their baseline arrhythmia status is and what potential things could be changing that. And then being aware that of the agents that develop cardiomyopathy, they also, once they develop cardiomyopathy, predispose them to additional risk of the arrhythmia potential. And this is a nice segue into our next speaker who's going to talk about when we develop those arrhythmias, especially looking at atrial fibrillation, how we're going to manage these strategies. So thank you.
And our last speaker of this session is Dr. Michael Bradley from University of Pennsylvania, and he'll talk about anticoagulation.
All right. Well, thank you so much for the invitation to speak today. And I really just want to give you congratulations to Dr. Blaes and Konety for already putting on a fantastic meeting so far. So, as you all probably know, I'm both a cardio-oncologist and an electrophysiologist, and I think you're going to see that arrhythmias are a significant issue in cancer patients that really requires a collaborative and nuanced approach to care. So these are my disclosures. So a little roadmap for today's talk. So first, I want to discuss some cancer therapeutics that are associated with atrial fibrillation, that discuss various strategies for thromboembolism reduction in cancer patients with AFib, and then highlight some of the limitations that we have in our current knowledge, and identify some priorities for future research in stroke and thromboembolism prophylaxis in cancer patients with AFib. So arrhythmias are a commonly encountered toxicity of various cancer therapies, though the mechanism of arrhythmogenesis varies. In some circumstances, this could be due to direct toxicity affecting either ion channels or intracellular signaling pathways, as is the case with your BTK inhibitors. Or in other cases, it may be secondary to another toxicity like myocardial inflammation, heart failure, or ischemia. And this is just a chart that goes over the various cancer treatments that are associated with arrhythmias, ranging from atrial arrhythmias to ventricular arrhythmias and brain arrhythmias. Now, multiple epidemiologic studies have demonstrated an increased rate of atrial fibrillation in cancer patients, and this is likely due to shared risk factors, systemic inflammation, and then, of course, the cancer therapeutics themselves. So in the study on the left from South Korea, the authors demonstrated that the incidence of atrial fibrillation in cancer patients was about 6.6 per 1,000 person years, with cancer being an independent risk factor for developing atrial fibrillation. If you look at the heme malignancies, atrial fibrillation was most associated with multiple myeloma and amongst solid tumors, esophageal cancer. And in a study on the right, this was led by Adi Yuha, he looked at the serum Medicare database and reported that the rate of atrial fibrillation in breast cancer patients, the annual incidence was about 3.3%, with the highest rate occurring in the first 60 days of breast cancer diagnosis. Atrial fibrillation was more common in patients who were diagnosed with higher stage breast cancer, and a new diagnosis of atrial fibrillation was associated with increased cardiovascular mortality in patients. So we know that certain therapeutics themselves can lead to the development of atrial fibrillation, and the ones that we think primarily are the anthracyclines, the alkylating agent melphalan, and then the BTK inhibitors. And I'm going to spend a little bit of time talking about BTK inhibitors because we know that AFib is a serious toxicity and it can lead to some anticoagulation challenges. So ibrutinib is a small molecule inhibitor of the tyrosine kinase that's used in the treatment of various B-cell malignancies. Ibrutinib is associated with the development of atrial fibrillation with rates in the literature in excess of about 15%. And this systematic review and meta-analysis from Daryl Denal, the pooled rate of ibrutinib-associated atrial fibrillation was 3.3 per 100 person years compared to 0.86 per 100 person years for non-ibrutinib regimens, with the relative risk of ibrutinib-associated atrial fibrillation being about 3.86. Now, Witzer and colleagues reported that the median time to develop atrial fibrillation setting by their users is about 7.6 months. The cumulative incidence of atrial fibrillation with ibrutinib was about 6% at 6 months, about 7.5% at 1 year, and then 10% at 2 years. A prior history of atrial fibrillation, older age, hypertension, and hyperlipidemia were all associated as are considered risk factors for the development of an arrhythmia. So I think it's clear to everybody that there's increased rates of atrial fibrillation with ibrutinib. But with the development of the second generation covalent BTK inhibitors, as well as the non-covalent inhibitors, there's been some questions as to whether or not there's a class-related effect. And in fact, if you look at some of the original studies with acalabrutinib, which was the first of the second generation inhibitors, the rates of atrial fibrillation were lower than what was seen with ibrutinib. So in the ELEVATE-TN study, which looked at treatment-naive patients, rates of atrial fibrillation were between 3 and 4% in the encalibrutinib arms, but about 1% in the non-encalibrutinib arm. And then the ASCEND trial, which looked at patients who had relapsed or refractory CLL, rates of AFib were about 5% in the encalibrutinib treated patients and 3% in the patients treated with other regimens. And then most recently is zanubrutinib, also a second-generation covalent inhibitor. And in the Alpine study, it showed that there was a significantly prolonged progression-free survival in patients treated with zanubrutinib compared to ibrutinib. And once again, the rates of atrial fibrillation were much lower, about 5% with Zanu and about 15% with ibrutinib. So all of this led people to think that maybe the AFib rates are due to off-target effects. And a really intriguing study suggested that the mechanism of ibrutinib-associated atrial fibrillation may be due to the inhibition of C-terminal SERT kinase, which is not affected by some of these other BTK inhibitors. And interestingly, C-terminal SERT kinase has already been implicated as a component of atrial fibrillation pathogenesis in the general population. So other theories have included a reduction in signaling in the PI3K-AKT pathway, as well as impairment in calcium channel handling. But I think that with increasing time and with increased experience with these ATK inhibitors, we're seeing more and more atrial fibrillation. We saw that in the cumulative incidence in the Wixer study, and now we're seeing it with the calibrutinib. Recent data from the ELEVATE-RR study demonstrated higher than expected rates of atrial arrhythmias with acalabrutinib, reported at around 90% with acala. Now that was still significantly lower than ibrutinib, which was around 16%, but certainly this was higher than in those original studies. So I think that we're probably going to be seeing more AFib with zanubrutinib over time, and I think that this really just speaks to the fact that there is something arrhythmogenic about this class of drugs. So given the burden of atrial fibrillation in cancer patients, it's important to understand the risk of thromboembolism in this population, although prophylaxis strategies can also pose some unique management challenges. So right now, we suggest using the CHA2DS2-VASc score in conjunction with the Hasbled score and platelet counts to try and determine the best strategy for thromboembolism prophylaxis in cancer patients. And if the decision is made to offer anticoagulation, there's increasing evidence to support the use of DOACs in cancer patients. So in this sub-analysis of the Aristophanes study, when compared to warfarin, apixaban is associated with a lower risk of stroke and systemic embolism and major bleeding, whereas rivaroxaban and dabigatran demonstrated similar rates of comparison. And if you use the CHA2DS2-VASc and the Hasbled scores to guide therapy decisions, then many cancer patients are not getting appropriate treatments. In our study that we published a few years ago now in JACC CardioOncology, about 44% of eligible patients who were defined as having a high CHA2DS2-VASc score and a low Hasbled score did not receive anticoagulation. And only 13% or 18% of these patients had platelet values under 50,000. So I think this really highlights the need to improve our application of standard atrial fibrillation treatment algorithms to the cancer patient population. And more recently, the Blitz AF Cancer Registry really reported very similar findings to what we reported back in 2020. They showed that when patients were enrolled in their trial, a significant number of them were either undertreated or brought no treatment for their atrial fibrillation. So all that being said, note that there are challenges with using anticoagulants in cancer patients. One of the reasons is drug-drug interactions. For example, we know factor Xa inhibitors can affect the CYP3A4 system, and direct thrombin inhibitors can impact the glycoprotein, and all of this can affect not only the metabolism of the anticoagulant, but the cancer drug themselves. But cancer is a disease process that can have increased bleeding. And that might be due to hematologic abnormalities that exist in the setting of cancer, like thrombocytopenia or anemia. There may be something inherent to the cancer itself. For example, specific cancer types are more prone to bleed, like those that affect the GI or GU lumen. And then we know some of the treatments can also lead to bleeding. So in this retrospective study, for example, we found that apixaban had a higher rate of major bleeding in GI cancers compared to non-GI cancers, and even more so in GI luminal malignancies. And apixaban had higher rates of bleeding compared to enoxaparin in those GI luminal malignancies. For this reason, we are often recommending using low molecular category for patients who have GI luminal malignancies who may require either prophylaxis or treatment of thromboembolism. But apixaban did have lower rates of clinically relevant non-major bleeding compared to rivaroxaban. Now, we already heard that BTK inhibitors, particularly iberdomide, can lead to increased bleeding, and this is due to its effects on platelet aggregation, resulting from inhibition of the glycogen 6 collagen activation pathway. In addition, iberdomide can lead to thrombus instability by impacting FLET2 signaling, and it also affects the ability of platelets to tether to injured vessel walls by impacting glycoprotein 1 beta and glycoligrams factor. You can see from this meta-analysis that the relative risk of overall bleeding was significantly higher in iberdomide, but major bleeding was not significant. Now, the big question is, are the JACC and CAS-led scores accurate? So this was a retrospective study out of England that looked at patients with a history of breast, prostate, colorectal, lung, or hematologic cancers. And the authors found that amongst those populations with atrial fibrillation, the JACC score actually performed pretty similarly to patients without cancer in predicting thromboembolism risk and atrial fibrillation, though they did find that the CAS-led score did not show good discrimination, indicating opportunities to optimize bleeding scores. But truthfully, other studies have suggested that the JACC score may not be so accurate as cancer patients. The study on the left is out of Denmark. They showed that patients who had a JACC score of 1 had higher rates of thromboembolism, whereas a JACC score of more than 2 had lower rates. And then in a similar study that was published in JACC CardioOncology, looking at patients with a JACC score of 0 to 2 who were not on anticoagulation, the 12-month cumulative incidence of an arterial thromboembolism was about 2% in area nucleated patients with cancer and only 0.8% in those without cancer. So again, we really probably are going to need to develop some better risk scores for this population. So this was a SEER Medicare analysis that showed that cancer led to a 9% increased risk of thromboembolism in the setting of atrial fibrillation. And the authors concluded that adding cancer to the JACC score improved model prediction, so-called CJACC score. But I think it's important to remember that this did not account for differences in anticoagulation stats. That's one issue that the authors did not do. And I've already shown you data that it shows that many cancer patients are not getting appropriate anticoagulation. If you look at this study from Dr. Abdelkadir, he actually showed that cancer is not associated with stroke risk after matching on stroke and bleeding risk and adjusting for anticoagulation status. So these data do not suggest that we should be adding cancer, and it should not lower thresholds for anticoagulation on patients with AFL. Lastly, I just want to touch on alternative strategies for thromboembolism prophylaxis. We do know there's a lot of bleeding in these patients, and there are going to be individuals that cannot get anticoagulation. So the left atrial appendage occlusion devices are becoming an attractive alternative. There aren't a lot of data out there, but there is a study from Northburn at Mayo Clinic that showed that there was no significant difference in bleeding, device thrombus, stroke, or overall mortality in the patients that got a left atrial appendage occlusion device with cancer versus those that did not. But remember, short-term anticoagulation or antiplatelet therapy is necessary, and there are going to be patients that cannot get that no matter what. And I do think there's still questions about device-related thrombus, particularly in the hypercoagulated cancers. So in summary, AFib is common, particularly with our BTK inhibitors. Cancer patients are often not receiving guideline-directed anticoagulation for thromboembolism prophylaxis. The JACC score may not be accurate in predicting thromboembolism in cancer patients. Remember, bleeding risk and drug-drug interactions impact the ability to safely deliver anticoagulation to some cancer patients with AFib. And the left atrial appendage occlusion device may be a viable option, but we still need a lot more data to fully record. Thank you all so much for your attention.
Thank you to all of our speakers. Unfortunately, I think we've run out of time. And so in the interest of staying in time, the speakers will be available. Please reach out to them with your questions. Thank you. Hello, everybody. Thanks for sticking around. My name is Dr. Michelle Bloom, and I'm a heart failure cardiologist and director of CardioOncology program at NYU.
Hi, everyone. My name is Dr. Christine Bryson-Masley. I'm a medical oncologist and medical director of the cancer program at Mount Sinai Hospital in Toronto, Canada.
And so it's really our pleasure to co-moderate this next session on cardio-oncology and heart failure. And our first speaker is Dr. Anita Jaiswal. She is the chair of cardiology and professor of cardiology at the University of Texas MD Anderson Cancer Center in Houston, Texas. And she will be discussing the role of permissive cardiac toxicity.
Thank you for the opportunity to speak here. It just seems like okay. My disclosure, not relevant to this at all. Over the next 10 to 11 minutes, I'd like to cover just some broad aspects about the concept of permissive cardiotoxicity, put it in the context of heart failure, and then what are the essentials needed for what we practice permissive cardiotoxicity. So this terminology of permissive cardiotoxicity, I want to acknowledge really, Dr. Porter is here in the audience, and I think he really deserves a play for this, because we've been doing something for quite a while and never really thought of this way, and maybe it gives it legitimacy to what we practice a lot in cardio-oncology. So several of these are borrowed ideas, and thank you so much. So permissive cardiotoxicity has really been the shift over the last several years. Initially, it was all about, oh my God, cardiotoxicity, stop the cancer therapy. And that's really what happened when trastuzumab cardiotoxicity was seen around the late 90s, early 2000s. And there's been this shift in that paradigm of, should the cancer therapy not be considered, or should it be discontinued due to the risk of or actual cardiovascular toxicity, to now, how can this cancer therapy be continued if it's really needed? Because the patients may not have many viable options or alternatives for cancer therapy. And cardiotoxic cancer therapies may then need to be continued in these patients who are either at risk for cardiovascular disease or with manifest toxicity. So it's really been the shift again from prohibitive no cardiotoxicity to permissive cardiotoxicity to allow better outcomes from the cancer perspective while maintaining cardiovascular outcomes. And so the way Dr. Porter and colleagues describe this as was permissive cardiotoxicity is the concept that balances the benefits of effective cancer treatment with acceptance of its associated and often off-target cardiotoxic effects, while providing the best surveillance and attenuation of the toxicity. And as we think about this, I think there's two really broad patient populations to be considered. Although we often consider this in the context of cancer therapy-related cardiotoxicity, I think it's also applicable to those who are with pre-existing cardiovascular disease getting potential cardiotoxic treatments, or going for high-risk procedures, not just high-risk surgeries, but therapies such as CAR T-cell therapy, stem cell transplantation, etc. And I just took the liberty of modifying this concept again in the same paper, starting off with those patients who either have pre-existing cardiovascular disease or during the course of cancer therapy develop mild to moderate cardiotoxicity. And then, of course, the serious cardiotoxicities. And what we often focus on, and when we're thinking about permissive cardiotoxicities, are these patients that have either asymptomatic LV dysfunction, or patients that have mild heart failure symptoms with or without LV dysfunction. And I do want to broaden it a little bit further to those patients with checkpoint inhibitor-related myocarditis, or whether it's really myocardial inflammation and they have a mild troponin elevation, we do a biopsy, they have mild inflammation but really no necrosis. Is that myocarditis? Is it myocardial inflammation? What do we do with the checkpoint? And then finally, there's a group with really serious cardiotoxicity. Usually we don't like to continue that same agent if possible, although they may be rare circumstances. And whatever we talk about permissive cardiotoxicity sort of assumes, but is really the biggest constituent of this practice, is the role multidisciplinary discussions between cardiology, oncology, and other teams, as well as that shared decision-making with the patient and with the patient's family. And this is, as we go through some examples of what we do in practice as far as permissive cardiotoxicity, I think starting off with really what is well known as the trastuzumab-related cardiotoxicity, and the FDA having these strict criteria about where we should hold it, interrupt it, when we can restart after the LVEF comes back to baseline, and then permanently discontinue it if the LVEF doesn't return to baseline in 8 weeks. And we know that interruption or discontinuation of trastuzumab is associated with worse cancer disease-free survival and overall survival based on retrospective data, as well as the fact that the closer the patients get into that 1 year of therapy rather than shorter-term trastuzumab, usually they do better from the cancer perspective. So we don't have a whole lot of randomized clinical trial data in this space of permissive cardiotoxicity, but at least these are two nice proof of concept prospective studies, that single-arm studies that looked at the use of trastuzumab in patients with mild LV dysfunction. And this was the SAFEART study, which had 30 patients, the Scholar with 20, but their concepts were very similar. So they all included patients that had received trastuzumab and had developed cardiotoxicity with mild LV dysfunction. So generally the EF was between 40 to 54%, depending on the way they described CTR-CD. And they excluded patients that really had severe cardiotoxicity, EFs under 40, under 35, or had significant heart failure symptoms. And the intervention included the initiation and then up titration of beta blockers and ACE inhibitors. They follow these patients closely. So the echoes became even more frequent than our usual 3 months. And I think in this patient population, that's really appropriate. So when they restarted trastuzumab, they followed them closer to make sure the EFs were not worsening. And clinically, of course, they were not developing heart failure symptoms. Both of the studies actually had very similar results, and about 90% of these patients with mild asymptomatic LV dysfunction could be continued on the trastuzumab without a significant decrement in their EF. 10% of patients did have an EF fall either to under 35 or significant heart failure symptoms as trastuzumab was stopped. So 90% of patients could benefit from this potential strategy. Of course, this is, we need to see it in a bigger patient population. The other thing I think that was remarkable in the 2 studies is, if you look at what the EFs did with this permissive cardiotoxicity strategies, the SAFEART, they started off at about 45%. And really, if you took the mean EF across the time period, it didn't change that much. Of course, we know there were 3 patients that dropped, but this was the average across the cohort. And it was similar for Scholar. In fact, at the end, about a year after trastuzumab, they noticed the EF had gone up to about 55%. And of course, they started off with just minimal LV systolic dysfunction under 50. And there is a randomized clinical trial with Scholar 2, which is ongoing with 130 patients testing the strategy against usual care. And, we're waiting to see those results, and hopefully we can improve this concept and go further. The staging group, as Scholar, was led by Dr. Leon, published this retrospective data in about 50 patients where a similar strategy was used. And again, they started off with just minimally depressed EFs, but as they continued and they followed these patients for 3 years on neurohormonal therapy, trastuzumab being continued, almost 90% of patients again completed the trastuzumab course, and the EFs at the end, the average EFs were somewhat higher than where they started with neurohormonal therapy. And I think this can then widen to other cancer therapy classes such as TKI with VEGF inhibitors, the combination of BEC inhibitors, BRAF inhibitors, EGFR targeted therapy. And although, again, the FDA has very strict different mandates, the concepts are similar. I would like to point out that not all LV dysfunction is cancer-related cardiotoxicity, and it is incumbent on us to really prove that there's no other etiology that's contributed, and that can be corrected. They could have ischemic heart disease, for example. And we should look into that while we start them on neurohormone therapy. And the other is agents like VEGF TKIs that really have this marked accelerated hypertension. Often that is the agent that's causing it rather than direct cardiotoxicity. And controlling that blood pressure aggressively can prevent and even improve the ES. And this is one area where it's nice to have blood pressure to work with, and then goes directly maybe to an ARNI and beta blocker rather than the usual ACE inhibitor route, because we're not showing what blood pressures do. How is this applicable to anthracycline cardiotoxicity? There are no prospective studies looking at this, but I think this nice algorithm that's there in the ESC guidelines, the bottom lines are anthracyclines are even a little more careful about. Although a number of them are reversible to some extent, I think they're less forgiving than agents like the HER2-targeted therapies. And if one does start them on neurohormonal blockers and tries to continue or reinitiate anthracycline therapy with EFs generally over 40%, one should follow them very closely and consider often off-label use of cardioprotective things like detroxycycline, liposomal doxorubicin, etc. And what about switching to immune checkpoint inhibitors? So we often face this: the patients receive immune checkpoint inhibitors, develop myocarditis, and now this was their last line of therapy. Often our knee-jerk reaction is really, it's difficult to reinitiate somebody on immune checkpoint inhibitors when they have developed myocarditis. However, it's something to remember that in general, immune-related adverse events recur in about 30% when they are challenged with immune checkpoints. This is not just myocarditis, this is across the board. And there have been several really small case series or case reports of patients that have been rechallenged. And out of these, about 31 patients, there was a recurrence before. However, this is just reports. We don't know how definitive the diagnosis of myocarditis was. Often these were milder cases, and how well were they followed. But it is something that can, again, be considered with multidisciplinary discussion and shared decision-making, but we don't do it very often. I would like to point out that at our center, we had 4 patients with really mild inflammation on endomyocardial biopsy out of about 28. And these patients, this was early in the day of immune checkpoint myocarditis, and they actually went on to get immune checkpoint inhibitors even after that, and did find they did not even receive immunosuppression. Again, this was early in the days. We're not sure what to do. So there are those circumstances with a lot more to learn, but if you ever consider it, it's a different checkpoint inhibitor, not dual checkpoints when you reinitiate, and of course, very close monitoring with components, etc. And I don't have time to really go into ICIs and heart transplant patients. That's really the ultimate of permissive toxicity, maybe for next time. So at the end, I think I would just like to conclude that we do practice this every day. Yes, permissive cardiotoxicity is a real thing, and you've been practicing it even if you hadn't realized it. So thank you.
Thank you, Anita.
Our next speaker is Dr. Darini Ramo. She is actually here an associate professor of medicine at the University of Minnesota, where she specializes in advanced heart failure and cardiac transplant, cardio-oncology, and also serves as the director of the cardiology program. And she will be discussing heart failure therapeutics during cancer treatment and beyond to survivorship.
Thank you, and Suma and the organizers for having me today. It's really my pleasure to be here. Here are my disclosures, not relevant to the talk. So cancer therapy is associated cardiotoxicity presents as a continuum of clinical features. And use as a heart failure cardiologist, we are also using the American College of Cardiology, American Heart Association staging of heart failure as we manage patients, and using that as a framework to guide this talk. Any patient who is exposed to cardiotoxic cancer therapy is considered to be at risk for heart failure or have stage E heart failure. They can progress to developing subclinical myocardial injury, asymptomatic decline in LV function, and may be referred to as pre-heart failure or stage B. They can go on to developing overt symptomatic heart failure, stage C, and ultimately progress to advanced heart failure, stage D, or death. And during the next 11 minutes, we will be working on talking about the management of each stage using heart failure therapies with the goal of preventing progression and improving survivorship. So again, using this framework, stage A is anyone at risk for heart failure, and the management goals when preventing your progression to stage B is really focused on what is a very team approach that can't be emphasized enough, optimizing cardiovascular risk factors. There are specific things that we consider when using anthracyclines. I'm not going to be talking about those, but what we will focus on are the heart failure therapies and do they have a role in this primary intervention. There are a few different multiple RCTs, and I'm going to be highlighting a few of primary prevention with heart failure therapies such as beta blockers, ACE inhibitors, angiotensin receptor blockers. Listed here are a few trials. Those highlighted in green had a positive result, and then in yellow were neutral results. And the highlight here is that most of these are breast cancer patients receiving anthracycline, some receiving targeted therapies. They were predominantly unselected patients. They did not focus on a high-risk population. And they used surrogate endpoints of imaging and biomarkers rather than clinical outcomes. Subsequently, a few more trials. The ICOS one was more targeted using positive troponin elevation to guide treatment, which is again a nuclear study. And then the STUPOR study, the initial ECHO study using GLS changes to guide initiation of cardioprotective therapies was neutral, and then more recently the MRI study showing a slightly positive signal. Now, there are multiple meta-analyses that have looked at the combined role of these cardioprotective therapies from primary prevention, and I'd like to highlight one, which is published a few years ago in JACC CardioOncology. This included 17 randomized clinical trials for nearly 2,000 patients with cancer receiving chemotherapy who received neurohormonal blockade with beta blockers, ACE, ARBs, or MRAs. The key finding was there was about a 4% aggregate attenuation in ES decline with neurohormonal therapies, but this is at a population level, and we don't necessarily know what it translates to at an individual level. There were multiple caveats in interpretation. There were small single center studies with wide heterogeneity in treatment effects, and thus there's a large unmet need of randomized clinical trials in this space that can guide effective treatment strategies. So there are multiple ongoing studies. I've listed a few here, particularly those looking at the role of the newer heart failure therapies like initial valsartan and SGLT2 inhibitors and so on. But currently, based on the data that is there, the American College of Cardiology, American Heart Association provides a Class 2B recommendation for the use of ACE or beta blockers for primary prevention, suggesting that using these drugs or primary prevention is of uncertain benefit. The European Society of Cardiology guidelines shown at the bottom give a Class 2A recommendation, particularly for patients who are classified as high risk or very high risk. Very briefly on statins for cardiac protection, there are a few different trials, and I'm highlighting just a couple here. The PREVENT the STOP 3A trial. The PREVENT study was predominantly breast cancer patients. with perhaps a slightly lower dose of anthracycline when they looked at changes in EF at 2-year period. There was a neutral study, or the START-CA, which studied lymphoma patients, slightly older, higher dose of anthracyclines. Was a positive study, but again, targeting a highly risk group. And it's possible that lymphoma patients with the higher inflammatory burden that they experience are more likely to benefit from the pleiotropic effects of statins. The European Society of Cardiology guidelines do provide a class 2A recommendation for statins for primary prevention for these high risk and very high risk patients. So if the patient wants to develop stage D heart failure, this is where they have structural abnormalities or asymptomatic decline in EF, is there any data to support use of cardioprotective treatment to prevent progression in stage C? There's limited data here. One study I will highlight is a study of over 200 patients from about 50 years ago receiving anthracycline-based chemotherapy and developed cardiomyopathy related to that. And among these 200 patients, as you can see, over 150 of them were in YHA class 1 or 2. A majority of them were stage D asymptomatic with heart failure. And what I've highlighted here, the white bar is the baseline EF, the black bar is the final EF. And even those patients who had asymptomatic decline in EF benefited by EF improvement with the use of these therapies. And again, starting them early, within 4 months of diagnosis was crucial in achieving that EF improvement. The American Association guidelines provide a class 2A recommendation in this setting for use of these ARB and beta blockers. And then the European Society of Cardiology guidelines are nuanced that talk about the use of naturally linked peptides or imaging changes or abnormal troponin to guide any fetal therapy. Now, of course, for patients who develop further reduction in EF or symptomatic heart failure, which is stage C, common sense suggests that you would treat them as anybody else with heart failure with the new therapies that we have. But the literature supporting the use of those drugs in cardiotoxic cardiomyopathy is limited. This is one study of over 2,500 unaffected treated patients. 90% of whom went on to develop cardiotoxicity, which was defined as a decline in EF of greater than 10 percentage points to value less than 50%. And they looked at the use of enalapril plus beta blocker, or one of them in recovery of ejection fraction. Whether they recovered EF fully, which was the black squares of the graph on the right, and then partial EF recovery, which are the black triangles. What they noticed was there was a greater improvement in EF observed in patients receiving a combination of ACE and beta blockers. And again, early initiation of therapy was associated with better outcomes. So as a heart failure cardiologist, we are very excited about the advances we've had in the last decade or so with sacubitril valsartan, with SGLT2 inhibitors. And we have what we talk about quite frequently are the 4 pillars of the quadruple therapy of GDMT for HFrEF. And again, we don't have the data to say that this is beneficial or not beneficial, but again, with the lack of data suggesting we shouldn't be, as long as patients tolerate these, it makes sense to use them. And so what the guidelines suggest is use these drugs despite the lack of evidence for this particular patient population, and initiation of titration of standard heart failure therapies would remain the mainstay of managing stage C heart failure in patients who develop cardiotoxic cardiomyopathy. What about those who go on to develop advanced heart failure or stage D? Now, these are patients who are refractory to standard heart failure therapies. And these are patients where, as a heart failure cardiologist, we are considering implantation of LVADs and heart transplantation. The cancer survivors derive similar benefit as the other population with advanced heart failure with other forms of cardiomyopathy. So what do we know about stage D heart failure? Not so much in the cardio-oncology population. So we know about 10% of anthracycline recipients develop over heart failure. The exact number of those who develop advanced heart failure is extrapolated from registries. And as you can see here, a very small number of heart transplant recipients and LVAD recipients have chemotherapy-associated cardiomyopathy. So heart transplantation really is the gold standard for advanced heart failure therapy. So we looked at the UNOS registry, which is a large analysis registry of heart transplant recipients. And we looked at over 10-year period from 2008 to 2018, over 18,000 heart transplant recipients, and compared the outcomes of those who had cancer therapy-associated cardiotoxicity to other forms. There were about 377 patients who were
reported as having alpha-cyclin associated cardiomyopathy, and we looked at outcome at 5 years. So what I'd like to highlight here, the table may not project well, but the key findings are patients with alpha-cyclin associated cardiomyopathy as compared to other forms of non-ischemic and ischemic cardiomyopathy, more likely to be younger women, fewer comorbidities, and higher cardiovascular resistance, a habitual of chronicity of heart failure. And despite this, when we looked at 5-year survival, these patients did just as well as those with other forms of cardiomyopathy. The graph on the right, the blue curve represents those who legitimize a cardiomyopathy, and as you can see, their survival curves are over that. Not everybody is with a history of cancer and subsequent cardiomyopathy associated with that is a candidate for transplant. We typically don't offer transplant because of the risk of immunosuppression, reactivating cancer or worsening cancers. And so most patients require some form of cancer-free interval, which may vary based on the cancer and so on. But for those who are not candidates for transplant, there are options for LVADs, which are left ventricular assist devices, durable support for those who have advanced heart failure in that case. And to explore how patients with chemotherapy-associated cardiomyopathy do with LVADs, this was an older INTERMACS registry that looked at their outcomes, compared those with other forms of cardiomyopathy. And as you can see, there was no major difference in overall survival, but these patients do have increased risk of major bleeding, as also right-sided heart failure and increased need for right ventricular support. So we looked at this earlier and used this framework of staging of heart failure to guide our discussion of how to manage these patients. And to summarize, Stage A, which is where they're at risk of heart failure, then clearly the current level of evidence is uncertain in terms of the use of heart failure therapies, but we want to focus on minimizing risk factors the best that we can. When they do develop stage B heart failure, there's perhaps some suggestion that these drugs may be beneficial. You definitely want to be treating them for stage C or similar decline in EF with standard heart failure therapies. And then for those who develop stage D heart failure, and heart transplant for that appropriate people. There are multiple questions that remain, including what are the long-term risks of neurohormonal blockade in these patients? Should we be targeting a high-risk population? And are we backing up the wrong tree? Should we not be focusing on neurohormonal blockade, but rather focus on targeting the cardiotoxic process directly? And then embedding cardioprotective studies in cancer trials may be a step forward. Thank you for your time.
Thank you very much. Our next speaker is Dr. Thanathan, who is a professor of medicine, director of the pulmonary hypertension at the University of Minnesota, and he will be discussing pulmonary hypertension and cardio-oncology.
Thank you for the invitation. So first I want to thank the organizers, Dr. Konety and Dr. Blaes, for the kind invitation, and the respected chairs, ladies and gentlemen. I'm new to this meeting, so just to get me oriented, because I've never attended a cardio-oncology. How many oncologists are there in this group? Raise your hands if you're an oncologist. Okay, so how many cardiologists? Oh, got it. Okay, good. So that makes my job a little easier. So I'm a cardiologist. I focus on pulmonary vascular disease and right heart failure. So the invitation for me is discuss pulmonary hypertension and cardio-oncology. This is the first time I'm giving this talk. And the reason why so far we are not involved in cardio-oncology is it's never been a problem, but with growing cancer therapeutics, pulmonary hypertension has become an issue. So I think it's a very appropriate topic in this decade. So these are my disclosures. And the most important disclosure is the first time I'm giving this talk. Okay, so moving on, for people who are not cardiologists, how do we define pulmonary hypertension? So pulmonary hypertension is a hemodynamic condition. It's defined by a mean air pressure greater than 20 millimeters of mercury during a right heart catheterization rest. Okay, there. If you do have pulmonary hypertension, then we look at your pulmonary vascular resistance, and if your pulmonary vascular resistance is greater than 2 units,
We call it as pre-cap. So what is it then? Post-cap. Sometimes when you have heart failure, when you have elevated left side of the pressure, that causes increased conditional levels, that causes increased PA pressure. So that's called post-cap. But in those cases, your resistance would be normal, but your resistance is highly probably the pulmonary hypertension, but it's pre-cap. We classify pulmonary hypertension into 5 different types. It's called WHO classification of pulmonary hypertension. It's not a perfect category. It's a clinical working framework. There's more research in the field to differentiate them phenotype of better because they can be overlap. But for now, we classify them as 5 different groups. You can see to your right most is you're in group 1 or pulmonary arterial hypertension. This is problem in the blood vessels in the lungs. The blood vessels are remodeled. The distal capillary arterioles. They can be idiopathic, they can be genetic or heritable, or they can be associated with a systemic disease like scleroderma, portal hypertension, and generalized. It's very rare. It's 50 million prevalence. The second category is called the group 2 pulmonary hypertension, which is due to left heart disease, which is the most common. It can be post-capillary or recapillary. The next most common one is group 3 or pulmonary hypertension due to chronic lung disease. Any lung disease that causes hypoxia, COPD, ILD, obstructive sleep apnea, VCD hyperventilation syndrome can cause pulmonary vascular pulmonary hypertension. The fourth category is CTEV or chronic thromboembolic disease due to blood clots. And the fifth one is miscellaneous causes. So going back into pulmonary arterial hypertension, it's characterized by progressive growth of the small blood vessels and basic constructions. You can see on the top cartoon to your right is a normal small pulmonary artery. To the left is a remodeled pulmonary artery with like intimal thickening, smooth muscle thickness. And the schema below illustrates the same. This slide is one of my favorite slides. It just highlights what is the natural history of an untreated pulmonary arterial hypertension. The x-axis is time, y-axis is different hemodynamic variables, and they are divided into 3 different columns: pre-symptomatic, symptomatic, and decompensated phase. In your pre-symptomatic stage, when you are first diagnosed or when you're starting to develop pulmonary hypertension, when the patient starting to develop pulmonary hypertension, their PA pressure and PVR, mean pulmonary artery pressure, pulmonary vascular starts to go up. When your cardiac output is maintained, right ventricle attached to a very sympathetic port that maintains by hypertrophy. So patients who might be asymptomatic, but once over time, as the disease progresses, as PVR continues to get worse, the right ventricle starts to decouple or uncouple or decompensate. It no longer can maintain the cardiac output either at rest or with exercise. And that happens, patient starts to feel the symptoms: shortness of breath, chest pain, lower extremity swelling eventually. Over time, the right ventricle starts to fail and eventually can lead to death. Regardless of what type of pulmonary hypertension I discussed in my previous slide, is associated with BADX. PH is associated with increased mortality. This was recent data we published from a multi-center cohort in the United States called the PVDOX cohort. It looks at group 1, 2, 3, 4, 5, and you can see every type of pulmonary hypertension is associated with increasing mortality. Group 3 or lung disease is the worst. Group 2 is the next, followed by group 1 and group 4. Okay, so then coming to the link between cardio-oncology and pulmonary hypertension. Well, sitting here is thinking pulmonary hypertension is slightly different from all other topics we're discussing because pulmonary hypertension, unlike other complications related to chemotherapy or cancer therapeutics, can also be related to the cancer itself. So pulmonary hypertension can complicate the malignancy itself. So the link between cardio-oncology and pulmonary hypertension can be due to cancer therapeutics, underlying radiation, malignancy radiation. Okay. So first, let's look into cancer therapeutics. This is a study published by my French colleagues, and this study looks at what are all the drugs that are associated with pulmonary hypertension. So what they did was they invented this pharmacovigilance database from WHO called WICI database. It's a database which collects voluntarily reported side effects. And they did a statistical analysis or disproportionate analysis where they look at the incidence of an adverse event related to a drug compared to other adverse events related to the drug. And if you have a higher disproportionality analysis, like an index, that means there's increased risk. And you can see here, there are a lot that projects well But there are a variety of the drugs that are implicated with common hypertension. Some are very well described, some are probable, some are passable. On the very well described, the main group is your alkylating agents, which is quite commonly used by now. This next is the tyrosine kinase inhibitors, followed by interferon, and then other anti-neoplastic and chemotherapy drugs. So this spectrum is growing. That means we are going to see these patients in the future more and more. So we need to be cognizant of this and be aware of it, treat it better. So focusing on one of the few drugs that are particularly associated on hypertension side. It's a tyrosine kinase inhibitors are the main group of drugs that are associated with hypertension. This is again by our French colleagues published, the largest study so far published. What they did was they did a similar approach. They did a pharmacovigilance approach, and they went to this WHO BICI database, which is a pharmacovigilance database. What they found was there were approximately 400 patients with pulmonary hypertension that was reported and related to tyrosine kinase inhibitors. Out of the tyrosine kinase inhibitors, there are 28 protein kinase or tyrosine kinase inhibitors that were reported. There were more than 100 reports, close to 400. If you look at the top right-hand panel, there's a graph that gives you the relationship of like the disproportion of the index for different tyrosine kinase inhibitors. The most prominent one is for the dasatinib, followed by a few other kinases. But there were 4 that were close, but the dasatinib was the one that was very, very close. The bottom panel looks at the number of case reports reported and the time the drug was introduced in the market. Immediately after the drug was introduced, there was an uptake in reporting of pulmonary hypertension associated with these drugs. Then on your left-hand side top panel, that's a correlation map between the disproportionality index and affinity of the tyrosine kinase inhibitor for those tyrosine kinase. And interestingly, the correlation was very high for tyrosine kinase inhibitors for the SRC kinase, which is dasatinib does. The rest of the kinase inhibitors were not that much. Then they looked at the relationship between the doses and the number of events. There was really no, the tree map here on your left lower-hand panel shows the relationship. There is no relationship between the doses and the number of events. Even like on the standard dose, the number of events are high. So how does TKI causes pulmonary arterial hypertension? It has been shown to cause increased smooth muscle proliferation and endothelial cell dysfunction. It can increase mitochondrial cross production and oxidative stress. It also got vasoconstriction. Again, no relation to the dose or duration of exporting. The second concept I want to introduce is something called PVOD, pulmonary vascular venous disease. It is a category of group 1, but in group 1, generally only pulmonary arterioles are affected, but in some patients, you can also have venules and capillaries also affected. This is called PVOD. And how do you differentiate them from PAH? On this pathology would be the best, but we cannot do biopsies on these patients. We have very severe tolerated. We do a CT scan, and the CT scan on the top left-hand panel, you can see this increased ground-glass opacity, pleural effusion, mediastinal cardiopathy. And the bottom picture shows autopsy of a patient who dies of PVOD with venular reporting. Why do I mention PVOD? Your alkylating agents, graft versus post-reaction, which oncologists always encounter, can manifest as PVOD. So the common drugs are cyclophosphamide, metamizet-C, and cisplatin. Graft versus post-reaction. In the early cases, it's an endotheliitis. Because of the autoimmune process, there's endothelial cell dysfunction, which can cause this problem. How do you clinically diagnose? Usually patients are present with group 1-like symptoms, but they will have very profound hypoxemia, like out of proportion to the organ dysfunction you're seeing. The problem is very, very poorly responded pulmonary vascular therapy. Most of them will need bilateral lung transplantation. Obviously, if they have an underlying malignancy, that's a problem. So it could be a death sentence for many patients. The next group of drugs is interferons and pulmonary arterial hypertension. Both interferon alpha and beta are associated with PAH. It's been shown in both experimental and patient-related studies that there is a relationship. The way it does it, it increases as interferon, IV protein, and endothelial pulmonary artery smooth muscle cells. So it goes and binds to the interferon receptor in these pulmonary artery smooth muscle cells and endothelial cells, and increases this protein level. This protein is a mitogen, it causes smooth muscle proliferation, it causes vasoconstriction. So if you really knock out the receptor, even if the receptor knockout mice, they don't get this pulmonary hypertension getting better, moving the FACC. The next group of drugs is HER2 receptor antagonists. The most common one is the trastuzumab emtansine, the TDM1. This is again a pharmacovigilance study. So you can increase, you can see the auto words, the disproportionality of that. It's very high. None of the other HER2 receptor antagonists are associated with pulmonary hypertension. The landscape now moving on from cancer therapeutics to cancer themselves. The most important malignancy need though is myeloproliferative disorders can be associated with pulmonary hypertension. The carton on your left, the essential thrombocytosis and polycythemia vera can cause hypercoagulable small distal vessel clots, and it can cause chronic thromboembolic or type 4 pulmonary hypertension. However, myelofibrosis on the other end can lead to pulmonary arterial hypertension. So this study is again from the French colleagues who are leading in the drug and WHO. 90 patients with myeloproliferative disorder, 42 PV patients, 35 ET, and 13 primary myelofibrosis patients. Their survival is extremely poor. You can see the median survival in this one be like 3 years. I want to introduce this concept of pulmonary tumor thrombotic pipeline job. So some cancer or gastric cancers can metastasize to the can cause vascular metastasis and present as pulmonary hypertension. So this metastasis causes intimal proliferation of the arterioles. Usually patients present with acute, rapidly progressing pulmonary hypertension, organ failure, inevitable pulmonary hypertension, organ failure happens over years. These patients present, I was okay 6 months ago, I'm not okay now, they got a cardiogenic shock immediately. So it's rapidly progressing. You need to have a very high index of suspicion. The diagnosis is usually delayed, and you need to look at radiology and other things to diagnose. CT scan would be helpful. You see a ground gas capacities in the CT chest or tree in bud appearance. Tree in bud means it's something bad in the lungs. Interlobar septal thickening, nodules and media center putting up at the other close. We don't know how efficacious and safe or pulmonary vasodilator therapy in these patients. Most of them are diagnosed postmortem. So high index of suspicion, treatment underlying cancer, treat supportive care, and big pulmonary vasodilator. So other cancer therapeutics that can cause problems is radiation, can cause lung fibrosis, and that can lead to hypoxia and pulmonary hypertension. Bleomycin can cause pulmonary fibrosis and cause pulmonary hypertension. Same thing as so. When and how to screen for pulmonary hypertension? Look for symptoms. Usual symptoms, Konety symptoms are exertional tremor, chest pain, angina like symptoms, syncope, late symptoms, and right out lower extremity sinusitis. Echo is the screening test of choice, but in the right that the physicians need for confirming the diagnosis. So to conclude, I would say pH can complicate growing number of cancer therapies and several malignancies by themselves. I think as cardio-oncologists, you should be cognizant of this fatal cardiovascular complication for early recognition and treatment so that you can get improved prognosis. Echo is a screening test of choice, but I think there's need for a consensus on surveillance echocardiogram. When should we do it? How often we should do it? I'll stop there. Sorry for taking one.
Thank you very much. The last speaker is Dr. Sebastian Schmidt, who is a true cardio-oncologist. He's a trained cardiologist and a trained medical oncologist. He's an associate professor in the head department of cardio-oncology at the Center of Postgraduate Medical Education, Warsaw, Poland. And he will be presenting on cardiovascular surveillance, SGLT inhibitors, and novel therapies after cancer treatment.
Thank you for sharing this in medicine introduction. Ladies and gentlemen, great honor to be here and to be speaker of its such excellent session. My purpose is difficult because I have a huge topic and a few minutes for discussion. This is my disclosure. So I prepared 4 questions for you, and I will try to answer at the end of my lecture. And the first question, do we need cardiovascular survivors in CardioOncology. Look at the data from Cardiotox registry. This registry included mainly breast cancer patients treated mainly by anthracycline with anthracycline-based chemotherapy, sometimes with anti-HER2 therapy, and we can conclude that 3% of patients could experience severe cardiovascular toxicity, cardiac toxicity, and this toxicity may lead to significantly increase of mortality. So I would like to be focused on these patients with mild cardiovascular toxicity, because we can try to avoid future cardiac damage by cardioprotection. I like this study because this study confirmed me that when we observe patients with abnormalities in GLS, when we use cardioprotection very early, and in this way we can avoid the significant decrease of ejection fraction, and I believe in this way we can protect the future of the health of cardiac muscle for future, better future in our patients. And I would like to remind you that the highest risk of cardiotoxicity is observed in high-risk patients, but is the same group of patients may be at risk of high mortality, not only cardiovascular, but all-cause mortality, including oncological mortality. So we should be focused during surveillance of this special group of patients, high or very high risk. And of course, I like this document of guidelines published by the European Society of Cardio-Oncology. Congratulations to Alex and Teresa for leadership. And as you can see, we should recommend more frequency of echocardiography examination in high and very high risk patients. And the same we can recommend in patients during treatment with anti-HER2 targeted therapy, but include only examination by echocardiography, because the indication for biomarkers is more weak, because we should consider biomarkers in high and very high risk patients, and may consider only in low and moderate risk patients. So the difference in monitoring is significant between patients treated with chemotherapy with anthracycline and in women treated with anti-HER2 targeted therapy. And please remember about the echocardiography examination 12 months after the end of chemotherapy with anthracycline, and the same for patients for women with breast cancer 1 year after completion of anti-HER2 targeted therapy. And sometimes we should recommend echocardiography 3 months after the end of chemotherapy and cancer therapy in high or very high risk patients. This recommendation came from the data published by Daniela Cardinale. Daniela confirmed that the highest risk of cardiac damage, decrease of ejection fraction, may be observed during the first month after completion of chemotherapy with anthracycline in breast cancer and lymphoma. And in this period, our heart failure treatment is the most effective. So we should recommend echo examination during the first years after completion of chemotherapy with anthracycline. My second question is, do we need cardiovascular surveillance during long-term follow-up? We may discuss about benefit and the cost. Look at the data published by my research group, Polish Lymphoma Research Group, and independently of mortality related to lymphoma, we observe the significantly higher cardiovascular mortality in patients with arterial hypertension. Arterial hypertension is only medium risk factor, but in these such medium risk patients, we observe significantly higher risk of cardiovascular mortality during long-term follow-up. And I like this recommendation from guidelines published by the Society of Cardiology because, firstly, low-risk patients may remain low risk after the end of cancer therapy, and we should regulation every year cardiovascular risk only. The same we can do in patients with moderate risk, and such patients may remain after completion of cancer therapy in moderate category risk. But in such patients, we may consider echocardiography every 5 years. But we should notice the other situation in high and very high risk patients. Of course, such patients may be defined by the baseline evaluation before anti-cancer treatment, and such patients may stay either permissive cardiotoxicity in high or very high risk. But the low risk or moderate risk patients may become high or very high based on the type of cancer therapy and type of cardiovascular toxicity during active cancer treatment. And such patients should be evaluated by echocardiography. We should consider echocardiography 1 year, 3 years, and 5 years after the end of chemotherapy with anthracycline. And the next point is the reevaluation after 5 years after the end of chemotherapy, because in this way we can define the late high risk of patients. As you can see, poorly controlled cardiovascular risk factors may define these patients, and we should consider cardiography every 5 years after the end of chemotherapy. This is very important and very practical in my opinion, and a key recommendation where we recognize at least moderate cardiac dysfunction related to cancer therapy. We recommend for such patients ACE inhibitors or beta blockers. And as you can see, when we recognize only mild cardiac dysfunction, we may consider this JACC because we need more data about the efficacy. And my next question, do we need novel therapies in cardio-oncology? I believe yes, because look at the data from this meta-analysis. I'm sure that you are not happy after analysis of this data, because the benefit associated with FACC inhibitors as primary cardioversion is not significant in patients treated with anthracycline or anticoagulation therapy. The benefit associated with beta blockers is smaller, clear, is significant, but in my opinion, clinically non-significant, because the differences in protection of value of ejection fraction is very, very low, and only observed in breast cancer women and during treatment with HER2-targeted therapy. And may be observed tachycardia in many breast cancer patients, and in this way, I believe that beta blockers may be effective. So I think that RNE may be the good choice for the future in cardio-oncology. This is a very small study, 28 patients and Argentinian authors instead of analogue or Siddartha, they use sacubitril and sacubitril/valsartan, and in this way, the patient achieved an improvement defined by the increase of NT-proBNP and improvement in clinical study was improvement exercise tolerance. And this next study, the largest study I found, but as you can see, the number of patients is very low. But this study included control group, and we compared the benefit due to treatment with sacubitril valsartan is very clear, significant. In my opinion, the most important result of this study that the benefit is independent of the baseline value of ejection fraction. So patients with heart failure with preserved ejection fraction may experience significant improvement. So I believe we need more data, especially in patients as primary prevention with sacubitril valsartan. There are two ongoing studies, one in Norway. Our colleague Jaiswal is one of co-authors, and second one in Poland. My colleague Mateusz Dicer from Lipshultz is the leader of this study. And my last question, do we need flossings in our daily practice in cardio-oncology? I believe yes, because look at the data published yesterday by JACC CardioOncology, clear benefit of primary prevention with flossings in cancer patients with diabetes mellitus, and of course without cardiac dysfunction at the beginning of analysis, and flossing may lead to improvement, decrease the risk of cardiac dysfunction during treatment with cardiotoxicity. And this is very important, and that all patients could experience the benefit instead of patients with myeloma treated with proteasome inhibitors. And I believe that we will be focused on this special group of patients. And the second very important study published at the beginning of this year, flossings as secondary prevention. So once again, cancer patients with diabetes mellitus and with recognized cardiac dysfunction related cancer therapy, different cancer therapies, and clear benefit as secondary prevention, and all patients could achieve benefit. And in my opinion, the most important result that all-cause mortality could be significantly decreased. In my opinion, the most important for our daily practice. But at the end, please return the discovery and published 1 year ago by our Canadian colleagues. And as you can see, diabetic cancer patients treated with anthracycline-based chemotherapy may experience benefit due to flossings, but the risk of heart failure and any cardiovascular disease is clear, but not significant. So I believe we need more data for our daily practice in cardio-oncology, and I'm happy that in Poland we have the study focused on primary prevention with empathy flossing for patients with chemotherapy with anthracycline, lymphoma patients and breast cancer patients. This is ongoing study. My colleague Anna Porowiec is the leader and co-investigator, and maybe in future, we can conclude the benefit of flossings in patients, lymphoma patients and breast cancer patients treated with chemotherapy and anthracycline-based chemotherapy. My conclusion very clear. I feel that we need more data for evidence of flossings that with valsartan. Thank you for your attention.
So I suspect we don't really have time for questions. I want to allow us to move on in the interest of time. Two questions? Okay, great. So we have time, I guess, then for a couple of questions, if anyone has.
I have one question. To Dr. Konety,
Can I ask?
Yeah.
Could you walk us through the rule of right catheterization in confirming the presence of pulmonary fibrillation in patients receiving the diazepam after the echocardiogram? After the echocardiogram, do we always need to confirm the presence of pulmonary hypertension in this group? And if a patient has pleural effusion, should we treat them before to advise suspending the treatment?
So thank you for the question. So your question is, if a patient with the CTM kind of be emotional elevated pressure, do we still need the right catheterization? The answer is yes, because echo is a good screening test, but as we know, you can underestimate or overestimate the pressure. We need to know the severity of pulmonary hypertension as a pulmonary hypertension clinic for us to plan treatment. How bad their pulmonary vascular system is, what is their cardiac index, what is their INH. Really, sometimes these people can also have an elevated ventricular pressure, so you want to know what their left side of their pressures are. So in general, it's a good idea to do that and inform the diagnosis, especially before you start them on a pulmonary based or diabetic. Pleural effusion in general should not change your right heart dynamics, but it should raise your suspicion for more left-sided heart failure, because right is not failure of the failure and because of the effusion.
Thank you. I've got a question for Anita. I'm going to feature several because I am a big supporter of permissive cardiotoxicity. We put it in the accepted management algorithm in the guideline. But there is that study from Memorial Sloan Kettering doing cardiovascular exercise testing and follow-up years, 7 years in median after trastuzumab. Women who got dysfunction during treatment, even though they then recovered their EF, had impaired long-term cardiometabolic function. So how does that make you think about what we should be doing, in particularly the cured group with early invasive cancer who broke their ventricular function?
Alex, very thoughtful question, and clearly I don't have a clear answer to that. But I think to get to that point, the patients first have to survive and to get to that point. So it's a risk benefit, and I think that's why that multidisciplinary discussion and the shared decision making comes into effect. And we don't know what they would have done if we didn't continue their trastuzumab too. So really, I think it would be like follow the scholar patients and see what they do with their VO2s. But I really think the cancer prognosis is so much of an immediate issue that to let that go in the face of thinking about some issues in the future may not, it really depends on what decision we make with the patient. So I don't know if I gave really a clear answer. I don't have a clear answer for you, but that would be
Yeah, I think there are probably two comments. One is, if you're letting someone have permissive cardiotoxicity, which we would support, they are now high risk long term, and that they should be then followed up using the high risk algorithm for survivors. And the second thing that maybe we as a community need to think about is the gradation of the permissive toxicity. When it's mild, and when are the tipping points on biomarkers, imaging that lead us into a higher risk. But you're absolutely right. We've got to keep the cancer therapy going because that's the overall greater benefit.
I think the other bigger question is, what do you do with that therapy once you started, right? The GDMT. Because in heart failure world, we see very often that patients that stop their drugs on their own, they do well for a while, but then they come back and then EF drops again. So I feel like the cancer patients may be lost after we do this initial thing, and that would be really important to continue and answer that question. Is it the same? I don't know why it would be that different from the general heart failure population. Hey, thank you. On to the next question.
Good afternoon. My name is Dr. Heather Blaes. I am from here from the University of Minnesota. My co-chair for this session is the esteemed Dr. Jean-Bernard Durenan from MD Anderson. And in this session, we're going to be talking about advances in radiation therapy around the world. We have two presenters today. The first is Dr. Carmen Bergam from Washington University, and the second will be Dr. Sarah Alcorn from the University of Minnesota. We will have time after both presentations for questions. So at the end of the presentations, if you just want to use the microphone. Up first, we look forward to hearing from Dr. Bergam.
Thank you so much for the opportunity to speak to you today. I know there was a survey a little earlier this afternoon about the number of oncologists and cardiologists, but how many radiation oncologists do we have here? Besides the other speaker? Okay. Good. Well, hopefully we'll impart some additional knowledge, and we're happy to discuss more later. So, here are my disclosures. So, as you know, radiation-induced cardiotoxicity is a clinical problem, and it manifests in a number of different ways, and it stems from injury in a number of different manners in the heart and vasculature, and it can be modulated by a number of different clinical and patient-specific factors. And a key thing, a key message is that biomarkers and preventative therapies, for the most part, are lacking. So I'm going to briefly go over some of the basics in biology of radiation-induced heart dysfunction, give some historical context, and some ways in which it's kind of come to the forefront in some of our normal tissue injury work in the radiation field, and talk about changes in heart radiation exposure over time. And then I know Dr. Alcorn will expand upon that, and talk about dose-volume relationships and cardiac outcomes and how that is going to change how we treat as radiation oncologists and hopefully the amount of side effects you see from our patients, and into the future, how to optimize and personalize care. So radiation therapy is received by about half of all cancer patients, and this includes breast cancer patients, lung cancer patients, esophageal cancer patients, and thorax. And often these patients are exposed to incidental heart radiation as part of their treatment. We know that the number of cancer survivors from thoracic cancers is expanding with improved outcomes, and so we have to pay attention to the symptoms and manifestations that might occur from this radiation exposure, and it also includes carcinoma patients. So radiation can improve cancer-specific survival, but heart radiation can cause long-term toxicity. And we know that patients who receive radiation therapy in thorax are receiving often additional other systemic therapies, which may include anthracyclines or other chemotherapies, but also now with immunotherapy and other systemic therapy, HER2, targeted therapy, for example, but it can also have cardiac toxicities. And many patients are already at high risk of coronary artery disease and heart disease because of their risk factors, and that also predisposes them to getting many cancers. So the mechanisms of radiation-induced cardiac dysfunction are many, and I'll just highlight a few of them. They're schematically shown here. But it's thought that one of the key injuries that happens initially with radiation therapy is injury of the endothelial cells, which, if you think of the tissues and cells in the heart, are the most radiation sensitive. So this can lead to destruction of the endothelial cells, injury, apoptosis, leakage of the vascular barrier, and downstream effects from that. Of course, radiation, like many chemotherapeutic agents, can cause DNA damage and reactive oxygen species increases. Also, it can cause inflammation, and it's not just inflammation initially. There's a lot of initial inflammation, but there also can be prolonged inflammation 1 to 2 years later. And this can lead downstream to fibrosis 1 to 2 years later. And mitochondrial dysfunction, like with anthracyclines and other systemic therapies, can also occur. And this is just showing schematically some of these changes. For example, in the vessels, as I mentioned, endothelial cell damage occurs, inflammation happens, the vasculature is usually leaky. We can have rarefaction occur where you have loss of microvasculature, and ultimately fibrosis within the walls of the vasculature as well. Inflammation is complex for radiation. It's time dependent, but certainly most both innate and adaptive immune responses are affected by radiation. And really figuring out and delineating these is very important. Some of our work in the lab has actually shown that perhaps lower doses of radiation can be helpful in some inflammatory conditions in the heart. So it's very complex, but certainly something it's important in the long-term toxicity. And I'm not going to go through this in detail, but certainly mitochondrial dysfunction can occur. This is just showing many of the ways within the lemon transport chain and apoptotic pathways or radiation and through those pathways and also lead to changes in reactive oxidant responses within the nucleus and lead back to changes in the mitochondria. This is just showing some of our lab results from our preclinical modeling, showing an example. This is 1 week after a high-dose exposure of radiation, not unlike many patients who might get an SBRT exposure or treatment for a JACC, for example, with high-dose radiation. And we see huge changes in gene expression. And this is 1 week after radiation in the left ventricular tissue. This is in the left columns are more sensitive rats and more resistant rats on the right. And so obviously we have a huge transcription response there and likely proteomic responses as well. And so all these changes can lead to manifestations in a number of ways, and that's part of the challenge of radiation-induced heart toxicity is how you characterize it and look for these long-term. So this is just some clinical data, and just highlighting some of it, but we can see that there is vasculopathies that can occur. There are also valvular disorders. There can be coronary artery calcifications that can occur, and myomathies and other changes. Pericardial disease is also quite common in those that receive high doses to large volumes of the heart. And if we think of cardiovascular dysfunction from radiation, it actually isn't just the heart. So this was schematically shown nicely in this review from ICOS, recently published, showing that in the brain, the carotids, that pelvic vasculature, radiation can cause changes there, and it's important to keep that in mind as well. So there's really an increased focus on radiation-induced cardiotoxicity, which was propelled forward with this landmark paper published in the New England Journal in 2013 by Dr. Barbie. And a key finding from this was that the mean heart dose in breast cancer patients was associated linearly with the risk of major coronary events. It was a 7% risk per gram of mean heart radiation. And if we look at the 9 years prior to that study, there was about 350 publications, and there's almost 5,000 the nine years after that publication, so about a 13-fold increase in interest in this. And the other landmark paper that I think really spurred a lot of exciting research in this area and highlighted the importance of this, because many physicians thought as doses go down that we don't need to worry about this as much, was this 2015 paper in non-small cell lung cancer. It's called RTOG 0617, a cooperative group randomized trial. They randomized a high dose to a lower dose of radiation for these patients, and they actually found that there's worse survival, surprisingly, in the higher dose group. In a multivariate analysis, higher heart doses were associated, predicted overall survival, so higher doses were associated with lower overall survival. And this led to many people still don't get their cohorts to see it. This was important in lung cancer patients, and of course, it's found to be, and it also highlights its importance since that time with the advent of immunotherapy and other improvements, where we're seeing these patients live much longer. So, as I mentioned, the landmark driving paper demonstrated a linear relationship between risk and events within breast cancer. There also have been other studies of breast cancer and lymphoma that have demonstrated this relationship. And in general, these studies show there's no threshold below which there is no risk. The linear relationship with mean heart test, however, doesn't always hold up. And you could imagine, for example, in an esophageal cancer patient or a lung cancer patient, you could have a much different distribution within the heart from, say, a mean heart dose size, where you could have a large portion of the heart getting 60 or a quarter of the heart getting 50 gray. And it's a mean heart dose of 5 versus the whole heart getting a lower dose of 5 gray. And perhaps those patients would respond differently. So I think the heterogeneity based on where the dose is deposited in lung cancer and esophageal cancer is important. We're going to highlight that just in a couple of minutes. In addition, the risk of cardiac events from radiation also has to do with their baseline cardiovascular risk factor profile. So smoking, hypertension, and diabetes, coronary artery calcifications, and all that show to increase the cumulative risk of cardiac events after radiation. And in general, the presence double the risk, and baseline ischemic heart disease has that near risk of a future event. For example, this was a larger study in breast cancer patients with an 18-year follow-up, and in patients who had smoking and radiation, and they tripled the risk of having a myocardial infarction. So over time, radiation techniques have improved, and Dr. Alcorn is going to be talking about that in a little more detail. We went from 2-dimensional to 3-dimensional treatment, which is CT guided, where we actually trace out the heart and look at dose to the heart. Before we were able to do that. And we also have seen volumes change over time, and improvements of systemic therapy allowing doses to decrease as well. And then we have a number of methods that Dr. Alcorn touched on that have decreased overall risk, which is great for our patients. When we talk about risk for radiation oncologists, we look at how we can minimize dose to the heart, and we have different constraints that we try to limit the heart to when we're planning our radiation. For example, in breast cancer, we aim for a mean heart dose threshold of 3 to 5 gray, even lower than that when possible. When we're treating the lymph nodes and left-sided patients, it may be hard to reach under 3 gray or under 2 gray. However, we've talked about the mean heart dose might not be the best dose to use. And we also use techniques that are more sophisticated, such as something called IMRT you may have heard of, or intensity modulated radiation therapy, where we get low dose spillage in more areas and less high dose concentrated, for example, on the heart. It allows us to have a more conformal treatment. And so it's not really known how mean heart dose would, in breast cancer patients, for example, we saw that it tracks when you have a lower dose to the whole heart as opposed to high dose to the anterior portion, like our traditional tangential plans, which we do all diagonal type time. So really, for us to develop and improve and personalize our plans, we need to have data on what doses are acceptable, which areas of the heart are most sensitive and most important to protect. And we have been amassing this data, and it's really a lot of this data, as I mentioned, came after those landmark papers in 2013 and in 2015. And this is just showing an example from a review that we wrote a few years ago with JACC CardioOncology that outlines many of these studies that look at how, as opposed to the whole heart dose, different regional heart doses, substructure doses correlated better with outcomes and color-coded by different types of cancer. But one thing that keeps coming out is that the LAT and CAPS areas in the left ventricle are important. And there's also some interesting data that's come out with the base of heart as well. And actually, in the last few years, we can add quite a few more studies to this. And so there are some groups that have some consensus guidelines that aren't completely based all upon data. And we try to follow these. And they aren't radiation oncologists, so I won't go through them in detail. But they are at least some guidelines and benchmarks, because if we don't track them and try to push these doses, especially with our more sophisticated treatment methods, you often can get higher heart doses than you need to get. We use this as a starting point for data is needed. It's actually often like hard to meet these constraints if you're treating the lymph nodes at a left-sided breast cancer patient, for example. And looking at dose constraints for lung and esophageal cancers, as I mentioned, the base of heart may be important. And there's some papers that are larger cohorts that have demonstrated that the dose to the LAD, the percent above, getting above a dose of 15 gray is important. And that's showing this in one of the studies here. We can see that those had that high dose percent of the LAD, more than 15 gray of greater than 10%, had a much worse or major coronary events than in those that had it less than 10%. Of course, these are important for us because this requires us to contour and trace out all these structures, which is quite difficult. And it's a lot of work. It's not easy to see these structures. We often don't have contrast CTs. We have motion of the heart, motion, breathing motion. And there are a number of atlases available, but I think the key to administrating, getting this to be more mainstream is to have auto-segmentation methods that are advanced and implemented. That's one of these is shown schematically or shown quickly here. But this is really what I think will help us to advance this and allow us to not only track it, but to limit dosage structures. This just shows the importance of this. This is from a trial of our a publication a couple of years ago. But you can see in this lung cancer patient that the LAD, I don't know if I'll put it here, but the LAD is receiving quite a high dose. It's actually getting 15% is over 60% on the left. But if you optimize it and put that constraint in, you can get the same coverage, the same low doses, and spare that organ. So if we know about it, we can spare it. And I think the other key to this is looking at regional dysfunction. I know we just had a new talk by some ways in which to do this, but if we look at regional dysfunction, I think the wave of the future is looking at dysfunction with certain dose in certain regions, and that's going to allow us to better understand how to best limit doses and minimize toxicity. So in conclusion, radiation-induced heart disease is an important clinical problem. We've had less exposure over time, but patients are still at risk and we need new markers and therapies. The biology is complex, but the more that we know and we're learning, that will help to guide these therapies and biomarkers. And radiation to different heart regions is going to personalize the care so that cardiologists you hopefully will be seeing on toxicity, but also highlights the importance of speaking to the radiation oncologist to ask what kind of medical patient has if they don't know what doses they received. More perspective that as needed to guide personalized care. With that, I wanted to thank you and thank the organizers and also my department in the thank you.
Next, we'll hear from Dr. Sarah Alcorn from the University of Minnesota.
All right, thank you. Thank you again for having me here today. So I'll be talking about advances in radiotherapy and how that may interface with cardiac endpoints. And other than employment by the University of Minnesota, no relevant disclosures. So when we're thinking about radiotherapy approaches and how they've evolved over time, there are several ways that we've been potentially efficacious at reducing cardiac exposures that I'll cover in my talk. I'll talk about new modalities of radiotherapy treatment, better setup and immobilization techniques, and the way that smaller fields and lower cumulative doses have been used in some settings to reduce cardiac endpoints. So I'm going to use as a historical context for breast cancer to elucidate these changes in radiotherapy advances over time. So Tolar and colleagues compared the mean heart dose in tangential breast radiotherapy plans over several decades and showed this really dramatic reduction in mean heart dose over time. So from the 1970s, where the mean heart dose was something like 13 Gray, this was in the era, as Dr. Burgum said, of 2D radiotherapy, where our treatment plans were based on orthogonal x-rays and anatomic landmarks, and we couldn't see the cardiac silhouette or anything else to really avoid cardiac dose. To the 1990s and 2000s, when we started using 3D-based planning and optimized our positioning and other parameters for treatment, such that the mean cardiac dose has been slowly but surely decreasing over time. So I'll tell you a bit about the modalities of treatment. So 2D was based on X-ray and anatomic landmarks. Couldn't really do much to avoid that heart, and you didn't really know where it was necessarily. 3D conformal radiation is an X-ray approach, or photon radiations. I'll use X-ray and photons interchangeably here, which is based on CT-based planning. And in 3D conformal radiation, there's a limited number of beams that are directed in a opposed field, at least at the level of the chest, or of the heart rather, to direct with radiation treatment. So what that might look like is, for example, we might have this posterior lateral beam coming from one side, and then an opposed medial anterior beam. And anything between those beams of radiation essentially gets a prescription dose. So those colored shaded lines there, anything within that red region is receiving 50 gray, which is the prescription of this radiation plan, including the tissues adjacent. And then as you get close to the edge of the field, you'll see the dose decreases rather quickly. So the dose is high within the fields and in the adjacent tissues, but low outside of that target area. So that's 3D conformal X-ray radiation. And then another advancement was intensity modulated radiation therapy, IMRT. And this is different. Instead of having two primary directions of radiation approach, we have several relatively low dose radiation beams coming from many different directions. And where those beams overlap is where the dose is deposited. So we can increase conformality, really focus on the breast and nodal volumes, but that does come at a cost. So as these beams are coming from multiple directions with X-ray, they have an exit pathway, and that results in dose exiting the patient and distributes this low dose bath of radiation, for example, that purple 5-grade isodose line there, into the heart. So, and other structures nearby. So the benefit is conformality. The downside is this exit dose and this increased dose of low radiation over a larger region. And then last is to our X-ray approaches, we have proton radiation. And proton radiation has a different physical property. In the breast region, it's directed anteriorly. And as the proton radiation passes through the tissues, it has a point at which it essentially stops depositing dose. So instead of having an exit dose, it comes in full force and stops. So oriented from the front, you can cover your internal mammary, your chest wall, your axillary nodes in that region. And then there's fairly low distribution of dose in the low dose range around that. So these all have their pros and cons, and I've listed above each of the pictures of average radiation dose affiliated with each of these treatment plans. And so the most broadly used is a 3D conformal radiation. It is fairly easy to set up. It can be delivered in many sites across the country and world. And depending on the patient's anatomy and some other metaparameters I'll talk about, we can actually achieve relatively low cardiac doses. As you remember from Dr. Bergen's talk, 3 to 5 gray, ideally for a mean heart dose, although that may not be the best parameter to measure. We can get those achieved in many cases with 3D CRT and some of the other approaches I'll mention. However, if the patient's anatomy is such where we really need to, say, avoid the LAD, if you look at the 3D CRT picture and the LAD is circled there, and it's in that pathway of yellow, which suggests it's getting 40 gray, which may be quite high. So if you have that from your 3D plan, you may need to use a different approach, such as IMRT. You could avoid those high doses through the LAD, but the mean heart dose will be appreciably higher due to the beams out from many angles and exiting out through that normal tissue pathway. So you pay for it. You get the conformality, but the low dose bath is higher. With protons, you may optimally be able to minimize both the LAD and the mean cardiac dose, but this is our most limited radiation resource. There is a very limited access to proton radiotherapy in the US and abroad, and access to that may be quite limited for patients. We would preferentially use that for patients who need extra dose near the heart. They may have Crohn's disease remaining in the internal mammary lymph nodes, or on a research study, and I'll talk about the randomized study of proton versus photon radiation a little bit later on. So another approach in addition to these modalities has to do with the way we can set up and treat our patients, and this is deep inspiratory breath hold. So deep inspiratory breath hold is an approach that can be used with any of the modalities I just mentioned. We ask the patients to take and hold a deep breath during their radiation planning setting as well as their treatments. And when they do so, the air in the lung displaces the heart posteriorly, diaphragm goes down, the heart goes down as well. So the heart gets pushed back and pulled down further away from the left chest wall in many cases. And you can see these pictures with free breathing versus the deep inspiratory breath hold. If that red line is the line of those tangent radiation fields, the heart is no longer directly in its pathway. And then radiation distance is everything in reducing dose. So this can reduce the dose to the LAD and the mean heart by about 20 to 70%, depending on the patient. So it's our most useful modality really for left-sided breast cancers. Another modality that's helpful is prone radiotherapy. So patients can be treated on a special breast board for prone treatment where there's an aperture where the breast falls, they're laying on their belly, breast follicles through the hole. This physically displaces the breast from the chest wall and the heart. So that can lead to significantly lower heart doses. One downside to this is that it is difficult to treat nodal volumes in Crohn's. So this is really an approach for whole breast radiation only. And it does require that the patient have adequate breast tissue to fall below the breastboard, so it's not really appropriate in the post-mastectomy setting for most cases. So it's a little bit more limited in terms of patient selection, but it can appreciably reduce the cardiac dose. In addition to different setup parameters as well, we've been reducing the radiation treatment fields, and that can have implications for cardiac dose as well. So accelerated partial breast radiation has been recently investigated, and instead of treating the whole breast area, we can treat and select patients the lumpectomy bed with a margin, and that's called partial breast irradiation. The accelerated approach was supported by randomized studies, including NSABP B39 and the Florence protocol out of our colleagues in Italy, and both local control and toxicity are similar or improved with partial breast radiation as compared to whole breast treatment, but it really should be isolated to certain low-risk patients. The inclusion criteria varies across these studies and by consensus groups, but in general, low risk would be unicentric, no negative, size being quite small T1 or small T2, negative margins, and low-risk DCIS if that's the non-invasive treatment being administered. In the lower left is the ipsilateral breast tumor recurrence rate at 10 years for whole breast versus accelerated partial breast radiation from the Florence protocol, not significantly different. So we do have evidence suggesting that for this well-selected group, this is an effective modality rather. On the right lower side, you can see what this actually looks like for photons. The first plan, and VMAT is a type of IMRT. And you can see that in a well-lateralized left-sided tumor, you may achieve an extremely low cardiac dose of 0.5 gray. And for protons, you may be even able to treat a medial tumor on the left right by the heart with an extremely low heart dose as well. And just by being able to treat a smaller volume, it increases our flexibility with bead placement. And so whenever the nodes are not involved or a smaller volume is on the table, we're able to avoid normal structures better. So that's the idea behind that one. I mentioned that we do have randomized studies investigating proton versus photon radiation, and the RADCOMP study is one such randomized protocol for stage 2 and 3 breast cancers. And this is for inclusion of patients for whom there is intent to treat the breast or chest wall and nodes, including the internal mammary lymph nodes. And so after stratification on important factors such as cardiovascular risk and laterality, the patients are randomized to proton or photon radiation, and this is with conventional approach. The hypothesis underlying RADCOMP is that for these patients, proton therapy will reduce the 10-year major coronary event rate from 6.3 to 3.8%. And this is based on the assumption that the mean cardiac dose for protons will be less than 1 gray, while as that for photons will be in the 4 to 9 gray range. This study does have ancillary cardiac study associated with it, and so blood draws, echocardiograms, and questionnaires are filled out and completed by patients at baseline, during, and after radiotherapy. And the primary aim there is for functional alterations, systolic function, ventricular arterial coupling, and systolic deformation. And the secondary aim is for biologic alterations with outcomes such as vascular dysfunction, oxidative stress, and inflammation as indicated by blood and other measures on that study. They are also collecting cardiac information relative to radiation dose to correlate with the outcomes, including the mean cardiac dose and coronary artery doses that we've been mentioning. So that would be the investigation of whether or not this advanced proton radiotherapy is measurably able to impact cardiac outcomes on a randomized study. Then the next question is, who can we completely drop radiation from and thus completely abrogate that risk? So the lowest hanging fruit there has been our elderly early stage breast cancer patients. And studies, including the CALCB 9343 study, have helped us establish that as a possibility. So this study was for univocal T1 breast cancer for women 70 years and older who were clinically node negative and had a margin negative resection. So after lumpectomy, they were randomized to radiation therapy with conventional fractionation with tamoxifen or tamoxifen only. And tamoxifen was used in this postmenopausal setting given the era in which this was conducted, the 1994 to 99. And at 10 years of follow-up, the freedom from local or regional recurrence risk was 98% for the combination radiotherapy and tamoxifen and 90% for tamoxifen alone, and at 10 years of follow-up. So that was statistically significantly different. However, the overall survival and other outcomes related to oncologic care were all equivalent and not significantly different. So the way that this is generally interpreted is that a 90% chance of freedom from local or regional recurrence with tamoxifen alone is a pretty good number. And because this does not translate on this study to a survival benefit, it supports the omission of radiotherapy for women meeting the study inclusion criteria. There's a similar study called PRIME 2, very similar randomization, 65 years and older instead of 70, and the outcomes are nearly identical at 10 years in terms of the local or local regional progression-free survival being improved by radiotherapy, but not overall survival. Again, support for omission for selected patients who will be getting endocrine therapy after lumpectomy. Another important omission study that has been directing our care is the role of omitting nodal irradiation after neoadjuvant chemotherapy. So the preliminary results of the NSABP B51 study have been released, and this was a trial of patients with T1 to T3 N1 breast cancer who received standard of care neoadjuvant chemotherapy and had a pathologic complete response in the lymph nodes. That's what the randomization was requiring of. And if they did have that complete response in the lymph nodes, they were randomized to either the experimental arm, which omitted nodal irradiation, or the standard of care arm, which was breast or chest wall and comprehensive nodal irradiation. So on the experimental arm, if one had a lumpectomy, they omitted the nodal aspect of radiation, and thus were often able to get the cardiac dose lower. And if they had a mastectomy, they didn't get any radiation at all. So quite a step down there based on good response to neoadjuvant chemotherapy. The preliminary results were announced at the San Antonio Breast Conference last year. They have not been published peer-reviewed quite yet, but at 5 years, there is no significant difference in invasive breast cancer recurrence-free interval or isolated local regional recurrence-free interval. Maybe a slight difference if you look at the absolute numbers in favor of radiation, but not a statistically significant difference at that time point. There's no disease-free or overall survival difference. There was some difference on the forest plots to suggest that maybe there are some subgroups for whom radiotherapy may be beneficial. A bit premature to say on the basis of the data that's presented. And presently, people are not dramatically changing their practice patterns based on this. One, it hasn't gotten past the abstract level just yet, and two, it's 5-year data. So I think it is potentially applicable for certain patients for whom a 5-year amount of data would be appropriate for guiding their decisions, as well as perhaps within that group, people who have a complete response in the breast and nodes to neoadjuvant therapy and who have more favorable profiles. Outside of that, I don't think there's consensus on how to apply these data just yet. And lastly, I'll just point out that in light of all of these advances, we still unfortunately see that outcomes may not be equally improved across all patient populations. And our colleagues from the Michigan Radiation Oncology Quality Consortium looked at their multiple facilities within their consortium and found that there were higher mean prognosis measured in Black and Asian as compared to white counterpart patients. And it's seemingly, and you can see that in the bottom left, they had different models that they were looking at, but for both conventional and accelerated radiation, it does look like this disparity was measurable with increased cardiac dose by these racial factors. And if you look at the bottom right, this did potentially correlate with the adverse effects seen in terms of ischemic disease and cardiac deaths that were seen preferentially in the folks getting conventional radiation in the Black population. So the authors surmise that unequal use of IMRT and deep inspiratory breath hold, as well as acceptance of higher cutoffs for cardiac safety at a facility level, might have explained some of these differences. And looking back, it seems that there were certain facilities that did not use the deep inspiratory breath hold. They may have used IMRT more, which correlates to a higher mean cardiac dose, and thus accepted higher safety cutoffs for cardiac dosing. And unfortunately, these were facilities in which the Black and Asian populations were particularly clustered. So this is an access issue, and hopefully not a marker of anything more insidious, but it points out that access is an issue as it pertains to any technology. The perfect example of that is proton radiotherapy, where if we find that there are significant improvements to cardiac outcomes, it is still going to be quite a limited resource. So in summary, modern techniques substantially reduce radiation exposure to the heart, and dose may vary with radiation target and disease site. As I just mentioned, these advances may not be uniformly available or applied to all patients, and that could actually augment disparities that we already measure. Our studies are evaluating the impact of dose to cardiac substructures and to better inform our planning and care. And out of the scope of my presentation today, we do not exactly have the well-known or best practices for concurrent and sequential radiation with immunotherapies or other systemic therapies, which may exacerbate each other in terms of cardiac toxicity. And I'll end there. Thank you again for the opportunity to present.
That's my recording. We do have some time for questions that if you just want to use the microphones.
Maybe while both of you are coming out, just real simple question. You alluded this towards the end. In the United States, do you have a percentage of what institutions are using breath hold, probe, all the things you outlined?
That's a good question. I do not know the answer to that. There are different approaches for deep inspiratory breath hold, some of which are just as simple as coaching a patient to hold a deep breath, some of which involve surface scans of the patient to ascertain if that breath is being held adequately, and some of which even involve devices that go into the mouth and actually provide a little positive pressure and help with that breath hold and measure it. I think probably in sequence to what I mentioned, the commonality decreases accordingly from simple to complex there. Nobody rates.
Years ago, we did a survey of Astro members from our next society. Of course, that is select. That in that survey, as I recall, over half of participants have that, but it does cost like well over $100,000 to get that in one machine room. So it certainly is not available everywhere, and especially if you think about beyond first world, like other parts of the world, it certainly is typically not available. Yeah, but I see it probably in the U.S. more than half of unplayed.
Christine Burry.
Thank you. Yep.
Yeah.
So this is a question for you, probably maybe for Dr. Melbourne. You mentioned the importance of endothelial damage in radiation damage in general. When you think about cardiomyopathy, is this then a microvascular disease? Does this lead to microischemia maybe, or is this a cardiac myocyte disease? And do you know of any experimental evidence for one or the other hypothesis?
In general, the dogma is that the initial insult is endothelial cell damage, and it is known that cardiomyocytes are quite radiation resistant, because they're both mitotic. But certainly, if we irradiate cardiomyocytes, we see cases of reactive species and many changes. It's not clear, in some of our animal models that are higher doses in general, we certainly can see myocardial damage, but we also see endothelial damage. There are some really old studies that tried to calculate that in animal models, and it was thought that the endothelial damage preceded the cardiomyocyte damage, which is what I think where that dogma comes from. But I think that it's difficult to say in patients that it is all stemming from the endothelium. Certainly that is important to lead to cardiomyopathies. But, certainly cardiomyocyte changes happen as well. And how that progresses long term, I think, is unknown.
Steve.
Great presentations. We know radiation is a gift that keeps on giving. And so just two quick questions. One is in our breast oncologist, and I also treat esophageal cancer. So we give a lot of chest wall rads, immunotherapy, taxanes we heard today about the microvasculature. And we do it sometimes concurrently. So we're, as you know, Keynote 5-2 just read out 5-year overall survival. There was no difference. So they don't really see the detailed cardiotoxicity from that study. But that's a study that we're giving
and the JACC, so with immunotherapy. Then we are giving AC chemotherapy with immunotherapy, so we're going to have 2 hits theoretically. And then if a woman has a left-sided breast cancer and she has a germline BRCA mutation, we're performing a mastectomy, so you don't have the buffer of fat tissue. So you're doing direct left-sided chest wall grafts, for example. What are your thoughts? Should we be delaying immunotherapy because we are doing concurrent immunotherapy with RADs? And then, of course, if they have a germline BRCA, doesn't then, creates more issues because they don't have a DNA repair mechanism. So what are your thoughts on what should we be doing? What is the best optimal treatment strategy in these women? And typically, they are young. And so we're going to be seeing these delayed. We don't have 5-year survival, but we're not looking at cardiotoxicity. We're not doing echoes. We're not, for example, really following them. So what is your recommendation for us?
So is your question specifically, say, in triple-negative breast cancer patients who have BRCA mutations?
Well, overall in general, we have about 15% triple negatives tending to have germline BRCA.
So we published a white Astro think tank group about the presence of BRCA mutations and normal tissue toxicities of radiation. There isn't a ton of data on it, but the consensus was from the group, given the data we have, is because these patients still have an intact copy of BRCA that outside of the tumor, but the normal tissue should, the toxicity profiles should be similar. We don't have evidence that they are higher, but that we don't have a lot of data. So the consensus was that if patients need the radiation, they should get it, whether or not they have it. Of course, there's different, PCT3 radiations, things are different. So that was the consensus. However, it is something I think that is important. And now with the addition of immunotherapy, we always are giving it, in my patients at least, they're getting it concurrently. So I have a triple negative breast cancer patients. Often they could be, they're 20s and 30s. Sometimes they're getting left-sided radiation, exposure of the heart. Even if they're getting proton, they're still getting some radiation with immunotherapy. They've already gotten chemotherapy and such. So very high risk. We go off of, the Keynote study, there was like a subset of analysis looking at toxicity, and it didn't show a big difference in those who got radiation concurrently or not. But that isn't a lot of data. It's not long-term data, not great data. I do think it's important to look at, there are a few animal models looking at it, and some of the suggestions are that we probably could have worse toxicity. And so, in these ongoing trials, I think it's very important. Something we didn't talk about, but there was a nice paper a couple of years ago looking at cardio-oncology outcomes in cancer studies with radiation. And even after the Darby paper in 2013, it's still exceptionally low, and it really hasn't changed much. So the more data we can get on this, the better, because we can alter how we're treating patients that are planning, and then also the follow-up and sequential versus current.
Dr. Carver. Yes, my talk starts now. This is more theoretical, because I'm sure there are data. What do you think about the use of statins as the first part of the question, prior to treatment and through treatment, as cardioprotective activity? And then the second part is the role of the SGLT2 inhibitors. Do you think there is currently any role, or there will be a role going forward?
I'll answer the first part of the question, and then I'll have you repeat the second, because I didn't hear that whole part. But as far as that use, there have been some retrospective data. There's been some preclinical data that suggests that it could be helpful. Another recommendation we didn't get time to talk about, but the ICLAS it had a consensus statement that recommended that radiation oncologists look at coronary artery calcification that are plantar scans, because there's, contrast can see that. It's not as sensitive as a specific scan of that, but and we should ensure that those patients for sure are on statins and refer them to cardiology or CardioOncology. And that was really news to many radiation oncologists. It wasn't something we really think about. So I think that is a key point. As far as all patients being on it, or patients with any cardiac risk factor, it's really unknown. But I would say that there is more data coming out with the preclinical models and such that suggest that it would be helpful, and it makes sense.
But right now, we don't typically do that. I think it is important, though, to make sure that if your patient has a risk factor, especially in something risk factors, especially in coronary artery calcifications on your initial scan, make sure they're seeing a cardiologist, check if they're on a statin, and have them see the appropriate physicians for management.
I think I would just add to that attention to the laterality of treatment and the rate and the radiations will be important when we're stratifying such patients, because it's certainly, as you saw from my presentation, not all is equal. So the relative benefits to these interventions relative to the radiation dose should be considered. And I don't think this is straightforward anymore. It's that may have been before.
Yeah, another question.
Thanks for a wonderful session. There was mention that even for implants where the heart is not included in the field, there sometimes can be an increase in risk for cardiovascular disease. And I was wondering if you could comment a little more on that and maybe some of the disease in terms of effectiveness.
I think perhaps that slide was talking about how different areas that we treat, there are risks. For example, in the green, there is risk of microvascular, chronic disease, and cancer patients. There potentially is something with more distant changes of radiation systemically. I think not as much is known about that, but certainly in the areas that we treat. Anywhere about the journey around the body can be affected by radiation, cause a related changes from that.
I think I read something about prostate cancer, radiation for prostate cancer, increasing cardiovascular risk, and same things right-sided and left-sided breast cancer, and both having increased cardiovascular risk.
Yeah, so do you want to speak to the right-sided breast cancer? We didn't show it here, but we have some interesting slides that we discussed. We don't have time to put that all in, but actually right-sided breast cancer patients, especially using 2D and traditional 3D, and they have nodal involvement, do have areas of the heart typically that we're seeing dose. So I think that always just comparing right-sided to left-sided it's a crude way to look at increased dose, but it isn't perfect, and different areas of the heart in addition get exposed with right-sided. There is some interesting data with prostate cancer, cervical cancer, cardiovascular risk. And of course, there can be confounding factors they try to control more, such as endocrine treatment and such. But there certainly are plausible ways in which, and in fact, with animal models where you treat kidneys and areas under the diaphragm, you get cardiac damage. And so it's not just clear how important that is clinically. I think it is something that needs to be teased out in case it is happening and to discover the mechanisms, but not all established, I would say.
We're a question over here.
Excellent dogs, thank you. Should I, as a cardiologist, be risk stratifying patients receiving intrahepatic non-radiation as a higher risk group?
I think, again, it is just going to be reflective of the modality by which we treat it, because there will be many folks who, with a deep expiratory breath hold, or maybe proton radiation, their cardiac dose may be quite low. I think, unfortunately, we just still, as you heard Dr. Burgos talk to, we have this symphony of outcomes that we can look at. We're not totally sure for breast or other cancer sites, which is the primary important site, is presenting mean cardiac dose. And as we were saying, that's not as important outside of the breast world. It's probably not independently important. It's a proxy for something that we haven't measured yet. And we think that the LAD and the left ventricle may be of key importance, but it's not exactly clear what that pathway is. So ultimately, it would be wonderful if we could, either by the calcification route or others, help work with CardioOncology to risk stratify. I just don't think we're quite there yet, or we've had a hard time knowing which data we could hang our hat on just yet.
We have Dr. Anita Jaiswal.
I thank you for really nice lectures. Carmen, you mentioned it briefly about substructures versus base of the heart. And, as I think about it, each patient is slightly different, and then you have these AI algorithms, and how accurate are these in telling us it's the left pulmonary versus, and then there's the pulmonary veins. So is it better to do I would love to hear your thoughts about just that base approach that is being looked at. Yeah, so the base of heart data actually came from some unbiased permutation testing with, I want to say, like 1,100 lung cancer patients.
from a group in Manchester, and they found that survival of these patients, not cardiac outcomes, but survival, correlated to this area near the base of the heart. The difficulty, I think, for a lot of us is, and I've talked to the investigators there, is how do we contour this amorphous area? And they've developed some ways to kind of backtrack and figure out what that area is. And they have a couple other studies that support that. And they actually have some trials, sort of a rapid RT trial, it's called, that's stratifying patients and limiting doses in Manchester. It isn't done a lot. I don't know any other group doing that. It's just in the marvelous area right now. But there's a whole line of research about how accurate it will be, AI-based and Atlas-based contouring is, and motion, and all these different things. I also think it's kind of a proxy. So getting that area lower, if you do contour the LADs, if it isn't perfect in its motion, you're still limiting dose to that area, because as we know, the patient is breathing, there's small movements, there's daily setup, even with imaging. So the dose is kind of feathered around there. So, but limiting the high dose to that area in general is probably helpful once we learn exactly what those areas are and what those dose constraints are. But yeah, I think that it sounds simple, but it actually is quite complex.
We have one more question.
Again, great talk and great series of talks again, Dan Addis. One question that I've still biologically had from beginning, which still I think still rings true today, is what is truly the effect of RT on the arterial vasculature? How much of this actually contributes to the bad risk that we view, that we see of basically overall cardiovascular medicine in this population? I think for years we've always said RT induces hypertension, maybe hypotension, but I don't think anybody really, I'm not aware that's really great data on this. What is your perspective on this?
Are you talking about like systemic arterial?
Yeah, chest and even head and neck/neck, chest, but primarily thoracic artery. And again, I know you've done a lot of great work.
Including that. We actually just did a huge, through the United Nations group on the effects of H and the cardiovascular. We did a huge literature evaluation of all imaging and biomarkers in the arteries and heart. We certainly, studies can show changes in the arteries. There are not as many studies on that. Same with the carotid, obviously, hyperplasia and carotid disease, certainly with the high dose people get with head and neck cancer radiation directly to them. But I would say that arteries themselves isn't clear, but we can extrapolate just looking at the response of radiation in the heart and others, that there is a prolonged wound healing type response that can happen in inflammation. And actually, Dr. Lipshultz has talked, I talked to him after, and he's seen this as well. As someone mentioned, it is like a gift that keeps on giving. And so I think that there is something that probably, if you were to get by this area, it's changed, how often it leads to something that's actually measurable. And that's something like vital side change. I don't know how often that is, but I think the key thing is probably if that patient has additional injury, has something else that comes on it, they may respond differently. They may not respond as well. We actually have some animal models showing that in general with some cardiac findings, but obviously not great data. So I don't know how well I answered your question.
No, you did. And I think the last, if you could switch one thing, I think that I've maybe I'll talk to you about later. What do the preclinical data that maybe affirms or disaffirms all the experience that we've had for so many decades about what it's really doing to the vasculature? So that's really interesting. Thank you.
So I think this concludes our session. We have a poster session and a debate.
Wanted to make a big announcement. So just wanted to congratulate Suma and Anne on truly a phenomenal day, and all the speakers and so next, as today said, is a poster session, 4:30 now at 6 more JACC. We're very, very happy to host this session. I'm very thankful for the opportunity to do so. Thank you.